introduction of you. Dr. Carides is an assistant professor at the computer science department at Rice University. Prior to that, he was a postdoc fellow at IBM, Watson Research Center, and he will give us the talk remotely. Thank you so much for joining us. And yeah, the stage is yours. Thank you.
Thank you very much. I hope you can hear me well. It's really unfortunate that I cannot be here, but actually I'm in Eastern Europe right now. It would be really a stretch actually to fly back to Vancouver. I mean, we just arrived from Houston. So really unfortunate. I'm really sorry about this. I mean, I would like to be part of this very nice workshop, and I would like to thank the organizers for the invitation. The topic of the workshop is about federated learning and vision. So the talk that I'm going to present is not only about federated learning, but it's going to be in general distributed learning, the efforts that we have made the past 3 years at Rice University. It's an idea that it is mainly supported by NSF and Intel, but also like partially supported by Amazon and Microsoft. And it's about the general trend, to be honest, that I see and we all see recently, where big models do not need to be trained all together with the old parameters being, let's say, updated, but potentially there are different ways of like maybe selecting some of the parameters to be fine-tuned. And this is an idea before we go into now the idea of adapters and prompt tuning now in NLP, et cetera, et cetera. So I just find it a very nice idea that maybe collectively we can think about how we can actually train these models. This is a joint work with several co-workers, but mostly I would like to mention Chris Germain from Rice CS that we joined with, thought about this idea. Okay, so it is about efficient distributed learning via the idea of like subnet training, and I will go through it right now. Before I start, actually, the only thing I want to say is that I cannot see you guys. So if there is any question, please come and talk, like speak up if you want, if there is a microphone, and I'm more than happy to answer any questions that you guys might have. Okay. So what is the idea? And I will start directly. What is the idea of initially we called it independent subnet training, but actually it is generally subnet training. And I will tell you the story, like how we thought of it, like from the very beginning, how the idea evolved, and what we have been recently working on. So the original idea started very simply. It doesn't have to do with anything with like a vision. It was kind of like, let's start with an MLP and see what we can do. So what you see on the left-hand side of this slide is a bottom-up representation of a multi-layer perceptron, where you have the input layer, 3 hidden layers, and the output, where you can see things can be dense, like MLPs, and even now, they're a basic, let's say, component of neural network training. Even right now, we're even thinking whether the attention models are actually large MLPs, like the MLP mixer kind of like idea. So it is a basic and a very useful, let's say, model to start with. And you can see that it can be a dense, actually it is a dense operator. Like it might be simple, but if these layers are super wide, then all these edges represent weights. So it means that you have big matrices to worry about. Okay, so in a classical distributed setting, or like federated learning, you would assume that this model is sent to every worker. They are locally updated, and the same updated of size, let's say, models are sent back, right? So it requires a lot of communication, computation, communication back, and you repeat that. And this can be like a burden, right? So the subnet training is the idea of, can we actually create weaker versions of this model by keeping the input and the output layer fixed, meaning that we do not subsample the neurons, the features in the input and the output layer, but we subsample what is active neurons in the intermediate layer. Okay, so what you see on the right-hand side is 3 subnetworks where with black dots, you see the active neurons that we pick to be active for each of these individual weak classifiers, let's call them like that. And you can see that now I don't have to worry about every edge. I just want to worry about the sparse set of the edges that are activated for each of these workers, right? So the original idea, and that's actually I keep using the same image from the very beginning since 2019, where we started this kind of like idea, because I think it is very illustrative. Initially, we thought of this as the sets per layer, the black dots, they are independent for each of the subnetworks. So there is no overlap between the first, the second, and the third, let's say, subnetwork. But later on, we dropped this kind of like idea. Okay, so by just saying that, I'm just saying like, given the original, let's say, network, I generated 3 subnetworks, where 3 is a random number, like arbitrary number here, where the union of the neurons in the subnetworks makes back the original network. This is a small note here. Of course, the union of the parameters of the edges do not make back the original network, but I didn't tell you yet what is the algorithm here. Okay, so what I'm just representing here is like a neural network decomposition. It's not an algorithm, but I just tell you that a big network can always and also carefully be decomposed into smaller, weaker versions of the original network. And maybe by training these smaller versions in a distributed fashion, maybe this is more beneficial than setting the, in some way, instead of setting the full model like back and forth in a distributed setting. Okay. So as I said before, this is not an algorithm. So the question is like, how can I use this decomposition in a classical scenario, like in a federated learning, where usually there is a parameter node, which is, let's say, big companies, it might be Facebook or Google, Microsoft, whatever, that they care about learning a bigger model. And you have a bunch of workers, let's say, and for this kind of like a workshop, let's consider them as smaller, let's say, devices, which actually really fulfill our needs here. Okay, so what the parameter node, like the centralized node, sees is like a current version of the whole model, right? So they see the big model, and what you would do actually in the independent subnet training is, instead of sending the current model and copy that for every worker, you actually sub-select and you select indices, and you say different indices are going to be sent to each of the worker, so that each worker actually is agnostic of the full model at this point. They just see a smaller model to worry about, okay? And by the time they get the current model here, XT represents the current version of the model, but also they do not consider the full model, they only consider the corresponding indices, okay, assigned to each of the worker. They can do some, and like as we do in federated learning, a specific number of like local STD updates, okay? And that's not the end of the algorithm, because as I show later on, if we just decompose that once and we'll let these smaller networks to be trained fully, right? Then this is the idea of ensemble training. It's kind of like you have weaker classifiers that they are not communicating at all until you get at the very end that you're going to use them somehow in order to make a decision. So in our case, we just do a small number of local updates. And this is just one iteration. What I mean by that is like the updated models, the subnetworks, are sent back to the parameter node so that we recreate the bigger model. And in the next iteration, randomly selected subnetworks are going to be created. What I'm trying to say here is that it's different from ensemble methods, because per iteration, with high probability, we're not going to see the same subnetworks created. It might be the case that in the next iteration, worker 1 might see neurons that they were actually updated in the previous global iteration from worker 5. And somehow this helps setting information implicitly among the workers. Okay, so before I continue, I know it is very difficult And because I'm remotely, if there are questions, I would like to answer them, given that right now it is a very basic model. So if there are any questions, I don't want to interrupt with your, let's say, the way that you thought about it. If you think that I should take questions only at the very end, let me know. But if there are questions, I can answer them right now from the audience.
Yeah, there is a question. Can you please come to the podium? Yeah. Thank you.
Can you hear me?
Yes.
Okay, my question is, so when you're saying that you're only providing it with subnets, there is these workers, they're not seeing even the embeddings or anything of that sort?
Whether there are any, what do you mean to see any embeddings?
So is the worker not seeing any full version or anything that's a vectorized version, anything at all?
No, nothing. Yes. So they just see a smaller version. It's not that we distill an information or we embed or we compress or whatever. They just see a smaller version of the big model.
Okay, sounds good. Thank you.
All right, I think we're good. Yeah, Dr. Kurdas is still there. Okay, I think there's an internet issue. Let's just wait maybe 1 or 2 minutes.
Many sorries for that. I don't know why this happened, but let me actually continue from where I was. Sorry for that.
That's fine. No problem.
So let me actually, so what is the vision that we have as a group is like whether we can move away from it's not like a bad thing to do the regular training as stochastic gradient descent where you see the full model, but whether there are like approximate ways of doing training, okay? And this is not the first, like we're not the first to think about approximate training, and I will actually try to connect with existing results. For example, there is this idea of skimming where you have a big network and at some point you make a decision where you say, you know what, I'm not going to see all the components, all the blocks of the neural network, but I'm going to drop some of them for some of the iterations to approximate the training, right? There might be cases where you decide to do an early exit. Still, this is an approximate training because you make a decision not to see the full, let's say, stack of like layers that you have, but you actually say, stop here and exit because I'm happy with that. And recently we have this kind of like ideas of sparsely activated MOEs, like mixture of experts, where there are some layers within a big network where you decide to split them. And because there is like, usually it is a very wide MLP in this particular case, where you say that part of it is going to be, I'm going to create different experts out of it by splitting it. And then I sparsely activate this. All these are kind of like ideas of approximate training, and IST fits in this idea because I'm not saying that it is like, let's say, a completely new idea and breakthrough. This IST, like independent subnet training, is nothing else but unstructured distributed dropout. The idea that I just described is dropout. I just say that for this iteration, I will decide which of the neurons are going to be active, and I'm going to do that in a distributed fashion many times. like for many workers, in order for them to be updated like in parallel and be combined, and you actually keep doing that. Okay. The question is like, can we actually, so what are the main questions, if I want to say, is that instead of just saying this abstractly, can we actually focus on neural network architectures to see how we can actually tune and make sure that these algorithms work per different architectures, whether this is useful for scenarios like federated learning, and whether we can actually provide theory about this. This also, from a different perspective, instead of just algorithms, also connects with systems, like systems in a distributed training. It's not like a new idea since 2010, let's say, for neural network training. We have the ideas of data parallel and model parallel. For example, federated learning is mostly data parallel, where the full model is sent to usually to every worker, but they have their own local data. And that's kind of like the main idea. There are more recent approaches like model tensor parallelism, 3D parallelism, and we have notable implementation, but not in the federated learning scenario. Like we have the cases of Megatron. Microsoft has the zero infinity and deep speed kind of like ideas, where they're mostly used in scenarios like I have a large model and I would like to use a cluster of GPUs in order to train it. But in a federated learning scenario, you have to figure out also like different ways to do that, because now you have to consider that it's not like always like a GPU at the very end. It could be like a lighter, let's say a worker. So what is our idea, if I want to compare it, is an end-to-end, let's say, it's still model tensor 3D parallelism, but it is actually approximate. Because the main difference of IST, the way we split the model, is that, for example, the Megatron is the idea that still splits the model, right? But the idea is that we always reduce back. We always make sure that the iterations of this distributed training is always identical to a regular centralized SGD training. In our case, we have surrogate functions. And the only question here is like whether the path of this approximate training that we follow in a way follows, or it is quite similar to a regular, let's say, gradient-based training without losing much and actually having gains in efficiency. Okay, so this led to a series of papers. It was a little bit difficult for us to convince at first the reviewers. The idea exists until like since 2019, at the end of that, beginning of 2020, we live in the machine learning, let's say, world, a lot of rejections. We managed to publish the first paper in the VLDB 2022, to be honest. But since then, I mean, that's the good thing. I mean, we managed actually to put IST on map, and we could publish more papers on that. Okay, and I will tell you like what was the story initially, starting with the VLDB. So what I actually described to you right now was the case of on the upper left corner, which is the VLDB, where we started with MLPs because we thought that this is the main bottleneck in distributed training. Like you might have convolutional layers, but if at the very end you have, let's say, wide layers, it could be like the majority of the computation and communication that you're going to do. So we consider the case where, yes, you might consider computer vision ideas and applications where you have a CNN at the very beginning, which is global and always shared with everybody. We don't know yet how to decompose a CNN, let's say, layer. But the MLP part, which is most of the weights for the case that we considered, it is going to be split in an IST fashion in a distributed setting. And we tried that. I know it is not the best way represented because I don't want to focus too much like on the results. But if you focus on the right-hand side of the 4 plots, what I want to say is that we tried initially with the full ImageNet. By full ImageNet, I mean the 14,021,000 classes situation, where by having like 21,000 classes at the very end, it means that there is at least one weight matrix that one of the dimension is 21,000. You cannot avoid that. This is the number of classes you have. So it is a very big, relatively for federated learning scenarios, let's say matrix, that in a regular case, you have to set it like as is to every worker. But we say, what if we actually split it, we make it smaller, and maybe we can gain something. And the results were, again, without getting into too much details here, we can get to the same performance or even better. I want to highlight that because that's a very interesting point, in a faster way, both in communication like flops, number of bits, but also wall clock time. So that was a very encouraging thing, that when we focus on MLPs, IST makes a lot of sense. And to be honest, just to tell you, like 2 days ago, I was reading a paper about whether MLP mixers is the new, like, it's all about MLPs. Like if you have enough computation, you can actually set up a big MLP and you're going to have like good enough, let's say, performance compared to even attention-based models, right? And it is even the case that you can increase the dimension of your model, but you can keep the sparsity, like the active neurons, as a small one. And this actually increases the accuracy of the models. Like in general, this is an open question that I'm very interested in. I would be happy actually to discuss it, whether that's the reason why IST actually performs better than training the dense model, to be honest. So that was the initial idea, and I don't want to be out of time. And then we said that, okay, who cares about MLPs? Again, remember, this is back into 2020, where someone would say, I also care about ResNets because I want to do convolutions. I like computer vision applications. No federated learning yet. Okay. So we focused on ResNets, but then in ResNets, you have so many different blocks, like components that you have to care about. It's like you have the convolutional layers. You might have, like, let's say, pooling operations. You also have the MLP at some point. And then we said that what if we do the same idea, but we apply it on the residual block? So residual ResNets is like, the nice thing is like you have the same block repeated many times, most of the network, and you have the skip connections. So we thought that maybe the IST could be applied in a stochastic depth kind of like situation, where from a very, let's say, deep ResNet, let's say ResNet 1, I don't know, 101 or ResNet 200, I can create smaller ResNets by selecting the blocks, make them like smaller, let's say less deep. I train them locally to every worker, this, let's say ResNet 50 to every worker, before I actually go back and I recompile the ResNet 200 and I keep doing that. And it turns out that it works really well in a distributed fashion. Like we managed to really reduce, I'm not talking about even abstract, let's say numbers like flops and gigabits in terms of like computation and communication. We reduced the wall clock time. Like we managed to achieve close to, let's say, the actual linear, let's say, speed up. So for 4 machines, we managed to have something close to 0.5. Given the small data sets we tried with 8 machines, we managed to do like almost 4 times, like we couldn't go beyond that. I think that this is also the limitation of the data set and the model size. But that was quite like encouraging if you compare it to the regular training. You can actually get the same accuracy in much, let's say, less number of like actual wall clock time, let's say seconds. Okay. And that was kind of like the next step, going into more complicated results. There is this also like idea that I really like also proving things. So the question was like, what about theory? Whether what we're doing is kind of like arbitrary and maybe it's kind of like pure luck. It turns out it is not. We managed to theoretically explain, starting with MLPs, why this works, whether there is a connection between the over-parameterization and the number of workers that you have in your system. So the answer here is like, if you really want to use, let's say, 100, let's say, workers, you cannot split the model as narrow as you want, because then you're going to end up with weak classifiers that do not make sense, like they do not help at all. So if you really want to use like a lot of workers, it means that also your model should be bigger enough so that the smaller subnetworks you create is not like they're meaningless. So there was this connection between all these things, and that was very useful and published like a TMLR. And we managed actually to extend this to different, let's say, architectures. We have like proof and connection of all these things, also for SNETs. And as we saw later on, we said that what about other architectures? We tried graph neural networks, where we actually managed to say that this goes beyond, let's say, just regular, let's say, Euclidean space, let's say, data sets. Now you have graphs, you have the adjacency matrices. All these things actually work really well. To be honest, like GCN is nothing else but a variant of MLP also, to be honest. And the nice thing about it was, at least back then, through the IST, we managed to be the first to really consider super wide, ultra wide GCNs. Like what you see here in this bubble, this D is the width of the original GCN. Like we consider GCNs, graphical convolutional layers, with width of number of neurons being at the level of 32K. And we said that if you just call PyTorch, it will not run because it is out of memory in order to handle that. But we managed to say that if you're careful about it, you can still run these models by splitting them into smaller subnetworks and then combining them back. And yeah, that's kind of like the main highlight of this kind of like idea. Okay, so also it is theoretically justified. I don't want to go into that. But yeah, this is kind of like the first, let's say, set of results we got on like IST. And we're really I really like this idea because this slide is more like not to put necessarily a stamp here, but it's just to say that this is an idea that also other teams also liked, not necessarily, to be honest, citing us, but I saw that there are more papers and more ideas that they go towards, let's say, sparse-based, let's say, training. The only paper that I remember reading before our paper comes from Google, that comes from this 2018 paper, where the idea was like only just a paragraph in a paper where it was actually saying, if you have a big matrix of a neural network, just split it into smaller parts and then send these same smaller parts to every workers, the same thing, to be trained and accumulated, and you keep doing that. So it's different from what we're actually proposing. And now you see, like, I know that it might be Nicholas Lane on the call. You have Fjord, which is like an idea co-designed with Samsung. There is like from Google the partial variable training, also federated dropout and federated pruning. And I want to keep this list as the actually grows larger about what we can actually do with sparse training in federated learning scenarios. So it's not the end of the talk, but I just want to say what was the initial take-home message is like IST could potentially be a slightly different distributed protocol because you split the model, you split the data if you want. It's not the regular, let's say, training dynamics of gradient descent. You still do gradient descent, but on surrogate functions that potentially has impact in communication and computation and actually in walk clock time. Okay. And there is also theory to explain some of the design choices that we actually made. Okay. So the question now that I want to kind of like go and start closing this talk is like, where do we go from here? And of course, this is a workshop about federated learning. And that was the original question that also, because it was funded by Intel was really interested in what can we actually do in terms of like federated learning. And we start thinking about the IST in federated learning, where the idea was like, operationally, nothing changes. The whole discussion is, if I do the same decomposition, but now every worker has data coming from a different data distribution, would IST break down and do not work, or would it still work? And without having the results here, actually, it is a paper that it seems to get like have gotten like good reviews. Is that we propose the idea of using pre-trained models in computer vision, where, for example, think of like you have like a wide ResNet or something else as a pre-trained model, and you just use like the embeddings at the very end. And in order to do, let's say, classification, you append an MLP at the very end of that. And we try to do that like in a federated learning. Assume that every worker, the only thing that has to do is to download, let's say, a pre-trained, let's say, DenseNet or two of them. And then you concatenate the output features of the local data. And then the only thing that you have to do in a federated learning is to train the MLP, right? And it turns out that really works really well. Like IST actually performs much better, or at least on par, but way faster than federated averaging or whatever you name it. We tried several cases like Nova, FedNova, and Moon, that actually it's the way to go, because you have small devices and you don't want to train the big model on the small devices. So IST plus FL is something that we're really interested in. We also got into the case whether this decomposition of the models could also be something that could work with asynchrony. Mike Rabat is one of the speakers. They have a very nice work on like asynchrony. We like this idea, and we actually asked the same question: can we actually have IST where the models are not actually in a synchronized fashion, they're aggregated, but maybe every worker just sends the updated model before they get, like, let's say, a stale version of the previous model, etc., etc. Of course, we do not take carefully privacy concerns, whether there is a secure aggregation. This is why, for example, the attempt by Facebook is much better than ours in these aspects. But we saw that you can actually have asynchrony to accelerate training without losing much. So you can actually reduce the communication, work log time, and computation by just having asynchrony with IST, because it feels like hog wild, like this old version of like, how can I actually do asynchronous computation in classical convex optimization machine learning models. There is also theory about this. Don't worry, I don't want to get into that. And one of the last things I want to say is that through discussions with Mike Rabat, he always, I still remember the first question that one of the first questions he made, why do you care about IST? You can actually use a lottery ticket hypothesis, meaning that you can pre-train a little bit, select the core model as a pruning, and then you can distribute this sparsified version for the rest of training. And that was a very, let's say, valid and cool idea, actually, that we tried, that we saw that maybe with IST, you can do end-to-end sparse training. So even the pre-training of the pruning methods could be done in a way that there is no point in training that the full model is going to be trained altogether. So you do the pre-training in an IST fashion, you split the model into workers, etc., to get it to the point that you can actually now say, can I prune, have I got to an early bird ticket, let's say situation where I can select a sparse version of the big model to keep doing the rest of the training? And the answer to that is yes, you can do that. IST, even if it is an approximate training dynamics, it really follows the regular training dynamics, which means that it does not lose the tickets. You can still preserve them. And that's also like a very cool idea in a federated learning scenario. It could be the case that you don't have to train like for the whole, let's say, lifetime of the model, the full model all the time. You can actually do a little bit of pre-training, sparsified with lottery ticket or pruning methods, and then you can keep doing the training with like with smaller models. Okay. Also theoretically justified, etc. Ongoing work is like, okay, everybody talks about transformers or visual transformers in this scenario. This is kind of like attention is not something that you can very easily split. We managed to do that, but now we go to the point, and I'm also like judging our own work where everything is about adapters. Like nobody wants to retrain the whole model. It's a matter of like having a model like GPT where you actually add a little pieces like intermediate or at the very end or even at the very beginning, which is the prompt tuning. And the question here is like, where does IST and all this sparse training can be actually applied, and whether we can actually do stuff on that. So this is something that I would like to thank everybody. I think that I'm actually on time. And again, very sorry that I couldn't actually be here, because I think that it is a very nice workshop. Thank you very much.
Okay, any question? Okay.
Maybe I missed this part, but how do you exactly split the parameters between the nodes?
Yes. Obviously, I skipped a lot of like details, but in most of the works that we actually did, and that's why I call it like unstructured dropout, is like randomly. We do not use any structure for the splitting. So if I have, for example, a layer which is like, I don't know, 4,000 neurons, and I have, let's say, 10 workers, I might choose to assign 400 neurons to every worker, randomly selected. And again, the other thing I want to say is that I never mentioned that there can be overlaps. So originally, the idea was about independent subnet training, that there is no overlap. But it could be the case that you can have actually overlaps among the selected neurons between the workers. In that case, you just average the updated values and you're going to be fine.
So basically the random is done on each node, or is it done on the parameter server?
It is done at the parameter server. And to be honest, I kept the parameter server because it is closer to a federated learning scenario where it is just usually one parameter server. But in that scenario, the parameter server at every global synchronization will say, this is the way I split the model. But it could also be the case that you have a decentralized parameter server where every worker could also be parameter server. And in that case, it's a different scenario, but we also have like this situation implemented.
Thank you.
All right, please go ahead.
Hi, thank you so much for the talk. I was wondering regarding the initialization of the parameters before distribution. I'm not so sure about the overlap situation. So in your case, you're just, if I'm understanding correctly, you're initializing the weights and then distributing them to the workers, right?
Yeah.
Okay. So in terms of initialization, what kind of methodology are you using for the initialization? Just any kind of random. Yeah.
So if you're talking about what are the, let's say, the weights values, is like what you have in the previous iteration. Yeah. It's not that we start from scratch, right? It's like whatever the previous iteration gives me, this is going to be the value that I'm going to send for the selected, let's say, sub networks that I send to each worker.
And even though that you might have some sort of understanding on how the network is oriented in terms of decisions, you're still sending the values randomly to the workers, or sending basically splitting the network randomly to the workers. You're not sending it specifically depending on the classifications weights.
Yeah, I mean, that's the thing, is like there are open questions here that we can actually explore. That's a very good question that I'm sure that there is a better way of splitting the model and making decisions, what kind of values and what would be the indices to send to each. That's kind of like the idea, for example, behind Fjord, where Fjord is it's a way that you decide, there is like a specific decomposition, which is in a way hierarchical. Like you have like a smaller model, but a bigger model that includes the smaller model, and you keep doing like that. If I remember correctly. So there are ways to do it differently. We just thought that this would complicate also the theory behind, like there is no way, or it is very difficult to have like something that it is not random, that at the same time you want to prove something about it. But definitely that's a very interesting question that you actually make.
Thank you so much.
Okay, any other? Okay. Is there time? Yeah, we have time. Yeah.
Hey, Tassos, it's Mike. Great talk.
Hi, Mike.
great to see all these extensions for both, all of the extensions that you're talking about on the slide. I guess two questions, maybe the more urgent one, if you have time, is do you have guidelines in general for how to decide what fraction of the parameters of the network to send to each client? How much you can partition things up, and how does that impact the performance? So how do you think about like what relative fraction of all weights are going to go to a given client?
So that's a very good point. And if I understand it correctly, is like whether you can have an unbalanced, like, can I send like a bigger model to a more powerful worker compared to a smaller model to a less powerful worker, right?
Yeah.
So
That and also if I have a very big network and I'm sending, say 1% of all the weights to a given client, is that much worse than if I could, maybe I could send 25%. But yes, I think the heterogeneous question also where you send more weights to more powerful clients is also super relevant and interesting. Have you thought about those?
So I mean, regarding how small the model can be, like you said, that whether I should send 1% or 25%, I wouldn't say that there is a guideline that I can go on paper and say that based on the theory, this is the send the 1% at a specific worker. Probably this should be such that this 1% does not lead to a very, let's say, small network, because it's going to be meaningless. This is what I'm trying to say. Like there is no pure guideline, but it's kind of like, do not overdo it and send a really, really small submodel, because probably it will hurt rather than help the whole process. Now, regarding unbalanced, I think that we're discussing with my students, but I'm not sure whether we made any experiments on that. But that's a good point. That's a good point. I haven't thought about it.
Thank you.
Right, are there any other questions?
Hi, I have a question.
Yeah, go ahead.
So in health application, particularly, the federated learning works with differential privacy. And so my question is whether adding differential privacy or noise to the model would it affect, in this setup?
Excellent question. And I really like that. I was hoping that Mike is not going to ask more questions because it will be more work for me, but now you asked the right question. This is something that I'm very interested in without being expert in differential privacy. I'm still learning about this, but I have the feeling like because the way we split the model is a random way, whether this actually leads into privacy amplification because it introduces more randomness, or whether it makes it worse. So back to your question, excellent question. We haven't tried differential privacy kind of like ideas. And I'm just curious, even from a theoretical point for a very simple model, whether the fact that you split the model makes the privacy better or worse. I'm not sure whether the audience is more expert than me or anyone there. But I'm super interested about this, and I'm already in touch with people to discuss and see whether we can do something about it. I don't answer your question, but I'm just telling you that I acknowledge that this is not exactly an issue, but an interesting, let's say, open question.
Yeah, I think maybe I can chime in a little bit. So I think that's a very interesting question. Actually, we did some work. We're using the parameter efficient fine tuning in the federated learning. So basically we have say adapter. As you mentioned, you append MLP, right? The adapter is like a small network. So you don't have to tune the entire pre-trained network. You can just pay a small portion. So we actually did the differential privacy part. And we found out that with this because you do the gradient perturbation, right? So, but you are not perturbate the entire network. You only perturbate the small portion of the network. So we found out that the degradation of the performance is not severe as compared to your full train or fine tune the entire model. So I think that's one, maybe the benefit of this kind of sub-network or small portion of the network. You just tune
Very interesting.
with the federated learning. Yeah.
More than happy to discuss that more, Chen. Like, yeah, we can take it offline, but that's a very valid question that, as I said, I remember reading Mike's work on like asynchronous, federated learning. And one of the things that they care about is like secure aggregation and what you're going to do. And this is something that we kind of like skipped over just because we thought that maybe let's try to do our own, let's say, naive way. But I skipped this kind of like vital things which are more like related in practice. Yeah.
Okay.
Thank you.
Yeah, I think we have one more question.
Sure.
Yeah, hi. So regarding the previous question about the splitting the whole network between the workers, is it like more important to put more beneficial to put bigger parts to the workers, or is it some kind of a threshold when it starts to be feasible and beneficial? So like regarding very big networks, you can split them into very big amount of more workers and they will have a lot of work. And given small network, you wouldn't have so many nodes to split between them. And how was like the threshold and trade-off between those?
Very interesting question. So if the model architecture is, let's call it like, it's not that I make like because I have a theory about this, but let's split this between MLP based scenarios and non-MLP based scenarios. For example, for the case of ResNet, we saw that it is more difficult. Like there was also like often the case that you need to fine tune them, like to really tune the model to not have like a small 1% gap between the regular training and our method. So we were losing by 1 or 2% if you don't tune it enough, which means that having bigger and bigger models probably goes closer to what a regular gradient descent will do, and probably it's more beneficial to do that. It's just like the trade-off. I have to send bigger models to the workers, and they have to update bigger models locally. So it's going to be a trade-off. Then it's going to be more time for that, but I'm going to close the gap. Now, if you go back to MLP though, and that's why I mentioned that, there is this trend, and there is also like theoretically justified in COLT, I don't remember exactly, where they say, if you have an MLP, that it is actually dense, keep how many active parameters there are, but increase the size of the MLP. So you're going to have a sparse MLP. This sparse MLP potentially can be better in terms of like tuning and like training and getting like good results compared to the dense version. So in that scenario, having like denser and denser, let's say MLP sent to the workers, I'm not sure whether there is like a phase transition where you actually start not getting as good as IST. I know it is a little bit controversial what I say, but we actually saw that by splitting the model, you can get a performance which is actually better than setting the full model to each of the workers. I'm not sure whether I'm answering the question fully, but that's kind of like what I know so far.
Yeah, that's super cool. Thank you very much.
So are there any questions for the online attendees? Okay, if not, I want to ask you, final question or maybe a comment. So you have this IST is the unstructured pruning, right?
Yeah.
So have you considered like from the software hardware code design point of view, right? Because we know this unstructured pruning is the network may not, take the advantage of the hardware. So like a PGA, if it's some edge device doing that. So have you tried structured pruning?
Yeah, that's something that we definitely care about. For example, when we do IST on CNNs, it's structured pruning because we prune the whole filter altogether, and it could be actually structured pruning. For the case of the MLPs, we haven't tried any of these, let's call it NVIDIA 2/4, let's say ratio, how they call it, like MN structured pruning. just because it's not my expertise, not like I'm a systems guy who is going to really fine tune everything to the level of like exploit. But I understand that this is like an issue. The only good thing of our method would be definitely the fact that you actually send less, for the case of federated learning, you send less kind of like information over the communication, let's say, channel. And even if like computationally, you might end up doing like a training if you're not careful about like over a sparse model, but still it is going to be the same amount of time. Communication wise is actually better. So I agree with your point. And we haven't done much work on that scenario, to be honest.
Okay. All right, thank you so much. So I think this is a very great work for the IST. You have a landscape of the, with this kind of foundation, you can keep building up from different aspects. Yeah, very looking forward to your latest update. Maybe you have the Intel October workshop. So yeah, very looking forward to it. All right, thank you so much for your time. And yeah, thank you again. Thank you.
Thank you very much. Thank you very much, guys.
Thank you. All right, take care. Okay, so I think we have our next speaker online. Dr. Lane, are you able to hear me?
Can you hear me? Hello?
Yes, I can hear you. So I think, yeah, I think we can get started. So I will do a quick introduction. So Dr. Nicholas Lane is a full professor in the Department of Computer Science and Technology at the University of Cambridge, where he leads the Cambridge Machine Learning System Lab. So we are fortunate to have you give a keynote talk. So if you're ready, please go ahead. Thank you.
Sure. Thank you very much for the kind invitation. It's great to be here. Let me just start by sharing my slides. Let's move into presenter mode of the slides. And okay, and then share it with Zoom, share screen. Does that look fine?
Yeah, we can see the screen. Yeah, thank you.
Oh, great. Okay. Yes, so what I want to do today is share with you my views about why we should be investigating federated learning, why it's so important to me. And I want to highlight some of the work we've been doing around the framework called Flower, and then explain how my academic group has been doing some work building on top of Flower in some pretty important directions we feel. And so let me begin this talk by unpacking this title. So the title is kind of deliberately provocative. It's saying machine learning in the data center is the combination of these two things, a dangerous dead end for society and the academic pursuits. And so it's worthwhile, I believe, to define what I mean by machine learning in data centers. And so when I refer to this combination, I'm talking about this ecosystem that you see illustrated on the slide. And so this is the ecosystem that we largely most consumers today can't escape, whereby if you're using Google search, if you're using a smartphone, you're going to find hundreds of models. And in the case of Google search, inescapable, the sort of workflow of models when you do a search or do anything else. Even when you're using something like Netflix, you go home, relax, you can't escape this ecosystem that's evolved, whereby we have, of course, these giant neural networks that must therefore reside in large GPU-based data centers, which are also combined with this need to consume large amounts of static data. And that's what this ImageNet icon is showing you here. So it's this ecosystem here that I want to put forward, that while it has provided us with a lot of beneficial types of technology, things like Alexa wouldn't exist without this type of ecosystem. I think looking back 10 years from now, we'll see a number of negative externalities that we really are going to be disappointed in, that society ever kind of really engaged in. And so I think I really want to emphasize how bad I think this might be perceived in history. And so Let me give you a couple of examples. Back in the 60s, people thought it was fine to smoke. Doctors even recommended, hey, smoking's fine, it's completely healthy. You saw adverts like this. And decades later, people realized that smoking was, it had terrible negative effects to people who engaged in it. And so we basically wish we never sort of promoted this type of technology, this type of activity. It's not the first time though. Another completely different domain, lead paint. There was a time when we painted the interior of rooms with lead paint. It was thought of to be fine at the time. There was a technology that we were fine and happy enough to use it for a period of time. We realized the negative side effects of this and we pivoted away from it. And again, I'm using these as examples to kind of put into context how bad I think history will judge the negative side effects of using machine learning when combined with the data center. And then there's examples I know that we kind of have still in society today, things like the impact on the environment, things like climate change are examples of activities that we have yet to get away from, and it's obvious that we need to do so fast. And then while I guess climate change is a fairly extreme comparison, I think things like lead paint and smoking are analogs of machine learning and data center. And so why am I so negative on this combination? Well, I think because there's a number of negative side effects, one of which is user privacy control. And that's what federated learning attempts to kind of often be used to ameliorate. But there's a large number of other ones that are almost, if not, they're arguably just as bad, if not worse. And so one I want to highlight is the brittleness of the safety, the brittleness of the systems that are built on this ecosystem. So if you're talking about robots, you're talking about smart devices like the smart stethoscope, if the intelligence of these systems reside in the cloud, if it's all data center based machine learning, it doesn't take much for these devices to become dumb again. And that's just a break or a slow down in the connection with the host cloud system. So this is an untenable position for building technology of this kind. Another one would be, it's well known now, the type of carbon footprint, the type of centralized level of control of data centers and the need of having all these GPUs that come with it. Something that I haven't heard focused on too much is that there's a very clear, in my mind, negative externality of using data centers and machine learning is the reliance on data sets that are, although initially you might think of them as being very large, like you can think of data sets such as ImageNet and the ones that have come afterwards and those that exist in other domains as being very large. In comparison to the real world that they attempt to model, they're actually very small. And it's because of their sort of scale and lack of diversity in relation to the real world that I think that they can be pointed at as being one of the reasons why we have quite biased machine learning. So there's a variety of reasons why machine learning ends up being biased, but I think one straight line you can draw is that the small scale data sets that struggle, even at their largest size, to capture the diversity and the sort of the complexity of the real world leads to results that you see on the bottom right-hand part of the slide here, whereby because the source data set does not adequately describe all the different types of faces that one might encounter, it's unable to model accurately large swaths of the population. And so that's one sort of less promoted side effects of this type of learning. Highly related to this is that I think it's interesting just to think of the context of data that we're not using currently. And so this slide here is trying to highlight that even if you think of all the data that's being used to train a model such as ChatGPT, and largely those models are based on web data, based on data that's easily accessible on the internet. In fact, this data, which is commonly thought of as being large scale, is actually dwarfed by the data that's currently unreachable. And so if you think about all the data that's locked away inside people's phones, that it's inaccessible, if you think about all the data that's locked inside various machines that exist within corporations, within nonprofits, within governments that are difficult, if not impossible, to currently access, you can start to see that if we have alternative ways to touch this data, to connect with this data, to train on this data, we can start to have models that are much more representative of the real world and have far less of the biases. And this is the promise that I think that federated learning offers us. In a nutshell, I think all of these reasons push us towards thinking about all sorts of kinds of different types and forms of decentralized machine learning. And although in the past my group has focused on things like on-device ML, which is very inference specific, and although there might be other types of really sexy new types of machine learning paradigms, the knock on often these emerging paradigms is that their accuracy in relation to the conventional data center supervised larger models is that the accuracy gap is just too big. I think when you evaluate what alternatives we have, federated learning is this sort of beacon of hope that we can start to consider and need to start to invest on and make more proliferated, make more mainstream as a way to move forward. What's quite unusual about federated learning as a technology is that simultaneously it is used today by billions of people. If you just take, for example, the Android keyboard, if you take, for example, Android's selection of a recommendation of settings, and there are various other kinds of applications that do exist from big tech. Interestingly, this technology is again used by many people for some daily applications, but also simultaneously, if you think about it, none of the breakthroughs in machine learning in the last N years are actually driven by it. And so it is sort of divorced from the current evolution of machine learning. ChatGPT, AlphaZero, any of the models you can think of and throw at me right now, none of these were trained using federated learning principles. And so federated learning as an approach is completely separate from the current evolution of ML. It's being used by many people, however, and so one could argue that it's currently in the sort of hybrid state, whether it's not really being used in the mainstream to solve the next steps of ML, but it's clearly being used in some places, although those places are relatively niche. And so the question we ask ourselves, the question that I really want the federated and people using federated methods such as CVPR community to think about is how can we transition federated learning to becoming much more widely adopted? When we asked ourselves these questions, we came up with a large number of hurdles as to what prevents federated methods from being much more widespread. Some of these will be very obvious to this audience. So one of these examples would be that most of the systems that you can think about that we see deployed are heavily reliant on supervised labels. And so things like some of these email systems I just threw out there wouldn't be a good application of federated learning because they demand many labels. And labels are very hard to get from, for example, client devices or devices, some of these isolated devices where data may reside, but it's impossible to access that data to label it. Another challenge is that, of course, because by virtue of the approach, we don't have this nice ability to handle IID limitations in the IID in terms of how the data is organized. The data appears at these clients, it appears in these systems based on how it is generated. And so it's very difficult for us to kind of construct nice, well-behaved mini batches where the distributions of the data in those mini batches properly align with each other and are nice and consistent, as we can do in data center-based machine learning. And then finally, a big reason why it's difficult to get it used in the mainstream is the heavy penalties in terms of system overhead, flow convergence, variations between the clients, the fact that basically the underlying hardware of these systems is not it's carefully designed as data centers to really service the training process. And so for all of these reasons, federated learning still remains a niche application. And so we asked ourselves, what would be the important step for us to overcome these problems? And so what we decided to do about 3 years ago was create a framework called Flower, where our first thought, our core thought was to solve these issues. What we need to do is do two things. One, we need to expand the number of people engaged in this topic. We want to make it as easy for any machine learning person to investigate the interesting challenges that federated learning presents as easily as they do any other type of deep learning. And we were sort of, when we looked at the different frameworks and how complex they were to use and how difficult they were to extend, we felt that we were really looking at frameworks that were sort of limited in terms of their evolution, and they were much more similar to the frameworks that existed in the world of just deep learning, as deep learning was still a niche activity. And so we wanted to create a framework that was first and foremost easy and extensible for a wide function of people to use. And so by that token, injecting more energy and community into the effort. The second thing that we were alarmed by was the lack of scale and realism within the evaluations, and the difficulty in achieving those goals were for any of the scientists out there. And so Flower is this open source community driven effort. I'll be talking about the scientific things we've built on this framework in the forthcoming slides. But before we get there, I just wanted to highlight that it's now widely used. There's over 35,000 downloads of this framework every month. And actually just about 2 weeks ago, we ran our developer summit for the framework. And we ran it inside Cambridge. We had 500 people register. We had about 100 people on site. And one thing I want to highlight to this audience, I think it's really interesting, is that we are within this framework, we're going to launch over the summer period, so July, August, and September, a program called Summer of Reproducibility, whereby we're going to offer up $100,000 in awards given out for contributions to building reproducible methods from papers on a common set of APIs so that anyone can use them inside the Flower framework without having to understand the internals. And so if you're developing a new exciting method and you want to compare it against a variety of other methods that exist in the literature, you can come to one place, use one common set of APIs, not having to understand all the different implementation details, and quickly benchmark what you've done against these prior efforts in a very easy way. So over the summer, we want to get to 50 different baselines, and we want to achieve this by incentivizing people to build out or port their efforts into these common set of APIs that we've announced. So this is launching in July 1st. But just to go forward, I also want to mention that any work I'm discussing here with respect to the Flower framework is really this big team effort. There are a number of the core contributors, but actually there are even more than this slide currently indicates, of students, people working in industry, postdocs in my group, and so on, who are building out different parts of the framework to make it easier for people to jump on into federated learning and sort of really start to innovate to solve those problems I was mentioning earlier. So this brings me to one of the core things we want to help facilitate with this framework. And I mentioned realism, but I want to focus not on the realism side, but on the scalability aspect. The figure that you're seeing here on the left-hand side is showing you a number of concurrent clients on the y-axis, number of total clients in the pool, and this is for the evaluation of more than 100 papers doing federated learning work. Each of those blue dots are different papers. I indicated, for example, the FedScale paper there with this red dot. And one thing we realized here is that although the motivation for many of these systems to have a large number of devices working together to generate these models in a federated manner, the very few of them were looking at the type of scale that one would imagine these systems to be deployed on. So they're building algorithms and then testing them under much smaller scale. And that is largely a function of just how difficult it was to do experiments when you had a lot of different clients in the pool. So not just 100 clients, not just 1,000 clients, but potentially you might have a million different clients in the total pool, and you might have 1,000 of them being used every single round. Pulling off that type of experiment was just simply too hard. And that's one of the things that we really wanted to shift the needle on with Flower. And so this green star that's being shown here is showing just one experiment that we did recently with Flower, where we're targeting a realistic number of desktop or server grade GPUs. I think it was about 4 or 6 different types of 4 or 6 GPUs being used to run a simulation of a federation, where we scaled it to, I think, around 15 million clients, where each training round involved 1,000 of those clients at one time. And so this is really just like a preview of the result. I'll show you how we do that in a couple of slides' time. But essentially, the components I'll be talking about are enabling the Flower framework to virtualize the memory usage of the individual clients, and then do a smart allocation of those clients as it's doing the simulation to provide this type of facility. And the Flower framework itself has a lot of different moving parts, like any framework might, enabling you to do things like run clients on real devices, develop on a small scale, do a simulation at a slightly larger scale, and then eventually deploy all within the same framework some new federated application based on a cool new technique that you happen to have invented in the lab. Now this pair of results here are the same, basically telling the same story that the last figure showed, but in much more detail. Left-hand slide is showing you for the Amazon book review data set under different configurations, showing Flowers able to robustly train at the scale of millions of clients. So this is important because for academics who want to investigate the effects of their algorithm at the scale that one might see them be deployed in the real world, it's important for them to be able to easily test them under the scale that you might see big tech run their federations. And so this is a gap that was present for quite a while until frameworks like Flower were able to provide this facility. But scale by itself is not enough. We also need to be able to have a good enough speed as we're doing these simulations to make it realistic for someone to investigate the design space of an algorithm, understand if it's behaving well, and so on. And so this next slide here that shows the figure on the right really speaks to the throughput of Flower when doing such types of simulations. And so this is for 3 different classes of data set. We have 3 different modalities. You have speech, you have image, you have text. We are comparing a recipe that we call pollen included with the Flower framework. And then you can see that the y-axis is the number of clients per second that are being executed during the simulation of these 3 distinct experiments in comparison to FedScale and Flute. And the takeaway message is that FedScale and Flute are being outperformed by this combination of pollen and Flower by 3 to 5x. So this is very important for people who want to explore the design space to start to crack some of those problems I mentioned before. So how do we do this? I just want to sketch out 2 main components to this solution. The first I alluded to before is called the virtual client engine. When you're running simulations of this large scale, one of the scarce resources that you have to sort of manage is that of GPU memory. And so again, remember that the problem space here is that I'm an academic, I'm running a research lab. I might have maybe 4 to 8 GPUs inside my HPC, and I want to use that resource to simulate a large-scale federated system. Now, if I do this naively, I'm going to very quickly run out of GPU space, GPU memory on my GPUs, because if I have millions of clients, they're each going to have their own little piece of the data set and so forth. And so I'll quickly run out of memory. So what the virtual client engine does is carefully instantiate the memory required by clients as and when they're needed. And so when a client is not needed, it's taken off the memory allocation for the set of GPUs. There's much more to it than that, but that's the key idea. It's a nice seamless way to manage the memory as simulations are being run. And then when combined with Pollen is the component of the sort of the ecosystem that makes smart resource allocations. And so we have the first part dealing with memory and smartly allocating memory of GPU memory. The second part, Pollen, is being driven by a model that can predict the execution time and other system requirements of each client that will be performed, the training of each client within a simulation of a large simulation over millions of clients. And this prediction engine, if accurate enough, is then able to do the scheduling of when different clients run intelligently. So you're maximizing the throughput of clients being simulated, irrespective of you're respecting the dependencies of the federated simulation, but you're allocating them to maximize throughput based on being able to estimate what are their resource requirements, and then you're packing them into each GPU and executing them in the order by which you can maximize the throughput. And so this combination of the virtual client engine and Pollen does allocation of work to the HPC resources in a way that's well tuned for the needs of a federated system, but is yet extremely different from the type of allocation strategies that you would have for regular large scale training. And this is why you can't just use some regular type of HPC large scale deep learning training and use that allocation algorithm and scheme across your HPC to run a scalable simulation of a federated system. And that's why you need this type of approaches. So I wanted to just give you a sketch of what that system is and how it allows us to scale up to large amounts of clients, and how it also allows us to drive throughput that's very fast to let you to do realistic types of simulation, to show you one important piece of the framework that we think is influential in allowing people to explore and innovate in these problem spaces. What I want to do now in transition to the remainder of this talk is examine 3 case studies, go through them one by one relatively quickly to highlight how my team in the academic group has used Flower to do different interesting types of FL research. And so I'm going to start here by talking about our investigation to doing speech recognition under a completely federated system, whereby we're not just talking about doing hot keyword recognition where you have a small vocabulary, but we want to train in a federated setting a full vocabulary, full-size speech recognition model. And the reason I picked this work was that it required, and probably the biggest part of this work was to develop an acoustic data set suitable for training an ASR system that actually had the real federated properties that one would encounter if you were truly doing federated learning for such an ASR system out in the wild. And so what we found was that there was a limited amounts of prior work for learning this task in a federated manner, but they all used a data set called library speech, which was and is kind of the canonical data set that you want to evaluate your ASR system, at least in being part of the sort of stack of data sets you would use. The trouble is that library speech is trained over a limited number of different speakers, and they're all doing it under relatively clean acoustic conditions and under fairly homogeneous microphone hardware. And that is completely different to how you'll encounter the speech collected from a federated system, where you'd have in a federated system, you might have thousands of different providers of information, of speech. There's obviously going to be lots of diversity in how people speak. It'd be very common for them to be speaking in very different acoustic environments. Some rooms could be large and echoey, some could be small, some could have lots of background noise. And that is just the baseline of how federated data is going to look like. And library speech completely different from that. So we constructed a data set we felt had these qualities. We based it initially by using Mozilla's Common Voice. We took the French data set and we massaged that until it came out with the kind of properties that I was discussing. For example, having very dynamic acoustic background. And that became the data set over which we wanted to examine training under federated systems. I'm just going to sketch out the sort of the recipe by which we arrived at an ASR system that was able to converge. Initially, given the complexities of this type of data, the prior methods that we saw in the literature just simply wouldn't work. They were unable to cope with data that was truly representative of how federated learning would look like out in the wild. And so initially, we're not able to train. But by experimentally trying different approaches out, we settled upon this solution that uses fairly recent types of ASR architectures. So you can see we're using CTC loss with a sequence-to-sequence attention model. We found that we had to move away from a conventional Fed average approach when we're aggregating the model weights to one that's based on the weighting strategy being driven by the word error rate. So we're aggregating more heavily from those that have low word error rate in terms of the clients. And then finally, we found that we needed to have a warm-up model. So we need to initialize the weights of the model that was trained in a federated fashion using a small number of centralized label data as a way to get this to work. And so in our results, we demonstrated that under very tough but faithful federated systems, this solution would be viable, where we are training for around 4,000 different distinct speakers with a test set of around the same size. And the warm-up size that we needed to have this thing converge was on the order of about 100 speakers. If I just move to this part of the result and draw your attention to the right-hand side, this data set is actually relatively challenging for speech recognition to be done. And so the types of word error rates that we observe are much higher than the ones you normally would see for other data sets like library speech. We saw word error rates of around 20%. But what was important is that we found by adopting the latest methods in FL and also adopting the methods that we developed for this particular task, we're able to approach that word error rate that we see in a centralized version relatively closely, which we thought was quite a successful indication of speech recognition being possible, even under challenging federated conditions. The second case study I wanted to highlight is that of an effort we undertook to measure the carbon footprint of federated learning as an approach. And so many of you will be aware that centralized machine learning has now been recognized as producing a lot of different levels of high carbon, depending on what you're training. And so this figure here is taken from probably one of the earliest papers to really highlight this this property. And so it was taken. It was based on training a fairly SOTA NLP model, whereby if you used all the bells and whistles, if you used things like AutoML, if you used all the different hyperparameter tuning that was sort of common to train this model, you ended up burning and emitting as much carbon as 5 cars being driven for their entire lifetime in the US. So obviously it was untenable. People want to look how we could do better. And what we realized was that federated learning is still, in this transition period of awaiting to be adopted more heavily. This would be a good time for people to start to measure, build models of estimating the carbon footprint of its current design so that we can inform how it's designed in the future to avoid similar types of consequences for federated learning once it's really being pushed into the mainstream. And so I just skipped the next slide. I just wanted to highlight the kind of carbon footprinting method, the gap in the methodology that we had to fill. It wasn't that hard to estimate data center types of carbon footprinting because those methods already existed. So you needed to kind of capture, for example, the types of computation with GPUs. There's this issue to do with having to cool a number of GPUs that were in close proximity. So you needed to model how much energy is required for the cooling. You need to capture things like data transfer and storage, but they weren't as nearly a bigger factor as things like cooling. In contrast, the parts of the model that were required to be able to capture federated learning style workloads need to be able to accommodate a much more heavier workload being done on CPUs, as that was the common sort of hardware you would encounter in a client. There's no need, of course, to cool because these are physically dislocated. There's no deliberate cooling going on, but data storage and transfer becomes, a really critical part of the model because it's very often the data will need to travel over wide area networks, cellular links, or large distances. And so storage, data transfer costs in terms of their carbon footprint need to be adequately captured in the model. Other aspects included knowing that depending on where the components, these distributed components exist and operating, depending where those things are located, you'll have different ratios of converting energy usage into carbon. And so, France, given its use of nuclear power, has a good ratio in comparison to places like the UK as a relative comparison. We have a quite extensive journal article looking at all the variations of federated learning, under which circumstances you have different types of trade-offs. And what we're really trying to do is provide a methodology other people can follow to examine this issue, guide how one would start to redesign certain parts of federated learning, but also highlight when does it make sense to use federated versus centralized learning if you're motivated by the carbon footprint. I want to show you just one illustrative example. It's a cherry-picked example to give you a sense of what we're able to do with this method. And I've picked a fairly interesting one because this is one whereby federated learning has actually a lower carbon footprint than centralized learning. And so this is the training of a ResNet 18. We're trying to increase the accuracy to a 60% level using CVPR 10. And we're comparing a data center based learning when we have a V100, one V100 in a data center. There's a cooling ratio of 1.67. This means 67% of more energy that is spent on powering all the other components needs to also be spent just to do the cooling portion. And then in the federated learning side, we're using 50 different Jetson Xavier boards where they're being recruited with 5 clients per round. And what's interesting here is that even though that the data center GPU is able to crank through the data much more fast, because we don't have to struggle with things like non-iodinous convergence can happen much more quickly. But even though all of this tailwind exists, under this situation, FL is actually able to outperform it in terms of carbon footprinting. And the key issue, the key thing driving this is figures of this kind. And so this figure doesn't correspond to this result, but the pattern exists. And this pattern is that for certain situations in these smaller models with small amounts of data, even though convergence is longer, and so the number of epochs to reach 60% is being shown here on the x-axis, and you can see that the blue line is federated learning, red line is data center. You can see that this one took 8 epochs versus 2 to train to the same level of accuracy. The gradient, the amount of emissions per epoch is much steeper for the data center, and so you can have these trade-offs occur whereby federated learning can outperform the data center. Interesting insight that one can build on. And so now that we're able to measure it, our next steps here is to hope that one can start to redesign federated methods that are much more carbon friendly. The last case study I wanted to highlight for us to discuss at the end of this talk is a kind of a key next step, I believe, for federated learning. It's really looking at how we can start to transition from using federated training largely to learn from labeled data, and instead looking at how we can learn from unlabeled data. Because for most application settings, getting labels from the edge is far more difficult. And so we're studying here an interesting combination of technologies. We're studying self-supervised learning when combined with federated learning under the context of video understanding. And I think this is the first time that these three different components have been come and put together. This was published in a last year at EECV, and we designed a system called FedVSSL. And so I'm not going to give you the details of the construction of the system, but I want to highlight a couple of things. That is, under SSL, the first step you want to undertake is the training of an embedding, whereby you want to train this embedding on a number of tasks where the label is able to be computed. And so you might look at determining if an image has been rotated. You might look at if an image has an occlusion, or a variety of other relatively simple tasks whereby the label can be easily inferred. And then you want to train the embedding to understand if for example, if the rotation is present or not. And then by doing this type of training, the embedding starts to learn a representation that is then useful for downstream tasks. In our system, we wanted to find a way of doing this pre-training and then downstream task training that have minimized the communication overhead within the federated system, and also was viable for low compute clients to participate. And so that resulted in us doing a series of pre-training tasks within the federated system. We have a particular type of weight aggregation and the way that the gradients are sent to minimize the overhead, but then the downstream task training happens in a centralized fashion. And so that's a reasonable assumption we felt, because you could have relatively small amounts of label data for a task like video clip retrieval or action recognition. You could collect these in a more controlled manner, but then you could also start to benefit from very rich data collected from these federated edge devices out there in the real world. What we felt was pretty interesting is in the results of this approach. And so it's the first time, as I mentioned earlier, that someone has shown a system of this kind in operation. We benchmarked on the Kinetics 400. We had in the results you see there 100 different clients, and each client had 8 classes it was doing in terms of the embedding learning. And what was an important takeaway was that we also observed that not only was the system practical in terms of its system overhead, but its accuracy actually was better than the centralized. It was better not only than the basic vanilla form of federated learning using federated averaging, but our methods were also better than centralized, which is something you don't often see in most of these tasks. So it was quite an interesting result. And to analyze this, we looked at the type of manifold that was being trained, and we found that the federated one was much smoother, less peaky in terms of its optimization point, and so it was easier for the model to find it. So federated was acting like a bit of a regularizer. And so those are the 3 case studies I wanted to show you. I'm going to conclude by presenting and discussing a prediction. And so it's a prediction about where I think federated learning can get to in the near term. We can definitely speculate about federated learning on the long term. I could say, oh, we're going to solve all of these problems and then paint a very rich picture. But I think actually sometimes seeing where we might be able to get to in the short term can be hugely attractive, because it can give us sort of some goals to try to hit and an understanding of how the world might look different if we can get there. And so I personally think in the long term, federated learning is going to become the dominant way we train all models. But the first place I think we're going to see it really start to shift the needle and people start to take notice would be in the space of IoT perception models. And so I think if things go well, if the current types of progress we're seeing in a variety of areas maintain, in 3 years' time, I think we can start to see IoT perception systems, as illustrated on the left-hand side, doing tasks such as baby monitoring, doing tasks such as observing people who come to the door through a doorbell, operating using self-learning, so learning the embeddings, and then perhaps either doing fine-tuning for a task either within the network or perhaps as a cloud as an additional step. But having a system of this kind, being able to beat any alternative form of data center based model. And then I think that largely this is going to be driven by the improvements in both efficiency and how we can perform the federated training and how this will blend with self-supervised learning. And what's going to happen in this prediction is that there's going to be a number of unfair advantages for federated SSL that will mean that it starts to overwhelm the data center alternatives in a way that they can't keep up. And so one core aspect of this would be, of course, that data centers could also do SSL type learning, but the sheer avalanche of data that we'll be able to access and not have to move from the edge to the data center will start to become a huge drag on data center alternatives. Essentially, those data center alternatives will have to use less data than the FL ones, because the FL-based systems will have already access without any cost to this data. Not only that, data center alternatives either will be trained with less data or with static data sets, things like ImageNet++, but where the FL system is going to have a much smaller domain shift between its task and the source data. And then finally, the FL system will naturally be able to cope with changes in the system in the real world. So as, for example, a doorbell system recognizing people coming to the front door, in different countries, you might have the postman dressing differently, and the system will be automatically able to adapt to this. Or if from 1 month to the next, the color of a delivery uniform or how people dress or how people sort of behave may change from 1 month to the next, and the system will automatically be able to make this adaptation without having to sort of really be radically trained because of the way that it's operating. And so these are the reasons why I think that this style of technique and model will be the first place that we start to see data centers being overwhelmed. But this will be sort of a canary in a coal mine, because this will start to be the beginning of the end for data center dominance. And this will change a lot of things in how the machine learning ecosystem functions and operates. For example, it would start to diminish the importance of huge, ever-increasing data centers, at least for tasks of this kind. And so there's an interspeech paper from last year, if you want to see us doing some of this projective analysis, although this was on the domain of speech, but we're looking at this exact same sort of issue. But I won't go into it. Essentially, it looks at the different challenges that one would have to overcome to make this viable. As I mentioned, I think it's realistic we could get there in 3 years from now, but there are a few moving parts that need to be addressed within this space. So that's all I had time for today. I really want to provide time for us to have questions and discussion. Thank you for listening, and I also appreciate the invitation to speak today.
All right, thank you, Dr. Lang, for that. Okay, any questions?
Yeah, I have a question.
Yeah, go ahead.
So this flower framework, I'm curious how general it is. For instance, I'm interested, and I'll actually be giving a talk in later this week, specifically for decentralized federated learning. Is this general enough that it could be applied to such a scenario?
Yes and no. So so yes, in the sense that we have some we have some alternative ways of using Flower, some alternative APIs and so on that are not part of the main branch right now that would facilitate this, because we had a few requests of this kind. So feel free to ping me and I can sort of point these out to you and we can discuss this further. But in the current main branch, because we were emphasizing on simplicity and allowing people to get up to speed very quickly, the current design doesn't support decentralized, because initially it wasn't required, but we're increasingly seeing this need moving forward. But I really encourage you to get hold of me, because we're designing, we have a prototype design, but we're kind of also improving it based on feedback from people like yourself who are playing in the space. Could I actually ask, what's the use case for you?
So yeah, I guess I'm just more interested in the infrastructure as a whole. The place where I'm presenting is at this DWeb camp. And yeah, I guess I'm just an enthusiast, and I'd like to help build out this infrastructure for, I guess a lot of the reasons that you pointed out, just the privacy situation, people owning their own compute, that sort of thing.
Oh yes,
and
got you.
so I guess that's my main motivation. And yeah, I'd like to see people's data stay with them and people be able to share knowledge. And I think that a big part of that is doing away with centralized servers. So a decentralized method of doing this seems really important. And you know, if you have all the building blocks there, maybe it's just a pull request away.
Well, I think it's a bit more of a change than that, but we've been working on it. But I think it's always important to listen to how people are, what are the APIs that they need and how they're actually assembling these things. But I'm with you. I think the future of FL also is largely decentralized, at least for many use cases that are kind of motivated by those, the core foundations of why we're trying to do this.
Yeah, I think that you'll certainly have nodes. I imagine sort of like a heterogeneous network where some nodes are trainers and some just do inference. But yeah, I think it'd be useful.
Totally agree.
All right, yeah, I'll probably connect with you afterwards.
Fantastic, thank you.
Okay, great. Are there any questions online? Oh, okay. Yeah, sure.
Yep. Hi, thank you very much for the talk. I had another question about the Flower framework. Does it currently support, or are there plans to support doing simulations involving other privacy enhancing technologies like differential privacy or secure aggregation?
Yes. So we have at the Flower Summit about 2 weeks ago, we announced the third version of our SA support. And so I guess the short answer is yes. The approach is that we have this modular design where we're trying to enable people to build the type of SA that they need, that enables them to have the certain types of trade-offs that they really require for their application, but allowing them to reuse as much of other people's things as they can, because we had noticed that the existing kind of approaches were kind of a bit monolithic in the way that they made you sort of engineer things. And alongside that, we are offering a kind of like a reference implementation that seems to be, generically useful for most people's applications, because there's quite a few trade-offs in terms of the quality of the model, how fast it converges, the overhead that it in sort of enacts, particularly on the server, and so on. So we kind of have a reference implementation where we've actually used different pieces of the literature. So, we've actually sort of talked to a lot of different authors out there who've worked in the space to kind of build our first reference. So the SA is a lot further along. The other one, DP, is not really quite as mature. We do have a design of the APIs that, again, where the thrust is to make it more modular, to let people build the type of DP support that fits their application well, and enables them to play with the trade-offs. But we don't have a good but I guess that's still sort of more in flux. It's still in version 1, and then the reference sort of implementation part of it hasn't been tested under a lot of the different types of attacks out there. But that's where the state of those two things are. But we're super that we want to kind of move that forward as fast as we can. So if anyone wants to contribute, that'd be great. We're also looking for people to join the team to kind of also in a more stable manner to produce that too. But yeah, that's where we are.
Excellent, thank you.
Okay, I do have one question. So yeah, I think this flower is a very good framework for the FL community. So since we are, I think here the vision conference, a lot of people are interested in benchmark in terms of vision data sets. So for this flower framework, are there any already benchmarks has already been built so we can just quickly run it, or maybe directly take the result like ImageNet or some other CVPR 10, 100, some other data set, and with different FL approaches?
Yeah, I think there is. It's let's see. I've definitely seen examples probably in the repo that have ImageNet, CVPR 100, CVPR 10. They're all there. But I think in terms of richness of different FL approaches, it's a bit lacking. So I think there's probably 3 or 4 aggregation strategies available. But I mean, what I would say is that one of the thrusts of this reproducibility challenge, this so we're calling it Summer of Reproducibility, is to kind of build it up much more quickly. And so I think if anyone here is interested in contributing, they should in particular get hold of Javier. He's the guy in the middle here, or or myself. I can redirect you to him. We're happy to take comments and questions. We'll be producing in probably before July the 1st, a complete documentation of the competition so people can participate if they wanted to. And I think it'd be a great way to kind of share with the community solutions and maybe implementations that people already have, and just normalizing the access to these things. Because one thing we found was that although you might have like a lot of different open source implementations, because of the idiosyncrasies of each one, they kind of demanded a lot from the authors. And so one of the kind of like core foundational aspects of this would be the need to organize the code and the APIs in such a way that someone could just treat it like a black box. We think that's the key.
Yeah, I think it would be great. Like the neural architecture search community, they have a NAS benchmark, right? You see everything is there, all the benchmark, you just run it. So I think some of my students struggling is reproduce some of the results from the other authors' papers. So they took a lot of time to tune the hyperparameters, those things,
Oh yeah,
FL system. So that's one, big challenges for us. Yeah, but thank you. Thanks a lot for the presentation. Yeah, I think anyone interested in the flower framework will definitely reach out to you offline. Yeah, thanks again.
Great. Thank you for the invitation, and thank you also for the questions.
Okay, all right, thank you. All right. Okay, so I think we can take a 5 minutes break, then we'll be back for the third talk. Okay, all right, thank you. do you prefer your video on or do you prefer do you prefer the video on or off? You wanna,
The video,
yeah,
it doesn't matter.
doesn't matter, okay, okay, maybe we can turn it on.
But will that be taking the picture of the audience or?
No, just you. Do you want, or I can turn it on if you don't mind.
I
Okay,
think it's gonna be a big face.
okay, so we can, if you don't want, we can just turn it off. Okay. Okay, so we're gonna start our third speaker. Dr. Yang Liu is currently associate professor at Tsinghua University and also the Institute for AI of Industry Research. Before joining Tsinghua AIR, she was a principal researcher and a research lead in the AI department of WeBank, China. So without further ado, I'll ask Dr. Liu to give her talk. Thank you.
Thank you, Dr. Chen. Thank you very much for having me here. Good morning, everyone. So today I'm gonna talk about a new emerging FL paradigm, which I term it knowledge transfer federated learning. Wait, sorry. I need to click this.
Yeah, I think you can, right now you can do this.
Oh, okay, I see. So the outline of my talk includes the following. First, I'm going to explain what I mean by knowledge transfer federated learning. And then I'm going to talk about two popular knowledge transfer federated learning schemes, namely KD-based federated learning and vertical federated learning, and introduce some of the research highlights in addressing key challenges in these frameworks. So let me begin by revisiting the various methodologies that we characterize federated learning. For example, depending on the type of participant, federated learning can be characterized into cross-device and cross-silos federated learning. Well, the concept of federated learning is first proposed by Google to allow millions of devices to communicate model updates rather than raw data to train machine learning in a collaborative manner. It is later applied to a cross-silos problem to address the data utilization problem across enterprise and organizations. In the in-cross-silo setting, the number of clients are typically smaller, and the client reliability is assumed to be high due to stable connections. So the red figure is actually a figure borrowed from our book that I co-authored with Professor Qiang Yang called Federated Learning, which is published in 2019. Another way to characterize federated learning is by data partition across participants. Specifically, if we project the users and features in one figure, we can show that there are different types depending on their overlaps. If they have very large overlap in features and different in samples, we call it horizontal federated learning, just like the data partition in databases. On the other hand, if they have a lot of overlapping in the feature in the user domain, but they're different in features, we call it vertical federated learning. For example, a bank and a retailer company in the same city may have a large overlapping user base, and they can collaborate to build credit models for local customers. And we observe that such scenarios are very common in industry. Notice there's yet another scenario where neither sample IDs or features have significant overlap, and for which we leverage transfer learning to improve the performance among parties. And this scenario is termed federated transfer learning. So in this talk, I'm gonna discuss a third way to characterize federated learning, which is by the type of information communicated among participants. Traditionally, model parameters or gradients are communicated among the central server and participating clients. And we refer such scenario as model transfer federated learning. More recently, however, new federated learning paradigms have been proposed to transfer knowledge instead of model parameters in the training process of FL. And typical knowledge includes sample logics or representations as commonly adopted in the concept of knowledge distillation. So one typical example of knowledge transfer federated learning is knowledge distillation-based federated learning, which leverage knowledge distillation to transfer knowledge between clients and server. In addition, we think vertical federated learning can also be regarded as knowledge transfer federated learning. Since in vertical federated learning, both data and the local models are kept private, and only intermediate results are from these local models are communicated. And these intermediate outputs can either be logics or sample representations. And so is federated transfer learning. And regardless of the various federated learning schemes and the characterization, the core challenges of any federated learning system are still the privacy, accuracy, and efficiency, and to address the trilemma over various heterogeneous scenarios. And privacy-preserving technologies such as MPC and homomorphic encryption introduce efficiency bottlenecks, whereas differential privacy suffer from accuracy loss. In addition, compression and quantization are also actively investigated to improve communication efficiency without negatively or impacting on the training accuracy. So for knowledge transfer federated learning, new advances and challenges for addressing these pillar issues have also emerged. So in the following, I'm gonna discuss addressing these challenges for two federated learning schemes, the KD-based federated learning and vertical federated learning, and starting with KD-based federated learning. So the development of KD-based federated learning schemes stem from several open challenges that we encounter with model transferred federated learning. First, it is well known that the NID distribution issue can cause convergence problems and the generalization problems of a global model, which led researchers to explore the route of personalization, which is to provide a more customized model for client. And secondly, because FL places computation burden on client devices, its capability is largely limited by the client resources, on which training a large model is often impossible. So we asked the question if there's a way to break through such model capacity in a heterogeneous environment. And one feasible approach is to address these challenges is through knowledge distillation. In a typical knowledge distillation-based FL approach, so clients and the server transfer knowledge through output of a public data set rather than private models. So the private models actually kept local, and the output knowledge of client models are aggregated to on the server to train a server model, which then transfers knowledge back to client. But these scenarios still suffer from many issues. One of them is the improvement of knowledge distillation-based federated learning our model performance is quite limited. This is because the heterogeneous knowledge and the central server capacity of the central server model is limited. So to further improve the model performance of the KD-based FL, we first proposed to place a larger server model. So let's put a large server model on the original KD-based FL approach. And by doing so, we try to address the question if we can accumulate knowledge at the server by learning effectively from diffused client's knowledge. In other words, will a large server model be mutually beneficial to both the server and client? And we achieve this by adding selective knowledge module using label data. On the right-hand side, we showcase the performance of both the server and client models improves as the server model become larger and deeper. And this phenomenon verified that placing a larger, deeper server model helps boosting the performance of both server and clients. But this is based on using a large variety of labeled public data. So this scenario depends heavily on the availability of labeled public data set to enhance knowledge fusion. We then ask the question, if we can actually perform efficient knowledge transfer using unlabeled public data set, which is quite difficult since labeled ones are very hard to obtain in practice, but unlabeled public data set has its own challenges. For example, the unlabeled challenges with labeled public data set are pretty obvious because clients usually have diverse expertise on different tasks. The knowledge quality from clients are both limited and heterogeneous. And measuring these clients' knowledge quality without using the ground truth can be very difficult. But to address these challenges, so we propose a framework termed FedHKT. This is the hierarchical knowledge transfer framework. And this is a framework that combined KD and Fed model aggregation. So our main idea is that since we don't have labeled data, then we can make a cluster of clients collaboratively learn a model to provide higher quality knowledge. Here, with the help of an edge server, we cluster the clients with similar data distribution together. Therefore, we can enhance their knowledge by collaboratively learn an edge model, making the edge model specialized in a subset of tasks. Then each edge model transfer the output knowledge on the shared public data set to the cloud server with knowledge distillation, making the server model a global expert. So finally, and the output knowledge of the server model is transferred back to the edge models and client models to promote their task performance. And this is a hierarchical knowledge transfer with the bottom layer as the same as the model transfer federated learning, which uses Fed average as its basic algorithm. But on the top, we have KD-based federated learning. So the combination actually gave pretty good results. Here, we compare the performance of FedHKT with baselines in homogeneous and heterogeneous model settings. The results show that the FedHKT achieves significant performance gains for the server model, but also improves the personalization and the generalization performance of the client models. So for this, we test both the personalized data as well as the global data, so that we try to understand the client's personalized capability as well as its generalization of its own model. And we show that over the different tasks, the results demonstrate that FedHKT actually enables efficient knowledge transfer between server model and heterogeneous client models. Next, we further extend this knowledge transfer FL scheme to the multi-model FL domain. Multi-model FL domain is less studied compared to the unimodal FL. However, with the increasing amount of multimedia data on modern mobile systems and IoT infrastructure, harnessing this rich data without breaching data privacy becomes a critical issue. So directly applying the KD-based FL approach to multimodal data sounds like an attractive idea because it can address both models with a unified representation. However, this strategy still faces a few critical challenges because there are at least two unprecedented heterogeneous factors: the modality gap and the task gap. So if I'm a unimodal client, then my representations learned from my local models are going to be very different from the representations learned from another multi-model client. And these representation gaps is called a modality gap. So the previous largest transferred FL frameworks are also limited to classification tasks because in the previous frameworks, we typically transfer the largest, which is the layer before the prediction layer, to use that as knowledge. But here in multimodal domain, there are many different tasks, and these tasks require representations rather than largest to be communicated. So we need to redesign the KD-based framework to counterpart these issues. To overcome these challenges, so we propose a framework which is called CREAM-FL. CREAM-FL is it can enable training also larger server models from clients and with heterogeneous model architectures and data modalities. And this is done through a representation ensemble transfer on public data. And meanwhile, it can effectively address the model drift challenge using contrastive learning. So we overcome the model drift problem using different type of contrastive learning. Specifically, we perform both the intermodal contrastive and the intramodal contrast in client's local training. The intermodal contrast is to complement information from the absent modality, where the positive pairs are local representations and their paired global representations from another modality. And the negative pairs are local representations and unpaired global representations. So the intramodality contrast can enforce the unimodal image clients to head towards the shared multimodal representation space to learn better cross-modality interaction. In addition to that, we also design a global representation aggregation. This is to use the global local cross-model contrastive score for weighting purpose. So we assign a higher weight to the local representation that actually better matches its counterparts global representation and the less proximate other unpaired global representation. We find the reweighting using such strategy is very helpful to bridge the training gaps between different clients. So we perform evaluations of our framework on image text retrieval and VQA tasks and compared with the existing method, including both the model transfer FL frameworks, such as Federated, Fed-Average, and Fed-IoT. Fed-IoT is another multimodal federated learning approach where they use Fed-Average to aggregate model parameters by a modality, then they assign a different weight to multimodal clients. And we also compare the other knowledge transfer federated learning frameworks, including FedMD, FedGEMS, and showcase that the CREAM-FL achieves noticeably performance improvement overall baseline in all settings. So here we show that we perform this the ablation studies on the 3 different contrastive modules of our approach. And we show that the performance continuously improve as we include each of the modules. Here, the RAMFL is actually the CREAMFL without C, meaning that we do not use any contrastive learning in this representation learnings. So the federated learning scheme is actually just a vanilla representation ensemble using KD-based FL. And on the right-hand side, we compare the communication cost of our approach as opposed to model transfer federated learning approach. So since our framework communicates sample level representations, we can observe that the communication cost grows as the number of public data or the dimension of representation. Each data point is the final model performance under the specific setting. And generally, we see that Fed average and Fed IoT exhibit inferior performance to CREAMFL with higher communication cost at the same level of performance. So this is the visualization representation of randomly chosen images from COCO and generated by one multimodal client and 2 different image clients. The left figure is a benchmark case without contrastive learning, where the aggregation is simple average. We observe that the model drift exists between the 2 image clients, and the model drift between the unimodal clients is much smaller compared to the gap between the multimodal and the unimodal client. Red figure shows the CREAMFL actually can pull the representations generated by different clients closer and effectively mitigate such drift. Okay, so before concluding this, the KD-based federated learning section, I would also like to discuss a little bit on the privacy issue of KD-FL frameworks. So we know that model transfer federated learning are vulnerable to some extent to deep leakage attacks. And I think the audience of this group may be very familiar with that already. So there have been previous studies that explore the connections between model parameters, gradients, and the raw data, especially for computer vision tests, where the pixels of image are correlated and can be reconstructed from the gradient values. So one advantages of a KD-based federated learning paradigm is that it does not transfer any model parameter, so it can eliminate the deep leakage attacks. But over the years, we have seen that such deep leakage attacks proposed are getting stronger and stronger. So we asked the question then, will there be a deep leakage from the logics in the FedMD-like schemes? It's going to be very challenging, but we identified a certain route that can achieve this. So we identified at least the 2 necessary principles to attack such FedMD scenario. In order for such attacks to be successful, first, it needs to be gradient-free, meaning that the attacker cannot use any of the gradient-related information because the models are kept private. On the other hand, the attacker also needs to be a knowledge decoupling. By knowledge decoupling, what we mean is that since the KD-based FL transmit the output or logics from the public data set, if we apply a direct inversion to that, it will mostly give us the public data set rather than the private data set. So we need to design an attack that only takes in the public data set logics, but return to us the private data. This is very challenging. And these principles make the attack very hard, but none of the existing method actually can achieve both principles. So we take on this challenge. And we try to propose a new attack framework with multiple steps. So first, we train an inversion neural network model on public data and their logics, just like the regular inversion model, except that the input to the model is not only the predict logics from the client-side model, but also the output logics from the server-side model. Remember, we have a server-side model also in place in the KD-based federated learning paradigm. And I will explain why we try to use both logics. And then next, we try to estimate the output logics of server-side and client-side models on targeted private data. So if we can estimate the output logics of the server-side and client-side models, then we can feed this estimate logics to the inversion neural network model to generate original private data. And finally, to refine the estimation, we can also use prior estimated from the public data set for regularization of our optimization. This is try to improve the final image reconstruction quality. And we term our method paired logic inversion attack, since it exploits the confidence gap between the logics of a server model and client model for the same input. So the inversion model we train has two terms. The first term is the normal inversion loss to recover the raw data. And the second one is the regularization, which forces the reconstruction to be close to an estimated prior of the private image, which are estimated separately from the public data. And the inversion model takes in two inputs, the logics of the public data and the logics from the server model and the client model. So once the inversion model is trained, we then estimate the output logics of private data using the confidence gap optimization. This is the crucial part of our method, because to accomplish this, we first formulate the evaluation criteria for the quality of recovered image as Q. This formulation is based on the intuition that both server model and client model should have high logics for the recovered image. However, since only the local model is trained on the private side, not the server model, then we will anticipate that the server model will return a logics with high entropy, higher entropy than the private client model. So we use the above criteria, which adds up these logics as well as the entropy from the server side. And we try to optimize, maximize this Q. And based on this formulation, we can actually derive the analytical solution for the optimal logics that can maximize Q. So as for the prior estimation, since the server can also access the public data, it is able to obtain prior data by transforming these public data. There are at least two ways for estimating these priors. First, for unlabeled public data, we can estimate the prior using the average of public data. If auxiliary insensitive data of the same label as the public data set are available, the server can also use scan to convert the insensitive data to obtain prior data for each target label. And finally, we use this framework and we test it on different data sets. Here, we showcase 3 different data sets where the private data are private faces, and the public data the younger, for example, the first one is the younger version of a female, and the second line is a master version of a person, which actually considered as a public domain in our framework. And the third case is a blurred public data, which is less sensitive than the original facial face images. So our strategy tried to use only the logics from the client and the logics from the server model to reconstruct private images. And as you can see that T represent the number of communications in federated learning in our approach. And our approach termed PLI, paired logistic inversion, can recover the private data as more communications grows. However, the counterpart, which is a baseline attack called TBI. TBI is the framework which is a direct logistic inversion model. It invert logic back to its original data using an inversion model. And we can see that TBI can reconstruct mostly public data. So this is a showcase that the performance of our PLI attack. And this work actually highlights the needs for the design and the development of more secure knowledge transfer federated learning algorithm. Of course, and our work has many limitations. And one of the limitations is that currently it only applies to facial recognition tasks. And we also have a poster at this conference Wednesday. So please check out our poster if you find our work interesting. Okay. So finally, I'm gonna spend the rest of my talk to discuss a little bit about vertical federated learning, which also transfers knowledge rather than model parameters in their schemes. The vertical federated learning problem is to find optimal model parameters that minimize the collaborative loss under the following assumptions and constraints. First, features of the same sample are distributed across multiple parties. And the samples are assumed to be aligned or aligned by encrypted entity alignment techniques. Thirdly, and each party owns a part of a complete model. Only one party has the label, which we term it active party. And those parties who do not have labels are termed passive parties. This is in line with many industrial applications, since the labels are very precious and it only be contained in one of the parties in participating the VFL. So during training and inference, model parameters and data both stay local, and what is communicated are just the model outputs. And this is the typical protocol to train a VFL. It contains two steps. The first is the entity alignment process, and the second is the privacy preserving training process. So the entity alignment process typically use PSI, private intersection, to find the common sample IDs without reviewing any unaligned data set. But after finding the common samples, then each party can start training the VFL model using the aligned samples. Specifically, each party computed its local model output on the minted batch of samples and sent the outputs to active party, which then aggregates and computes the training loss. Then the active party computes the gradients and transmits them back. Finally, each party will compute the gradients of its local model and updates their local model accordingly. So in VFL, we can decompose the model into a local model termed G here, and also a global module termed F here, which is only accessible by the active party. And the global module can be either trainable or non-trainable. If a trainable global module is in place, this VFL scenario is coincident with the vertical split NN. If many audience may be familiar with split NN, where the whole model is split into different parties. Thus, we term it a split VFL. If the global module is non-trainable, it serves as an aggregation function that aggregates parties' intermediate results, similar as Fed averaging. Then we term this scenario aggregate VFL. Another variant of VFL is that when the active party has no features and thus it provides no local model. In this variant, the active party plays the role of a central server. So in VFL, the naive framework requires communication between clients at each iteration, as I just described. With encryption, this becomes a bottleneck for efficiency. And here we borrow the idea from Fed averaging, where multiple local updates can be performed before each communication. We then asked if such multiple updates can also be performed in VFL. We leverage block coordinate gradient descent to achieve this goal. So for each local iteration, each party locally computes gradient based on its own data and steal the intermediate components from other parties in the most recent synchronization. And for each communication, instead of performing one round of local updates, we perform Q round of local updates to save communication rounds. And we term this approach Fed BCD. So we theoretically provide convergence guarantees for this algorithm, and experimentally show that the compare with vanilla Fed SGD, Fed BCD can save communication rounds by up to 70%. Other than that, we discuss also the data protection protocols of VFL. So the VFL actually needs to deal with both transmitted intermediate results and internal intermediate results. Transmitted intermediate results is the those information that actually communicated among parties. Internal intermediate results refer to information such as the internal local gradients. These may be the direct information from transforming these transmitted intermediate results. So based on what is protected and exposed during VFL training and inferences, VFL protocols can be summarized into different levels. Here we characterize each levels with a different protocol and a security. So the basic protocol is to keep the private data and model local, but transmit plain text intermediate results. But this can result in leakage, as I just showed before. The larger is the output, if transmitted plain text can be used to exploit other data, private data. So then we can further protect the intermediate results to use a standard protocol, which further protects the transmitted intermediate results. And the enhanced protocol protects the entire training protocol, including both the internal intermediate results. So even the internal results such as local gradients are protected. This is usually not protected in horizontal federated learning. And the strict protocol protects not only the training protocol, but also the local models from being exposed to its own party. So even after we train the local models, we still don't get access to that model because that model is a property that actually obtained from training collaboratively with other parties. So that model potentially can contain information from other data, and a strict protocol actually protects this information as well. But actually, in literature, we observe that there are many assumptions that actually relax these protocols, resulting in a relaxed protocol, which assume that either label or models are non-private. So various kinds of attack have been proposed under these above protocols, such as data reconstruction attacks, which include both label inference attacks and feature reconstruction attacks, as well as backdoor attacks, which includes both the non-targeted backdoor attacks and the targeted backdoor attacks. So similar to the backdoor attacks to general horizontal federated learning, the non-targeted backdoor attacks using missing features or noise to generate backdoor samples, and the targeted backdoor attacks using targeted basically they use designed triggers to form a targeted attack. And in these slides, we summarize the existing attacks to VFL by their attack type, VFL setting, model structure. I am not going to be going deeply through these attacks, but one take-home message is that these are attacks that attempt to target a lower security level, and those who target a higher security level needs require substantial auxiliary labeled information. So these attacks are still very challenging, especially for the feature reconstruction attacks. And this is a summary of the defense work that is currently being developed by different groups over the world. And we can see that cryptographic defense strategies are still the mainstream for provide secure computations. But there are still also emerging defenses. These emerging defenses explore different strategies such as mutual information regularization and adding specific noise so that they can target at a specific attack categories to maintain a good utility. And the need for VFL has grown strongly in the industry in recent years. And we show that, there are many companies and institutions owning small and fragmented data, constantly looking for compensating data partners to collaborate with AI technology for maximizing their data utilization. So we showcase there is a list of open source projects such as VBank's Fate, PyVertical, FedLearner, FedTree. These are all targeted at VFL scenarios. And the majority of applications are still concentrated in advertising and finance. But there are still major challenges in the advancement of VFL research, and we listed at least two here. So first, there is a substantial gap between the defense goal of VFL research and practice. So we showcase that there are many VFL defense work, outstanding works in the literature, but these objectives of research works mostly focus on achieving a state-of-the-art performance on a targeted attack type, resulting in fragmented evaluations on separated tasks. But in reality, the practical development of VFL systems calls for universally effective yet simple defense solutions to throughout all the possible attacks. So there is notably absent of comprehensive and fair evaluations that can encompass multiple attack and defense methods under a wide variety of VFL settings. And secondly, there is a lack of lightweighted unified VFL framework designed for rapid testing new attack and defense algorithms. So to this end, we want to propose our code base of VFlare which is currently still under development, but it includes a general pipeline to mimic the standardized VFL training and inference flow, including data model partition, communication strategies, as well as extensive attack and defense modules, which support newly published attacks and defense method. So currently it supports 8 existing defense strategies, 11 attacks, 9 models, 2 partition settings, and 2 communication protocols, and 10 data set. It is still under development. An unique feature of VFLARE is its effort to bridge the gap between the defense goal of VFL research and practice. Specifically, we benchmark existing defense strategies on their performance, depth, and breadth, where depth refers to their individual defense capability on each targeted task, and breadth refers to their comprehensive defense capability for all types of attacks. And to benchmark this defense, we take both the model utility of the main task and the attack performance into our evaluation to develop a defense capability score, which depends on the weighted Euclidean distance to an ideal defense performance. And for the breadth of defense, we aggregate the scores by type and further aggregate type level scores to obtain overall comprehensive defense capability scores. And we will showcase evaluation results soon in our GitHub. And if you are interested, please also check out the GitHub repository for more details for now. This is the work done in our group by some of my graduate students and intern students. So that's all I want to share with you today. And thank you very much for your attention.
Yeah, so I wanted to ask about the last slide that you had with this score. So it's dependent on a specific attack. So I'm a big fan of trying to have, let's say, privacy by design or provable privacy by design rather than measure empirical privacy for a given form of attack, which may not be the most powerful one that's possible.
Right.
So, I mean, how do you plan on do you plan on having a specific family of attacks and you just kind of take the worst one, or how is this score like well-defined, or will it be evolving over time?
Yes. And that's an excellent question. So currently we are in an effort to develop the scores, which comprehensively include all the heuristic, in practice, the most worst attacks. For example, for label inference attacks, this includes, many of the list above, and these are currently mostly designed to do experimental evaluations. And so for some of them, I think it is very challenging to actually achieve, theoretical proof for many of the attacks due to its experimental nature. And but I think this provides at least to the practical deployment, the practitioners of VFL, what is the most effective in practice, and that's the goal of this part of work. Okay.
Thank you for your presentation. It's really good. So my question is, you mentioned the communication cost in one of the figure. So it's a little bit vague. In what perspective did you mean communication cost?
Which part?
There's a figure if you go up. Yeah, go up. Yeah, up.
So
yeah,
before?
one more. Yeah, go up. Yeah, this one. Yeah.
Oh, okay.
So
I see.
Yeah, well, I just don't understand what's that. And by the way, because you consider communication here, there's another aspect is computation. So computation, communication, this could be the bottlenecks for the federated learning training.
Right.
So I want to know the motivation. So you pick a communication course here. Does that mean like you really consider communication now is the bottleneck rather than the computation?
Yeah.
Yeah, there's two questions.
Right. Thank you. So for the communication question, this is to showcase, the figure here is to showcase that the KD-based federated learning schemes, how the communication actually is compared with the model transfer federated learning. So to transfer models, it will also add a bunch of communication overhead, and the unit here is actually the base. So basically how much information we communicate to the server. And this is
What's the unit for the communication cost?
the communication cost. I think it should be the total number of information transferred in bits, but I need to check with the, like, you can check the paper. Actually, it should be the total number of communication. So the information.
Yeah,
Check.
I mean, at least it needs to have a unit, so it's a bytes or megabytes or something.
Right, it should be, that's what I said, that should be bits, but I think there should be bits, yeah. So in the it should be in the paper as well, so we will actually double check it and get back to you. Okay. It should be bad. This is just a showcase the how much information is communicated, because, for example, the model, the larger the model gets, the communication also gets higher. And this point is just to showcase to achieve the same amount of model performance, how much is communicated as compared to the Fed average, Fed LT, and the CREAM-FL. Yeah. Sorry, your other question is about the computation.
Yeah, which one is bottleneck?
This work mainly address the communication problem here, and for computation, I think because here we are comparing, multimodal federated learning on different scales. The multimodal computation, I think there should be right. So I sorry. So for this part, for this work, we didn't actually address the communication problem, and I cannot actually give you a conclusion on that. Yeah.
Okay, all right, thank you, Dr. for the presentation. Yeah, I have your slides here. Yeah. Okay, so okay, I didn't share the screen. Okay, so our next speaker is Dr. Michael Ravek. He is the founding member of the Facebook AI Research. And before joining Facebook, he was a professor at McGill University. So without further ado, let's welcome Dr. Ravek. Thank you.
Yeah, thank you very much. Thanks everybody for being here, and thanks also for the invitation to present today. So I'm going to take a slightly different approach today, and rather than giving an overview of lots of different material, I'm probably going to focus for most of the talk on one specific paper called Where to Begin, which talks about the importance of how we initialize when we're doing federated training, and thinking about how we can leverage pre-trained models rather than random initializations, and what are some of the consequences of doing this. And towards the end of the talk, if there's time, I will also talk a bit about self-supervised pre-training, not directly tied to federated learning, but why I think it's important and maybe a useful alternative to other types of pre-training. So this is joint work for most of what I'll be speaking about today, joint work with my colleagues John Nguyen, Johnny Wong, Kshitiz Malik, and Maziar Sanjabi, all of whom were also at Meta at the time when this work was done. So let's see. There we go. It's good. Okay, thank you. So to get us started and just to situate the discussion for the presentation today, let's just recall the Federated Opt or FedOpt Federated Optimization Framework of Reddy et al. From a couple of years ago. The focus of my talk today is going to be really on cross-device federated learning. And so in that setting, we have some clients, which are shown on the left, devices, in this case, maybe mobile phones. And there's the server in the cloud, conceptually one server, but often, this would be much more involved, but that's going to be coordinating the training. And to start things out, the server has some initial global model that's going to be used to begin the training. The typical steps in this framework go roughly as follows, right? So the clients are going to indicate when they are ready to train, when they're ready to participate. The server is going to perhaps use some client selection protocol to select a subset of the clients who will participate in the current round. It's going to send them the latest model, maybe also some additional meta information that could be useful for training. Then the clients are going to perform some local updates. Those could be a fixed number of local steps, or more commonly in practice, we might tell each client to perform a local number of epochs over the data that they have available. And they're going to do that using some optimization routine, which generically would be called client opt. There could be many choices for how that might work. As depicted in the bottom left here, you can see we have some initial model that we received from the server. We take a bunch of local steps. We look at the difference between where we ended up and where we began in that round, and that forms our model update. Once we're done training and once all of the clients are done training, and typically in order to preserve privacy, those will be aggregated using some secure aggregation protocol, so that what the server receives at the end is a weighted sum of these model differences from each client. Perhaps weighted could be different model aggregation schemes that one might use, but for example, it could be based on the amount of data that the client has or the number of local steps that it took. Then the server is going to finally perform some update to the global model that it's maintaining using another method that's called server opt that gives us the new global model at the server, and we begin the next round. Okay, so hopefully this is familiar to everybody, but this was just to get us all on the same page. Now, over the past couple of years since this concept of federated learning was coined, I guess back in 2016 or 2017, there's been plenty of research on lots of aspects in this figure. And in particular, basically steps 1 through 5 have been studied very carefully from various different client selection schemes, various ways of performing local updates on devices, perhaps incorporating additional information from the server in order to reduce client drift, different ways of aggregating, different ways of performing updates at the server as well. Incorporating things like quantization or other forms of compression to reduce the communication overhead between the server and the client, and so on and so forth. And in this work, we actually kind of wanted to look at a different part, which we felt hadn't received as much attention, which was this initial step 0. How do we initialize the beginning of training? We know in general in optimization, how you initialize can make a big difference. And so we wanted to see what were some of the consequences of how we initialize in the context of federated learning. Now, there's also several challenges that come up in federated learning. We've already heard from several of the other speakers this morning, and I guess for this crowd, it might be also very familiar. One of the main challenges comes about due to various forms of heterogeneity. So there's data heterogeneity where the distribution of data at different clients might not be the same. When this is the case, when clients are taking local updates, this can be a source of drift. The models at different clients drift apart, and this essentially slows down our training. This is a well-known phenomenon. Of course, if we were doing this training in a centralized manner in a data center, all the data would be in one place. We could shuffle or permute the data, and that essentially renders this heterogeneity problem, no longer a problem. But in the context of federated learning, due to privacy reasons, we cannot do that permutation or shuffling, and so we have to deal with this. The other form of heterogeneity comes about due to system heterogeneity. Different clients are different physical devices with different capabilities, maybe different amounts of memory, different compute. And of course, tied into this also is this idea of data imbalance. Different clients hold different amounts of data, right? Typically, if we're thinking about this data being generated in the context of some feature or an application on device, some users might use it much more than others, and so they're going to have more data. And so because they have these different capabilities or different amounts of data, if we're performing local updates based on, or local epochs based on the amount of data that we have, this can lead to what was called the objective inconsistency problem in a paper of Wang et al. In 2020, which then motivated them to introduce a method called FedNova, which we won't go into the details of, but I think is very interesting and a very important direction to consider. So we'll come back to that in a moment. Well, I guess on this slide, because there's been plenty of work trying to address various of these heterogeneity issues over the past several years. And again, these correspond to different ways to change steps 1 through 5 in the slide I had a couple of slides ago, whether it's changing the way that clients do their local updates, the way that the server does its local update by, for example, incorporating momentum, maybe incorporating some control variates, which involves transmitting additional information from the server to the clients or vice versa in order to reduce drift, changing the way that we aggregate to address the system's heterogeneity issue, and so on and so forth. And so all of these contributions modify aspects of the training algorithm or the dynamics. So as I mentioned at the outset, the question that we wanted to consider for the study I'm talking about today is, how does the initialization impact federated training? And the main motivation actually was the observation that, in many practical applications of federated learning, at least in the cross-device setting, there might be some sort of proxy data that's available. So it might not be the data that we're actually going to do the federated training on, because that's private and it's on users' devices, but maybe there's some other data that's somehow similar or related that we might hope to learn some useful initialization from. And so rather than initializing from random, which is often what we do or what we see in papers introducing new methods in the academic community, in the scholarly community around federated learning, it might be possible for us to start from a different initialization. And of course, there's certain things that we might expect to happen as a consequence of this, right? So we know in general in optimization, if you start maybe closer to the solution, you're going to converge faster, not too surprising. So maybe we'll hope to see that too in the federated setting. We know that for the most part, training deep neural networks is a non-convex optimization problem. One might hope that maybe starting from a pre-trained initialization also starts us maybe in a better basin or closer to a better basin of attraction, so that the local minimizer that we converge to is of a better quality. And one thing that we might not have expected, at least we didn't expect, but that is something that we're going to observe, so this is kind of a spoiler, is that it might actually turn out that by initializing not in a random way, but from some sort of a pre-trained solution, we also no longer have to deal with the same kinds of issues related to heterogeneity, or at least it's not as pronounced of an issue. And so we're going to see that this comes up in the study today. Now, I should say that there is some previous work that has looked into various aspects related to this. So on one hand, we know outside of the federated learning world, transfer learning is widely used. People, especially when they want to address tasks for which there's a small amount of labeled data, common practice for several years now has been to pre-train on some large, possibly related data set, and then transfer your model, maybe reinitialize your classification head if it's for a classification task, for example, and go from there. Same thing in natural language processing. We know that we do a lot of pre-training just for, say, a next word prediction task, and then we will fine-tune some additional classifier head or some other sort of head on top of the model to address some other downstream tasks. And there's evidence in the literature that these fine-tuning problems might be better behaved or better conditioned than when we start from a random initialization. So I shouldn't say than pre-training. It should be better behaved when we start from a pre-trained initialization. And the figure on the right is just one example. We have to kind of be a little careful how much of a conclusion we draw from this, but this is looking at fine-tuning in the context of vision classification models. And the observation here was that if you project down to 2 random dimensions, the contours around the area that you are fine-tuning look pretty well behaved, fairly convex. And this might be different than if you were to look at the overall problem that you're solving when you start from a random initialization. So this is outside of the world of federated learning, but maybe still gives us some inspiration or some hope. And in the context of federated training, there has also been some work that looked at starting from pre-trained initializations. There, the main motivation cited in these works and the main focus of those works was to understand, can we bridge this gap between a centralized accuracy and the federated accuracy that we get? So it's well known that when we do federated training, by doing this on device with local updates, often the quality of the model, the resulting model that we train, is not quite the same as if we had all the data available centrally and could train in the data center. And often that's pegged due to heterogeneity. And these works did show indeed that if you start from a pre-trained solution, that helps to bridge some of this gap. All right, so what are we going to look at in the study that I'm talking about today, or what did we look at? So we looked at experiments across a couple of different tasks, 2 involving image classification, others involving next word prediction for language modeling. We looked at a couple of different models, and we're going to look at contrasting and comparing what happens when you start with a pre-trained initialization versus when you start from the typical random initialization that one would use for training these models. And in order to keep the setup simple and for it to hopefully be reproducible by others in the community, for our pre-trained initializations, we tried to use model checkpoints that were already out there in the public. And so for the image models, we're using SqueezeNet and ResNet 18, so relatively small models, which might be appropriate for federated training on device. The pre-trained initializations that we're going to use for those are for models that were pre-trained on ImageNet, and those are directly available in the Torch Vision library. And in the natural language case, we're using also smallish language models, DistilGPT-2 and a character-based language model, which I think is primarily LSTMs. And you can see those are pre-trained either on Open Web Text or on Wikitext 103. Okay. Now, the approach that we're going to focus on in this paper is to start either use random initializations, as I mentioned, or to start with these models that have been pre-trained in the sort of standard supervised way. That's only one approach. There's definitely others that we could take, but for this initial study, we just wanted to start with something that seemed simple and ready to go. And when we transfer it to the federated learning task, we're going to keep all of the pre-trained features, everything except for the penultimate layer, to the values that they're at after this pre-training, and we'll randomly initialize the classification head. We'll do this because often, for the most part, the tasks that we're looking at in the federated setting don't have the same number of classes or the same size vocabulary as they did in the pre-training task. Okay. We're also going to consider a variety of different federated optimization strategies that fit into that FedOpt framework. So we have 5 different options for the client optimizer: standard stochastic gradient descent updates, which would be like local SGD or Fed average; proximal updates, like FedProx, where the idea is to not drift too far away from the model that the server sent; normalized averaging, which is going to weight based on the number of updates being taken locally on that device; MIME light, which is introducing control variates in order also to try to reduce drift; and as a 5th, for some of the experiments, we'll look at what happens if you just use full batch gradient descent. We did this in the paper. I'm not sure if I'm going to, maybe I'll mention it briefly in the talk today. And on the server, we're also going to consider 3 different options. So one is the server also just does stochastic gradient descent updates, treating the aggregated model updates as a gradient. In all these cases, that's what's happening. And the second option would be like for Fed average M, where we incorporate momentum at the server. And the third would be where we use Atom at the server, which would be akin to Fed Atom. Okay, so apart from changing these different local update methods and the server update method, here's how we're going to try to set otherwise the controls for these experiments. So we're going to have all methods run for the same number of rounds, using the same local batch size on devices and using the same cohort size. So that part is kind of the same across all methods. Now, clearly, these methods have some different hyperparameters, and we're going to tune those. And in particular, we're going to tune the learning rate for each method, as well as some of the method-specific hyperparameters. So, for example, in FedProx, there's this proximal penalty parameter. We'll also tune that for each workload and for each combination that we consider. So this is trying to give each method its best shot. And we're going to tune these separately for the random initialization and for the pre-trained initialization. Okay. So the main question that we wanted to get at then was, how does this initialization, well, you could ask, does the initialization impact all federated learning algorithms equally, or put differently, how does the initialization that we use impact sort of our interpretation or the behavior of these different federated learning methods? And so here's the kind of result that we see. It looks like a mess. So let me parse through it and try to interpret what is up here. Because when you're comparing lots of different methods with lots of different things changing, so here's what we have here. So for this particular figure, you can see that we have 9 different specific algorithm instances that are being compared. 3 different versions of what's happening at the server: fedaverage, fedatom, fedaveragem, and then 3 different versions of what's happening locally on device: proximal updates, standard SGED updates, or MIME-lite updates. We consider 2 different initializations, pre-trained or random. And so for 9 algorithms, 2 different initializations, we get 18 final accuracies. And so these are the 18 values that intersect all the way on the left and all the way on the right. On the left, it's for the pre-trained, where we start from a pre-trained initialization. On the right, it's when we start from a random initialization. Again, this is after the same number of rounds. What about all the stuff in the middle? The stuff in the middle is just interpolating between these 2 points. I don't want you to read into it basically at all, other than to observe that these lines cross a lot. They're spaghetti, right? And what does that tell us? That tells us that depending on which initialization we use, this changes the rank order of these algorithms and their performance, and basically which one we might prefer. Okay, and I'm showing this to you for one of these tasks, but we see similar figures across all of the tasks. And actually, there's one important point that I forgot to mention. So let me back up here. When I was looking here, one of the things I should have mentioned is, so on the left, we have the final accuracies for the pre-trained. On the right, we have for random. And you can see that the range is different also for these 2 different sides. In particular, when you start from a random initialization, the range of final accuracies that you reach after this number of rounds that we ran the experiments for is quite large relative to the size of the range that you have when you start from a pre-trained initialization. So already this tells you something which might not be too surprising, which is that if you start from a pre-trained initialization and you tune hyperparameters for each method, then the difference in performance amongst these different methods is not going to be as great than if you start from a random initialization. All right, so I was pointing out that we see these same conclusions across multiple different workloads, so different models and different data sets. And so one of the things also which might be expected is that there's no single method that wins out in all cases. This is often the case, but we did get the sense that for the most part, if you're going to start from a pre-trained initialization, then using fedatom is reasonably competitive across these different workloads and is a simple setup. So relatively few hyperparameters that need to be tuned. Okay. So what else do we observe? So another question we can ask in this context is, what if there wasn't data heterogeneity? So in this case, that basically means, what if we could shuffle the data across users, partition it across clients in that way? So we're still going to use local update methods. And I guess this is what we observe now is, so we're looking at 2 different initializations, pre-trained or random. Red corresponds to this ideal IID setting, right? We can't do this because of privacy, but we can ask the question, what would happen if we could? And what we see is, so it's been known in the randomized initialization setting for a while that there was quite a large gap between the performance, and this is consistent across several tasks, between if you had non-IID data or data heterogeneity versus if you had IID data at the clients. And so we see that when we start from a pre-trained initialization, not only does the performance consistently go up, as you might expect, but also this gap between the non-IID and the IID setting diminishes consistently as well. So, and this is specifically for Federated that we ran these experiments. So this suggests that when we're starting from pre-trained weights, then at least Federated might be less sensitive to data heterogeneity than if we were to start from a random initialization. Another thing we looked at is the effect of the number of local epochs, and found also this kind of surprising. Normally what we observe, again, this is for Federated, normally what we observe is if we started from a random initialization, right, as you increase the number of local epochs being run on each client, you expect there to be more and more drift, and so performance degrades. And you see that roughly here, and for some reason, when you go to 8 epochs, it jumps back up, but in general, it's decreasing. And it turns out when you start from a pre-trained initialization, you don't see this effect at all. And it's fairly consistent across. And so it's somehow it tells us that we're much less sensitive to how we tune that number of local steps or number of local updates, number of local epochs hyperparameter, which is also maybe interesting and useful to know for practitioners. Okay, so we have many additional results in the paper, and we have some various hypotheses for what might be happening. But I think the one hypothesis that's worth really mentioning in the talk today, if we wanted to try to understand why does pre-training help federated optimization, the one that seems to be suggestive of the answer is that when you start from a pre-trained initialization, you start from a better conditioned loss landscape. So what we do here is we take the initialization and we look at the largest eigenvalue, largest Hessian eigenvalue, and we compare that when you start from pre-trained versus random initialization, and you can see that it's consistently lower for the pre-trained initialization. So this tells us that in the direction of largest curvature, that curvature is quite a bit smaller. This suggests, that things are more well behaved. I think there's still much additional work that needs to be done to understand this further. But this was the most conclusive of the various hypotheses that we explored for why might pre-training help in federated optimization. Without going into all of the details, let me just kind of quickly rattle off a few of the additional observations that we made in the paper, and I'll refer you to the paper if you want to see more, or we can talk about this afterwards. So one not surprising thing is that the pre-trained initialization consistently achieves a better final accuracy. So at the end of training, it's consistently better, but perhaps surprisingly, at initialization, it is not always starting with a lower training loss. So there are multiple examples where when you start from a pre-trained initialization, the initial loss is actually higher. And recall, it seems maybe surprising at first, but recall that when we do this transfer, we still have to randomly initialize that final classification head on the model. So it's not like the whole model has been pre-trained. And so that kind of helps us explain why we might observe higher loss in some cases for that pre-trained setting. One of the other things we observed is that local updates are not always necessary when you start from a pre-trained initialization. So if you were, instead of doing multiple local updates on each device, so that would be like Federated with local SGD updates. If you were just to have each device compute a gradient, just a full batch gradient without changing the model locally over its entire training data set and send that back to the server. So this is what we would call in the paper Federated GD. So Federated because the server is using Atom, GD because the client is just computing a gradient. That was often competitive or essentially the same in performance when you start from a pre-trained initialization, as if you were to do local updates as well. So this is also kind of interesting. It's maybe surprising. I didn't mention it on the slide, but related to this is that, similar to the way that data heterogeneity was not as pronounced when you start from a pre-trained initialization, it's also the case that systems heterogeneity does not have as bad of an effect when you start from a pre-trained initialization. So you can have clients running different numbers of local updates, and you don't see the same kinds of objective inconsistency. Maybe the last point that I'll mention, but without going into detail, keeping in mind that I'm standing between you and lunch, is that not all of our observations are readily explained by existing theory. So often the convergence theories that we have for local update methods do depend on the quality of the initialization through the local loss, through the initial loss, sorry, the loss at initialization. Sometimes we observe that it's lower when you start from a pre-trained initialization, but like I mentioned, sometimes it's not. So this doesn't completely help us explain what's going on here. And so I think there's maybe other interesting questions. I think it's probably difficult because this requires us really to understand better the loss landscape of training deep networks in general, which is not something that I think we have a great grasp on right now. But I think there's interesting work to be done there. Okay, and so for my remaining time, let me kind of switch gears and let me say the following. So this is kind of more of ongoing and future work. So all of the experiments that I told you about so far, we're starting from a supervised pre-trained setup. Looking forward, I think self-supervision is going beyond supervised pre-training. I think is something that we need to do. And in particular, I think self-supervision is extremely important. And some of the previous speakers today have already mentioned this idea of self-supervision, but let me give my own kind of perspective and maybe try to also point you to some additional work to go check out later this week. So why do I think self-supervision is kind of an interesting way to go? Well, we know young humans learn quite a bit about the world just from passive observation, okay, not necessarily from receiving any sort of supervision. And so these are some experiments that are shown on this slide from more of the cognitive science and psychology literature, where there would be kind of a, so the setting goes as follows. So there's some new objects that probably nobody has seen before that are given names that are not very common, right? And in this experiment or a series of experiments, the first thing that would happen would be that a toddler and their parent would go into a room and start playing with some of these objects. And the parent was instructed to name the object with its creative name only one time during that episode when they're playing. Then the parent would leave the room and one of the administrators of this study would go in and they would talk to the toddler, ask them if they had fun, and they would ask them, oh, by the way, sorry, I can't remember. Could you tell me which one of these is the tema or which one of these is the dodi? And with very high probability, the toddler was able to point to the correct example. And so this tells us that, there's certain characteristics that we learn without needing a lot of labeled data, but we just learn by passive observation related to things like shape, color, and so on in the visual setting. But we believe this is a much more general principle. And so there's been a lot of excitement around self-supervised learning over the past couple of years, but I would like to kind of talk about one approach that I'm very excited about in particular, which is called the image joint embedding predictive architecture. And this approach works as follows. So we're going to have an image and we're going to think of breaking that image into patches. We're going to take a small subset of the patches and call those a context. And we're going to pass those through some encoder. This could be whatever your favorite backbone is. Let's say it's some vision transformer or ResNet to get some embedding of those patches. We're also going to take a target. From the same image, we're going to take a number of targets shown by these different colored boxes here, which don't necessarily overlap with the context. And we're going to encode those, and we're going to ask a predictor, given the encoding of the embeddings of the context and information about what is the region to predict what is the embedding or the representation of those regions if it had seen that. And we're going to train it in order to make those predictions. So we're going to train both the encoder and the predictor simultaneously to do this. And it turns out this approach is very effective. I won't go into all the details again in the interest of time. But one nice thing is that this approach does not require any handcrafted data augmentations. We're only using a sort of a form of masking here. And one other nice property of these embeddings, which I think makes them useful in general, but also maybe in the context of federated learning, is that they work quite well when you consider downstream tasks where you have a very small amount of labeled data and you would like to transfer very quickly. And so, for example, we set a new state-of-the-art for this ImageNet 1% semi-supervised evaluation task. This is where we do pre-training, and then for the downstream task, we receive only 1% of ImageNet with labels, and so that corresponds to having about 10 to 12 labeled examples per class. And you can see kind of the numbers here. It's showing the top one accuracy for this IJEPA, image joint embedding predictive architecture approach. compared to some of the other methods from the literature. Great. So if you want to learn more about this, then I invite you to come stop by the poster, which is going to be presented at the main conference on Wednesday, Wednesday evening, or I guess afternoon. Yes. And let me conclude or begin to conclude. So I hope the main message that you take away from the talk today is that pre-training can help alleviate the effects of heterogeneity in federated learning. I think there's still a lot more that we need to study to understand this phenomenon better, but I really do believe that there's something there. And as a recommendation to the community going forward, I'd like to suggest that when we're thinking about evaluating different methods, we shouldn't just evaluate them starting from randomized initializations, but we should also think about how they might behave if you're starting from some sort of a pre-trained initialization, because these seem to have qualitatively different behaviors for quite a few different algorithms. And in practice, we might be able to start, not always, but in many applications, we might be able to start from a pre-trained initialization. Thinking about future work, there for sure, I think we need to have some theory to better quantify the effects of initialization and pre-training in federated learning, and maybe also in general. Of course, there's issues that we'll need to also get a better handle on, things like how does the data set that you do your pre-training on potentially introduce biases, or more generally, how do we handle distribution shift between the data set that we're pre-training on and then what we were doing federated training on afterwards. And like I hinted at the end of the talk there's other forms of pre-training besides supervised pre-training that seem very both interesting and important to study further, things like meta-learning and self-supervised learning. And I'm going to wrap up early, but hopefully there's maybe a couple of questions and then we can also enjoy lunch. Thank you very much for your attention.
Hi, thank you so much for that great talk. I just was wondering about the speed up that you may have observed regarding basically pre-training the models. What kind of epochs did you save in terms of server time or like training time?
So we didn't try to quantify it specifically for this study. I think you could go about doing this kind of a study in one of two ways. One is you fix the number of rounds that you're going to do for federated training for all algorithms, and you see what is the final accuracy that you get to. The other approach, which we didn't do, but which could be done, would be to fix a target accuracy and see how long it takes each method to get there from different initializations, and that would help to quantify this speed up.
So part of this study, what was the cutoff mechanism?
Which cutoff?
Basically for the training, loss stopped going and you just stopped.
What was the stopping?
Yeah.
So we fixed the number of rounds. So we said every algorithm gets to run for, I forget, it changed for each workload, but say 1,000 rounds. And we see who gets to the best accuracy at the end of the 1,000 rounds.
Fair enough. Thank you so much.
I can have backup slides. Yeah, so this would be, these are, I wouldn't read too much from this, but this is the kind of thing that you see if you look at some of the training curves, right? Now keep in mind that, so I hesitate to draw too many conclusions from these because the learning algorithm, the learning rates here were tuned to get the best final accuracy for each method, not to get to a target accuracy as quickly as possible. So that might change things. But you see, for example, with CFAR, at initialization, the accuracies are not too different between pre-trained, which is in blue, and random, which is in orange. But it learns much quicker. Again, this is without quantifying.
Yeah.
Yeah.
Okay. Fair enough. Thank you so much.
You're welcome. Thank you.
This question refers to the slide which you just showed.
No.
So you always talked about the final accuracy, but what is the collaboration gain, right? So if you start with a pre-trained model and just use local data, you have a standalone accuracy. Compared to that, how much improvement do you get through the federation process?
Right. Okay, so this is a good question. What if you were to just have the pre-trained features and only train locally on device? Is that what you're asking? Yes. So I don't remember if we looked at that specifically in the paper. I think for most, yeah, so I don't have a concrete answer for that one. Other than to say, I believe that there is a gain. What we did look at in the paper, in the appendix, is what if you were to freeze the backbone and only train the classification head in a federated manner? And you definitely see a non-trivial gap between doing that and training the entire model end to end in a federated way, even from the pre-trained initialization. So my hunch is that I think some of these problems are even set up so that the question might be ill-posed if you don't do federated training, in the sense that any individual client does not have instances of all classes. And so you have to think carefully about how to evaluate in that setting as well. But it's a good question. It is a good question.
So I guess in that sense, you have the pre-training model, then you just train the locally. That's kind of like centralized transfer learning. Yeah. So that definitely, if the data distribution, is similar, or we all using ImageNet pre-trained model to fine tune. So in general, I think it will improve performance locally. Yes. I do have a question.
Okay.
So I think this is a very insightful work. We actually look at your paper, and also I think one other group from Ohio State, they also analyze the pre-trained model and train from scratch. So it gets maybe similar conclusion. So I was also wondering if you explore here you're using the supervised pre-trained model, right? So what about the self-supervised, like Dino V2, Dino series? Like what's the difference? Or which one we should, choose, in practice?
Yeah, so I think that's a great question. I don't have conclusions to share with you today, but I think it's definitely a question worth asking. Yeah.
Oh, hello. May I ask a question online?
Please go ahead.
Yeah, sure. Go ahead.
Yeah, I see your future work mentioned self-supervised learning for the pre-training. Can you elaborate a little bit how the self-supervised can be done with the pre-training?
Sure. So I'm thinking in this case of doing self-supervised pre-training in offline, not in the federated phase. There's several methods that have been proposed in the literature for how to do this. The IJEPA one is a recent one that I just mentioned, but there's several predecessors before that. So it depends on, kind of the modality of data that you want to deal with, whether it's images, images and text, and so on. I guess if you have specifics in mind, I'm happy to follow up offline and with suggestions for what you could consider there. But I think there's already kind of substantial and growing literature around various ways to do self-supervised pre-training. I don't know if that helps.
Okay, thank you very much.
Yeah.
Okay. So thank you again. So thank you, everyone. You have a question? Okay. All right, thank you. Right. So yeah, thank you all for coming to the morning session. So we're gonna start the afternoon session at 1:30 p.m. Okay. Thank you. So much. Going well so far. Going well so far. Is Dr. Shaw here? Dr. Shaw is here, right? Okay. We're not doing the CRCV launch anymore? Wednesday? Okay. Problem is. I know. Wednesday. Because usually you don't have to do the installation and the local logics, but self-supervised training, you're just training.
Yeah, okay. Thank you everyone for joining our afternoon session of the Federation workshop. So our first speaker of the afternoon session is Dr. Gloria George. She's an associate professor at the ECE department at Carnegie Mellon. And she's research focused on designing scalable algorithms for distributed machine learning and large-scale parallel computing. So, well, welcome, Dr. George. Will give us the talk. Thank you.
Good afternoon, everyone. First of all, thank you very much for the invitation and for the introduction. I'm happy to present my group's work on tackling heterogeneity in federated learning. So in this talk, I'm going to go over several different pieces of work from my group, which are joint work with several students at CMU, as well as collaborators from IBM and Google who are listed here. So to start, I'm going to give a very brief 1 or 2 minute introduction to motivate federated learning and heterogeneity in federated learning. So hopefully I won't bore those of you who know federated learning very well already. So as all of you know, today a majority of machine learning training is performed in cloud, in the data center settings, where you have a parameter server and many worker nodes which store partitions of the training data set. And a typical training process works like this. So the worker nodes, they read the current version of the model from the parameter server, and then they compute and send back gradients using samples drawn from their partition of the data set. And then the parameter server aggregates these gradients together to update the model, which is represented here by X. So synchronization delays due to slow workers or due to communication delays on this link between the parameter server and the workers can be a hurdle to scaling this framework to a large number of worker nodes. And over the past few years, there has been a lot of research in improving the scalability of this framework with algorithms such as asynchronous SGD, local update SGD, overlapping communication, computation, and so on. So there's been a lot of work on improving this setting. But in many modern applications, this paradigm of transferring all the data to the cloud doesn't work well, because data is collected at edge devices like cell phones, IoT sensors, tablets, etc. And if we had to send all of these data to the cloud, it would be expensive and slow, especially because these devices have resource constraints and limited network connection. Moreover, there can be privacy constraints due to which you cannot just send the data to the cloud. So that's where federated learning comes in, which tries to operate within these constraints by keeping the data on the device and shifting model training to the edge. So each client node here, represented by the cell phones, has their own data set that is collected from their environment. And they read the current version of the model and perform a few local steps of gradient descent, and only send back the resulting model updates to the cloud. So the data never leaves the device. And because of this, we have better communication efficiency as well as better privacy than the standard parameter server setting. So now let me more concretely define the objectives and the notation that I'm going to use for the rest of the talk. So here, what we'll consider is that you have a system of M devices. These are edge devices, and they have their own data sets. And these data sets induce local objective functions, Fi, which are empirical risk function computed over their data sets. And the global objective, which is shown as f of x there, is a weighted average of these local objective functions, where the weights pi are proportional to the size of the data set at the ith client. So the global objective, that's why f of x is summation of pi fi over all the clients in the system. So the goal of federated optimization is to find the model X that minimizes this global objective function that is find the global minimum of this objective function. Now, there are variants of this objective that are studied in the literature, such as in personalized federated learning, where you don't want to have a single global model. But for the purpose of this talk, I'm going to just focus on this objective where you want one global model that should work well for all the clients in the system. So that was the notation. Next, let me talk about the algorithm, the standard algorithm Fed averaging, which is used in most current implementations. So in this algorithm, what happens is that each of these clients perform tau local updates, where tau is a parameter that can be set by the system designer. So the algorithm operates in communication rounds, where at the beginning of each round, the current model is sent to the clients. Then these clients do tau steps of local SGD, and their resulting models, which are these XI. Now note that they are different from each other because the clients have heterogeneous data sets. So these resulting models are then aggregated by the central server by just averaging them in proportion of the sizes of the local data set. So this is the vanilla Fed averaging algorithm. And the goal of my talk here is to understand how this algorithm is affected by heterogeneity in the system, because heterogeneity is what sets federated averaging apart from distributed SGD in the data center setting. So what do I mean by heterogeneity? There are actually several sources of heterogeneity in federated learning. So I'm going to talk about 3 of them in this talk. The first is data heterogeneity. So as I said before, the data sets and hence the objective functions are different across these clients. And due to this, the local models start to drift apart from each other as they do more and more local steps. So that is what I mean by data heterogeneity. The second source of heterogeneity is communication heterogeneity. So in a typical federated learning framework, there can be thousands of these edge clients. And at a given time, only a few of them are available. And this is because of diurnal patterns, time zone, or geographical patterns where the clients are available for training only when they are plugged in for charging. So at a given time, out of these thousands, only a fraction C are available. And using these clients, the global model is updated. So this is what I mean by communication heterogeneity, because as you go from one round of training to another, the set of clients that are participating keeps on changing. And that's why the global model will also move towards the set of clients that are currently participating, and then it will shift towards the next set of clients who participate later on, and so on. So communication heterogeneity combined with data heterogeneity can affect conversions pretty drastically, because as you have more and more data heterogeneity and communication heterogeneity, it just gets worse. So the third source of heterogeneity is computational heterogeneity. So here, the edge devices are not homogeneous. So since these are, there are thousands of these edge clients distributed all over the world, they can be different in terms of their local computation speeds as well as memory. And therefore, it is not ideal to force all of them to do the same number of local updates. So in practice, maybe some devices do more local updates than others, and we should have a way of dealing with this type of heterogeneity in the system. Moreover, even if they do the same number of local updates, they can have different learning rates, or they may use adaptive local optimizers. So overall, these sources of heterogeneity are already there, and it is ideal for an algorithm to operate within these constraints and not force all the clients to be homogeneous, because heterogeneity makes the system more scalable and flexible. So the goal of this talk is to understand how these sources affect federated optimization algorithms, and then come up with strategies to mitigate the effect of heterogeneity while still preserving fast conversion speed. So with that, let me start off with data heterogeneity, and I'm going to show you a toy example to illustrate why data heterogeneity is a problem. So in this toy example, let's just consider you have two client nodes, and the x1 star and x2 star are the local optima. So these are the models that minimize the local objective functions of those two clients. And x star, there shown in green, is the global optimum. So because of data heterogeneity, these are three different points rather than all coinciding. And suppose we start off with that black dot, which is the current model, and each of these clients do just one local update. So if they do just one local update and we average them, then you can see that this global model moves towards that green dot, which is x star. So in this case, when you are doing just one local update at the client, data heterogeneity is not a problem, because the global gradient which is the average of this local gradient, is consistent with the global objective function. On the other hand, if you consider that these clients do a large number of local updates, which is what happens in practice, then each of them will reach close to their own local optima. And when we average these models, we get an average of the local optimas, which may not match with the global optimum. So as you do more and more local updates, data heterogeneity becomes a bigger problem. And how do you quantify how this affects the conversion speed? So several works in the literature have done this. So what they do is that they consider a bound on the heterogeneity, which is called the gradient dissimilarity bound, and then compute quantify how the error decays with the number of communication routes. So this is the error bounds. You don't have to look at the details. The high level idea is that the first two terms in this bound correspond to mini batch stochastic gradient noise. And the last term here, you can see it increases with tau, which is the number of local updates. So this is the term that is coming due to data heterogeneity. And this is called the client drift error term. So many works over the past few years in federated learning have tried to remove or reduce this client drift error. And some of the methods are such as reducing the learning rate at the client so that the local models do not drift too far away from the global model. Another way is to adapt the tau over round. So you start off with a large value of tau and then slowly reduce it over time. Or you can add a correction term to pull back the drifted local models towards the global model. So this is done in work such as FedProc, Scaffold, etc. So all of these methods, they work well to reduce the client drift, but they can slow down conversions because essentially you're pulling back the local models towards the global model. And in order to compensate for that slowdown, in theory, these works propose that we should use a larger server-side learning rate. So instead of the default value 1, which corresponds to just averaging the local models, like I've shown in the blue cloud over there, you can use a larger value of the server learning rate. But in practice, doing this can cause a large error in conversions. So in our recent work, which was in ICLR this year, we propose an adaptive schedule for the learning rate at the server. So here, when the server aggregates the local models, it gives them a weight which is proportional to the squared magnitude of the local updates in total. So you're summing over all the clients and then using that to decide the learning rate. And this gives a much better conversions than previous methods where you just use a fixed learning rate or a fixed large learning rate. Now, this method is inspired by the EPPM method, which was proposed for projection on convex sets. And we have convergence guarantees for this in the over-parameterized regime, where this X is high dimensional. But in practice, it also works well in the under-parameterized regime. So these are some simulation results which show that the blue curve, which is the Fed-EXP algorithm that we propose, does much better than Fed averaging and scaffold and other methods. So that was about data heterogeneity. There are some interesting open questions still left. So one of the open questions is that Fed averaging, which is the vanilla algorithm, actually works pretty well in practice, even in the presence of data heterogeneity, without using these methods to mitigate client drift. So one open question is trying to bridge this gap between theory and practice. And one conjecture that we have is that the gradient dissimilarity assumption, which is used in many theory works, may be too pessimistic. So we can try to come up with a more realistic data heterogeneity metric, which can give us a better idea of how the convergence is affected by data heterogeneity. So I'm not going to go into the details of that work. You can check it out with the link that I'll show at the end of the talk. So the second open question actually leads me to the second part of my talk. So if we go back to this bound that I was showing before, the client drift error term, you can notice that there is a eta square there, where eta is the learning rate. So if you look at the different terms in this bound, when you set a small learning rate eta, this client drift error term actually decays faster than the other terms. So it is not the dominant term in the bound. And in fact, when we have partial client participation, that is all of the devices don't participate in every round, then the error is of a higher order. So this term is not the dominant term. So what we really need to do is actually try to deal with that partial client participation error, because it is the dominant source of error more than the client drift error. So how does that additional error term come in? So this is an updated bound that I'm showing here with partial client participation. So now instead of all the clients participating, a fraction C of them are participating in every round. So you have a similar error bound. The first two terms are coming from the SGD noise. This last term is the client drift error term. And the third term is the partial client participation error term, which is a new term that comes up because C is smaller than 1. And by setting the learning rate appropriately, if you look at the orders of these terms, we can see that the partial participation term dominates because it decays at the rate 1 over square root of t, whereas the client drift error term decays as 1 over t. So in another recent work, we try to mitigate this partial participation term. And the idea that we use is that the client updates are correlated across rounds. So let's say you have one edge client, it participates in one round, and then it goes away for 5 rounds after that and comes back again later on. So when it goes away, the updates that it would have sent wouldn't be too different from the updates that it sent when it did participate. So that is the idea that we'll use. When we have missing clients, we try to use the latest observed update from that client as a proxy for their missing update. So to formalize that idea, what we do is that at the server, suppose we maintain a memory for each client. So whenever a client sends an update, you just store it in the server memory. And at any given round, when a subset of the clients participate, we use their update. And for all the missing clients, we use updates that are stored in server memory. So the combined update, which is a variance reduced update, is shown here. So these Ys are updates that are stored in server memory, and the deltas are the new updates that are sent by the clients, and you take a weighted combination of these to compute the variance reduced update, which is used to change the global model. So in theory, we can show that this idea actually eliminates the partial participation error term. So it is as if all the clients had participated and you did not have a bunch of missing clients. So there are some caveats here. We have to assume that the subset of clients which are participating are selected uniformly at random. And then you have this server memory for each of the clients in the system. So in practice, having such a large server memory buffer is not possible because you may have thousands of clients, but we can modify the algorithm to account for that. So we can consider a clustered version of this algorithm where instead of storing in memory a state for each client, you cluster clients together and only store one state for each cluster of clients. And even that algorithm does pretty well. It does almost as good as the original Fed-warp algorithm, but with much less memory cost. So these are some simulation results which show that Fed-warp and its clustered version outperform Fed averaging and other algorithms that are previously proposed. So that was about overcoming the variance coming from partial client participation. Next, I'm going to talk about client selection. So until now, what we were considering is that when a subset of clients participate, those clients are chosen uniformly at random from the whole population. But what if we are allowed to be selective and not necessarily choose clients in this unbiased manner? So what if we try to select clients in proportion of their local losses? So if you look at that objective function over there, f of x, it is a summation over the local objectives. So clients which have high values of their local objectives, fi, will dominate that sum. So what if we preferentially select those clients that have high values of fi? Maybe that will give us a faster convergence. So that is the idea that we use in this client selection work, where instead of choosing clients uniformly at random, we select higher loss clients. So this is a toy example to illustrate why that should work. So on the left side, I'm showing unbiased random selection. Here we only have two clients whose objective functions are shown in blue and green. And the red color curve is the global objective function. So if we select clients at random, then we keep switching back and forth between the green curve and the blue curve. And we try to take one step of gradient descent on each of these curves. And eventually, we will end up finding the minimum of the red color curve, which is the global objective. On the other hand, if we select higher loss clients all the time, then you always move down the green curve at the beginning. And then when that green curve dips below the blue curve, then you switch to the blue curve. So you get to the minimum much faster than what you would have done if you kept switching back and forth between the two clients. So that is the idea. Biasing can give faster conversions. On the other hand, biasing towards higher loss clients may lead to a bias in the solution as well, because now those clients are overrepresented in our global model. So we can also quantify that formally. I'm not going to show the details here. This slide defines a metric called selection skew, which measures that bias which is introduced in the client selection. So that selection skew is denoted by rho. And if you do unbiased selection, then this rho is just equal to 1. If we bias towards selecting higher loss clients, then it is greater than 1. And if we bias towards selecting lower loss clients, then it is less than 1. And we can show that the error after T communication rounds is given like this, where there is a rho appearing in the denominator. So which shows that as you increase the selection skew, you get faster conversions. But then you do increase the bias term, this last term, a little bit as you increase the value of rho. So inspired by this analysis, we propose a client selection scheme, which is called Power of D choices. So here, what we do is that in every round, instead of just selecting clients at random, we sample a candidate set of clients at random and then estimate their local losses and then choose a subset of this candidate set, which has the highest losses. So the candidate set has size D. And then from these D, you select a set of M clients which will participate in that set of CM clients. So you can see that D here is a tunable parameter. If we set D is equal to CM, then we go back to unbiased client selection. And as we increase the value of D, you're biasing more and more towards higher loss clients. And this idea of first selecting a bigger set and then narrowing it down to a smaller set has been actually used in SGD to improve conversions. So just in vanilla mini batch SGD. So we are using the same idea in the context of client selection and federated learning. And this does improve conversions, as you can see in some of these experimental results. So the random scheme is just unbiased client selection. And as you increase the value of D, you're becoming more and more biased towards higher loss clients. So we get faster conversions, especially at the beginning. But we do suffer from a slightly higher bias at the end. So to get the best of both worlds, we could adapt D over time. So you could start off with a large value of D and then reduce it so that we get fast conversions as well as a low solution bias at the end. And a drawback of this method is that the step 2 that I'm showing here is kind of expensive because you have to estimate the local losses at the clients. So we also have communication and computation variants of the method that reduce this cost. So these computation and communication efficient variants, which are shown in blue and green, give almost the same performance, but at much lower cost. And another interesting thing that we see in these results is that if you have more data heterogeneity across the clients, then actually these client selection strategies give a bigger gain in terms of the conversion speed and the final test accuracy. So the left side shows less data heterogeneity. So you can see that the gap in the curves is smaller, whereas in the case of more data heterogeneity, the increase in test accuracy that you see as compared to the random selection scheme is much higher. So some open directions in client selection are that can these kind of client selection strategies improve fairness or robustness of federated learning? Because you're preferentially selecting clients which have a higher loss, which might have some minority data. And initial results that we have indicate that this is true if these client selection methods can also improve fairness, but we still need to quantify that formally. On the other hand, these can also improve robustness. So if you select clients in the opposite way, instead of choosing higher loss clients, if you try to select lower loss clients, then you can get rid of adversarial clients that might be sending high values of local gradients in order to poison the global model. So these kind of client selection strategies can be used in both ways to improve robustness as well as fairness if we combine both these types of client selection together. So finally, in communication heterogeneity, I want to mention a work where you do not actively select clients, but you just let them participate based on the cyclic availability pattern that is there naturally. So as I mentioned earlier, these clients may be available based on the time zone that they lie in. So for example, when it is day here in North America, the clients here are not available because their cell phones are not plugged in for charging, and people in Asia who have plugged in their cell phones for charging, they might be available. So based on these cyclic availability patterns, we need to understand how federated averaging convergence is affected by these. Unfortunately, the current analyses, they do not consider these kind of patterns. They consider that from the entire population, you're selecting clients uniformly at random. So in our recent work, we tried to understand what happens if clients are cyclically available like this. So first, you have this first group of clients which is available, and we sample from that. Then in round 2, you have a different group of clients that is available, and then we are subsampling from that group, and so on. So the question that we try to answer here is, can we improve on the convergence rate order of 1/t that we get with Fed averaging for gradient descent done locally by doing this kind of cyclic client participation? And in our work, we analyze the convergence of federated learning under this cyclic participation setting. And then we show that if K bar is the number of client groups, so that is the gray color circles that I'm showing there, which become available one by one. Then for local gradient descent, we have this kind of a convergence bound. So the high level takeaway from this bound is that if you look at the first two terms, these are decaying at the rate 1/t square rather than 1/t. So you get a faster convergence rate with respect to the number of communication rounds. The last term, however, does decay as 1/t, but this term disappears if you have full participation within each group. That is, that blue color circle overlaps entirely with the gray color circle that I'm showing there. So we have similar bounds for local SGD and shuffled SGD as well. And we can show that as the number of client groups increase, we do get better convergence. So this is kind of a positive result, which shows that in practice, you can do better than what the theory tells us. So in theory, we assume unbiased client selection, whereas in practice, you have this cyclic availability of clients, and that actually gives a faster convergence rate than unbiased client selection. So I think I have only a few minutes left. So in the remaining time, I'm going to briefly touch upon computational heterogeneity, and then I'll take questions. So the last source of heterogeneity, as I mentioned earlier, is computational heterogeneity, where these client devices may have different speeds and they may do different numbers of local updates. So why is that a problem? So to understand that, let's again go to our toy example. So this is the homogeneous setting where you have X star, the global optimum, and X1 star, X2 star, which are the two clients' local optima. Now, if both of these clients do the same number of local updates, then we can show that for small enough learning rate, and if the number of local updates is not too large, we can indeed converge to the global optimum. However, if we have a heterogeneous setting where, let's say, the first client does a lot more local updates, and then we just average these resulting models naively, then we get a solution that is biased towards the first client. And this bias cannot be easily fixed by the techniques that are used to tackle data heterogeneity, because they just simply slow down this local progress at the clients, and they do not change the aggregation method. So in our work, FedNova, which Mike kindly mentioned in his talk this morning, we propose a generalized algorithm that tries to fix this problem by fixing the aggregation method at the server. So what we identify is that instead of the true objective, if you just naively average the models, it ends up optimizing a mismatched objective, which is biased towards clients that do more local updates. And to fix this, what we need to do is normalize the local updates. So in the original Fed averaging update rule, you would just average the dotted blue colored arrows, which are the local updates at the two clients. Instead, what we do in FedNova is that we normalize these updates by the number of local steps that are taken by the client. So since the first client takes 4 local steps, we normalize that arrow by 4. The second client does 2 local steps, so we divide that by 2, and then average those 2 green arrows instead of averaging the blue arrows. And we can adjust the magnitude of that averaged value by something like a server learning rate to make sure that we are not slowing down because we are normalizing the gradients. So this is the FedNova update rule, which does a simple fix to the original Fed averaging update rule and ensures that we are consistent with the global objective. And the FedNova aggregation method that I'm showing here works well for a whole range of client optimizers. So instead of vanilla local SGD, if we can do momentum SGD, proximal SGD, etc., it would still work. And it gives much faster conversions than regular Fed averaging. Recently, we also have a work that extends this to local adaptive optimizers, but I'm not going to go into that today. So with that, let me summarize. So today I talked about several sources of heterogeneity in federated learning and algorithms to cope with those sources of heterogeneity while ensuring fast convergence of federated averaging. So there are several interesting open directions, and these open directions are all related to modifying this objective function that I had. So in this objective function, we are only looking for a single global model, but we can modify that by considering that you have heterogeneous models at the different clients, where some clients may have a larger neural network, some clients might be training a smaller neural network, and how to combine them into a single global model. We can also consider concept drift in the data at the clients, or personalized federated learning, and also consider incentives for clients to participate or not in this federated learning process. So these are just some of the open directions, and there's still lots of exciting new problems in this space. So with that, let me end, and I'll just flash the archive links to our papers, which you can find online, and that's it. Thank you.
Thank you very much. My question is regarding what you talked about using the lowest laws to back out potentially adversarial. Isn't this counterintuitive with the fact that with the rationale behind using the highest law in the first place?
Yes. So that's a good question. So the question is saying that in the client selection work, I mentioned that you should try to bias towards higher loss clients, but then I said that to improve robustness, we should bias towards lower loss clients. So to get the best of both of these trends, what you could do is first consider a candidate set of clients, then select the lowest loss ones among them so that you winnow out the clients which might potentially be adversarial. And then in that reduced set, you select the higher loss clients. So you can take you can do a combination of both these approaches.
Isn't this kind of more or less a reformulation of the robust aggregation in the sense of you cut the tail of the distribution that you have more or less?
Yes, so that's the same idea. By removing the by removing the higher loss clients, you are kind of doing robust aggregation. But here we are not doing that at the aggregation stage, but rather at the client selection stage. Mm-hmm.
Yeah. Really nice talk, Ray. Thanks. I was curious about the client selection and privacy, and if you can talk a bit about that.
Oh, okay. So that's a good question. Privacy is something that we have not considered a lot in these works, but one of the concerns that could happen with client selection is that you get estimates of the local losses, which could lead to privacy concerns. But if we consider just noisy estimates, then privacy may not be an issue because the clients are not sharing data, but they're just sending gradient estimates, which they would have done anyway. So maybe that answers your question. Yeah, thanks. Mm-hmm.
Yeah. So is data heterogeneity really a problem, or is it a problem with the optimization method? So a lot of these things, I mean, ideally you want higher data heterogeneity, right? Because then only you can learn a generalized.
Right. So it's a double-edged sword. So as you said, having more data heterogeneity means you have more diverse data that is incorporated in the global model. So in theory, data heterogeneity is a problem because the optimization algorithm doesn't converge if you have unbounded data heterogeneity. So you have to have some bound on it. But in practice, what is observed is even the regular Fed averaging algorithm works pretty well. So you don't have to do much to counter data heterogeneity since the data is somewhat similar. But if you want provably provable convergence guarantees, then you have to come up with some techniques to combat data heterogeneity.
All right, so I have a quick question.
Yes.
So for the mutation heterogeneity you just mentioned, it's because of the resource on the edge clients. Like, I don't have the bandwidth to compute this many, local training epochs. Some have like larger memory or computation. It can perform maybe more local training epochs. So what is the cause for the computation heterogeneity? Are you referring this to the system heterogeneity, or this is different?
So one of the reasons is system heterogeneity. Some clients might be naturally faster than others, but another reason could be that the current algorithms often, they don't follow the procedure that I said where you do tau local updates at the clients, but the current implementations often do tau local epochs at the clients. So when you say epochs, that means a whole traversal of the whole local data set, right? And the sizes of the local data sets are different at the different clients. So if you do the same number of local epochs, you might end up doing way more local updates at some clients and less local updates at other clients.
Yeah. So I think that can be, in general, considered like a straddle form. Right? So that can be one reason, not for the communication, but for maybe the size of the local.
Yeah. So due to stragglers also. So one way to overcome stragglers is actually to allow such computational heterogeneity where faster clients can do more local updates and slower clients can do less.
Asynchronous better learning can solve this problem, or?
Yes, so asynchronous federated learning is another way to solve this problem. So instead of allowing clients to do different numbers of local updates, they still do the same number of local updates, but they are aggregated in an asynchronous manner. So yes, asynchronous federated learning is a way to address that problem. Yeah.
Okay. Right. Thank you.
Yeah.
Thank you again.
Thank you.
So I think we have our last keynote speaker, Dr. Lee from UIUC. I think she's online now. Dr. Lee, can you hear us?
Yes. Okay.
Okay. Okay, so if we, yeah, I think you share the screen.
See the screen.
Okay, all right. So yeah, let me first do a brief introduction of Dr. Lee. Is a assistant professor in the computer science department at the University of Illinois at Urbana-Champaign. Her research focuses on trustworthy machine learning with emphasis on robustness, privacy, generalization, and their interconnections. So, and Dr. Lee I'll take the stage. All right, thank you.
Yeah, thank you. Yeah, thank you, everyone. Sorry I cannot join in person this time. So today I will briefly talk about the certifiably trustworthy effective learning from certain perspectives, including robustness, privacy, and generalization. And of course, we don't have enough time to cover everything, but I hope from one of the angles, you can see the principle and bring the principle to general ideas. So first of all, as we can, everyone already know that federated learning has been used in different domains, including the V2X, autonomous drive networks, smart city, and even medical data and etc. places. But also they have such like powerful techniques, including federated learning and different frameworks of protocols of federated learning have also brought a lot of security and privacy concerns, including in 2026, the social press Twitter account was hacked via phishing emails, which has triggered the autonomous trading bot in a decentralized collaborative way to dump a large amount of stocks, which swept about $130 billion. And similarly, I heard a question related to privacy, and indeed that's a problem and concern when we use the powerful federated learning techniques in different domains. So I will briefly talk about these potential perspectives and some potential solutions. Obviously, it's not the end of the solution. So basically the question or the key question we want to explore here is what are unique challenges of trustworthy issues for federated learning, such as robustness, privacy, and generalization, and how we can provide certain types of guarantees to it in addition to our empirical analysis and defense approaches. So on the high level, in such a federated learning scenario with different heterogeneous agents and servers so that they can communicate and train the models, either a final one global model or a set of final models, depends on the different utilities and the requirements such as personalized and like unified models. No matter what types of protocol is, here we always face some security and privacy trustworthiness questions, including how to improve the robustness to unseen data manipulations, how to guarantee the privacy like verifications, for instance, differential privacy or other types of privacy metrics. And finally, how to improve the generalization of such a framework of models generalized to unseen data distributions. So in this talk, I'll mainly talk about robustness and privacy perspective, with the central goal of closing the trustworthiness gap between the distributions of training and testing. For instance, from the robustness perspective, we're trying to understand and deal with the adversarial manipulation of either training and testing distribution, which we should be more or less familiar when the attackers can manipulate the training. We usually refer it to poisoning or backdoor attacks, which is quite severe in federated learning case, because we know that in practice in federated learning frameworks, we have no control about the adversary or the authentication of the participant agents. So some of them could be free riders or even adversarial, which could lead to potential security concerns. And similarly, from the privacy perspective, we're trying to minimize the output distribution distance to protect the sensitive private information in the training. And similarly, from the generalization perspective, we're exactly trying to deal with the general data distribution shift compared with the adversarial data manipulation in the robustness case. So I would want to emphasize in this talk that not only these individual pillars here, but also their underlying connections are very important. We have spent a lot of effort focusing on uncovering the fundamental underlying connections among different aspects. For instance, we proved that the certified robustness of a federated learning framework can be represented as a function of epsilon delta for epsilon delta differentially private model. So with all these underlying connections, I think we'll have a holistic view of trustworthy machine learning or trustworthy federated learning itself with a complete view. So in this talk, first, let's talk about robustness, which is very important and quite interesting. So as we shown before that, say, given such a distributed federated learning framework, since we have no control of the authentication of different agents, it's possible that some of the agents are adversarial. So in this case, there are several work in the past showing that it's very possible for, say, a trained agent or participated agent to add some so-called backdoor triggers so that you can either fine-tune or train from scratch to train a federated learning framework by integrating some adversaries, and then the final trained model will be adversarial. Say during testing time, if there is some test data with similar triggers, then the test data can be predicted to be arbitrary adversarial target as designed by adversaries. But in practice, in this distributed framework, there are more interesting things can be done for adversaries. For instance, here, not only a single trigger is injected by an agent, but also it's very possible to design more stealthy attack, which is here, like say the original backdoor trigger is still this 4 rectangles, but then it's possible to separate them into different agents so that in practice, no agent will actually have the entire backdoor trigger. So that even you have the, say, infinite human power to look at each data and try to find the potential backdoor trigger, you will not be able to do that because such a backdoor trigger just never happens in the training data. So in this way, we can imagine the attack stealthiness is significantly improved here, but then we wonder how effective the attack itself. So let's take a look at a quick result for the effectiveness here. So the solid line shows this so-called, we call it distributed attack, which the trigger is distributed to different agents. And the dashed line shows the centralized attack, which is the trigger is given to one of the agents during training. And surprisingly, you can see not only that the attack success rate is higher for the solid lines compared with corresponding dashed lines, but also the attack effectiveness maintained longer for such solid lines because we add the trigger at the epoch here, and then we do vanilla fine-tuning later on. We want to see that how severe the backdoor should maintain over the later iterations. And you can see the solid line actually is very effective by maintaining the adversarial behaviors over different iterations later. So that is to say, with such distributed backdoor attacks, not only is more stealthy, but also the attack effectiveness is even higher, which raises a lot of concerns. So based on such interesting threat model and a bunch of previous threat model in terms of training time or backdoor attack for federated learning, which is quite realistic, then we can see there are different defenses developed against certain attacks. But all these defenses are empirical, and it's very important to provide certain certified robustness for federated learning or general ML cases so that we can have some guarantees for the robustness we get. So here in the past, there are several work proposed against the test time attacks in order to provide a lower bound of accuracy for the model given any adversarial constraints, so that such certification can be categorized as complete and incomplete based on different relaxations, etc. So I will not go to too much detail here, but the conclusion is that it's possible to certify ML against test time attack under certain adversarial constraints so that we don't need to worry about future adaptive attacks. but there is no work that can provide the robustness certification on the FL cases, especially against the training time attack, like the backdoor attacks we showed before. So in this case, here we want to introduce the first certified robustness of federated learning against the training time attacks. And before we go into detailed algorithms and certification, first of all, we need to finalize what do we mean by certification and what's the final goal we want to achieve in order to provide certified robustness for federated learning. So here we can see in the traditional federated learning, we have vanilla data and every agent have different data or data distributions, either heterogeneous or homogeneous, and then communicate with the server and train the final central model like that. And in the adversarial case, some of the data of an agent could be adversarial. For instance, here, some of the data have the triggers, say a triangle trigger, so that the final trained model will be polluted and will be poisoned in a way. So that during testing time, if you have a data point with a trigger, that the performance of the test data will be adversarial, like achieve any adversarial designed target. So in this case, we would say, in order to provide a certification, our goal is to provide a prediction such that no matter whether there is an adversarial agent in the training or not, the prediction of any given test data would be the same. So that would be the certification goal. So let me emphasize that again, which means given a federated learning framework, if it's trained with or without adversary during testing time, given the same test data, the model performance will be the same. So that will be the certification goal we achieve, we aim to achieve, so that we can see even with adversarial agents, the performance of during testing time will not be affected. So that's our goal, right? But of course, such an equivalence of the performance depends on the constraints and the properties of the attacks. So then let's look at what's the sufficient condition or the properties that the attackers need to achieve so that such certification can be obtained, approved rigorously in the end. So we can see here in the federated learning training, let's say in a vanilla training case, we have different agents, and then let's put the benign and the adversary agent side by side for analysis. So here we can see we have two types of data set. One is benign, one is adversary, and we assume within the data set we have this number, like R number of adversarial agent. So basically there are three levels of perturbations. One is the number of adversarial agent. One is for each adversarial agent, the maximum poisoning ratio, meaning how many data points can be manipulated within their data set. And then the third level is pixel level, which is like how large is a perturbation backdoor trigger could be such that the attacks will be effective and the defense will always be certifiable against that. So based on this, we can see that given these two types of data, we can train two types of models based on standard federated learning, including like some model updates sent to the server and then aggregate the model. The server will send the aggregated result back to the agent. So we can see here, in traditional training, we directly send the model update to the server and the server will send the aggregated result back. But here we will do some slightly updates for the training process, which is first of all, when the server sends the aggregated model back, the server need to clip the model parameters to a reasonable range and then add some perturbations to it, which means that we can constrain the sensitivity of the model itself. So we can see here, based on this, because we constrain the sensitivity of the model itself, then we can calculate the model closeness between the clean and the poisoned global model. So that's the first thing we obtained during training. And then with these two models, which we can control their closeness, then during testing time, we can perform certain parameter smoothing to got the final performance distance of the prediction. So here we can see, given like a model with, say, the model parameters W, we can sample perturbations of some Gaussian noise from certain Gaussian distribution and add the perturbation to the model parameter directly, so that for each types of noise injection, the model will have a prediction here. And after we add several number of noise, then the model will have several output, and we can take the majority vote over it. So the final result will be a smooth prediction over the different noises added to the model parameters. So basically here we can leverage the majority vote over all the CC is a noise. C is a prediction for each round of the noise added to the model parameter W here. So the nice idea between here is that by taking the majority vote over the predictions for each types of random perturbations for the model, we will be able to get a smooth prediction and therefore be able to control the output based on the model model parameter closeness. So with this, we can see if we can characterize how close the two model is, which is trained with and without adversarial agents. And then we can perform certain parameter smoothing to both of the models. And eventually we will be able to calculate how close the final prediction is, so that we can characterize. Remember, our certification goal is that we want to ensure the prediction is consistent, so that we can trace back to see what's the requirement we need for the model parameters and the training hyperparameters, etc. So this is the high-level process of the training and testing for this certified robust federated learning framework. And then let's put everything together so we can see during training and testing, there is no additional overhead compared with the vanilla, say, Fed average. So basically, we want to, when the server sends the aggregated result back, the server will clip the model parameters and add certain perturbations. And during test time, the server will just add perturbation to the model parameters and then takes the aggregated result as a final prediction. So our goal is that for following this training process, if the training data contain a malicious or without the malicious agent, the prediction of the final model will be the same, given any test dataset, including the dataset with the backdoor triggers, right? So in order to achieve this, as we can see, as we said previously, our goal is to make sure that the prediction is the same for the FL model trained with or without adversarial agents. And eventually, slightly more formally, what we want to get is that, for example, here the M is trained model and D represents the benign dataset, D prime represents the adversarial dataset, and X test is same test dataset, and HS representing the smooth predictions of the model, and S representing the smoothing noise itself. And our final goal is to show that the prediction of the model trained with D and D prime have the same prediction, right? And actually, we can exactly prove it under certain constraints. So let's take a quick look at the constraints to understand a little bit better of what we need to satisfy such that the certification could be obtained eventually. So here we can see, as a quick recall, our certification goal is that the federated learning framework trained with or without adversarial agent will be the same. And our process to achieve that is given two datasets, benign and adversary, and their difference is calculated this way, so that based on such a difference, we can calculate the model closeness by training process, which is clipping and smoothing the aggregated result when the server sends the model back to the agent. And then based on the model closeness, we can do the smoothing prediction and then obtain the final prediction consistency. So to achieve the first step, we bound the KL divergence of the model parameters by viewing the communication intuitions as a Markov kernel, which I will give a little bit more detail later. And once we get the model closeness, second of all, we can leverage Neyman-Pearson lemma to add the perturbations so that to get the consistency evaluation of the final predictions based on the closeness of the model parameters, which is the KL divergence of the models. So then let's take a quick look at each step. So basically, for the first process, as we remember, there are two parts of the training. One is for one iteration, the adversary will add an agent, adversary will add a backdoor. And in the second part is that after the backdoor injection, there are several rounds of benign training, right? So here, in order to get the model closeness in terms of the parameter, we need to characterize these two steps in terms of the model distance, which means for the first step, we can directly assume based on the model smoothness assumption, like here is the Lipschitz constant of the model, then based on the input difference, like the D and D prime, we will be able to calculate the model parameter difference for MD and MD prime, right? And then that's after the first backdoor injection round. And then after that, there are several rounds of benign training, which is very challenging to see how this model closeness goes after several like K round of communications. So here we view this different K round as a Markov kernel so that we can calculate the like the different contrast coefficient based on the trainings, like here rho represents the smoothness and the sigma represents the noise added during the aggregation for the variance, so that it's representing how like sensitive the model is. And then when we compose these two parts together, it represents the final model closeness based on the difference of the like the data set, like the delta, which is a backdoor triggers, and P is a poisoning ratio, etc., etc. And for the second step, then it means given this like difference of model closeness, we'll be able to like after the smoothing, we'll be able to characterize the difference between the top one and the top two of the smoothed output, so that we can leverage Neyman-Pearson lemma to prove the consistency of the final prediction. So with this, we can see, given this process, we'll be able to represent this constraint we see before, although it looks like complicated, but actually it's very intuitive as we mentioned before, and everything have this clear physical meaning. So we can see here, if we slightly reformulate this thing, it shows that the prediction will always be consistent as long as the RD represents the delta, which is the backdoor trigger, meaning the backdoor trigger is bounded by this whole variable. And this variable is actually very meaningful in terms of three levels: the feature level, which is the size of the backdoor triggers; sample level, which is how large is the poisoning ratio for each agent; and the agent level, which is how many adversarial agents there are in the training process. And then we can see here different variable here, like a Q divided by N represents the poisoning ratio of the agent. So if the poisoning ratio is larger, then the smaller the like backdoor trigger we can tolerate, which makes intuitive sense. And the second is the adversarial agent, number of adversarial agent. Similarly, the larger, the smaller of the trigger size we can tolerate. And here is a clipping norm divided by the noise level, which means if you have smaller sensitivity, then you can tolerate smaller amount of backdoor noise. Otherwise, you can achieve like tolerant larger backdoor. So this gives us intuitive understanding of how we can like improve our robustness based on this like different parameter choosing, so that we can see there are other variables. I will not go to more details, but we can see this give a practical guidance. Say if you want to train a robust federated learning framework, how those parameters should set based on this like bounded perturbation. You can see which one is like positive and negatively affecting the robustness, so that you can train the parameters in certain directions. So next, let's quickly look at some experiment to verify our analysis. So basically, we can see here with the noise level theta and rho. Here, first, let's look at the model smoothness. So here, different lines show different levels of noise. And the higher noise level is, the smoother the model will be. And then we can see indeed with higher smoothing noise, meaning the model is more smooth. And then the larger certification rate it can achieve, like from the x-axis, showing, like validating the result from our bound here. And second of all, let's look at the poisoning ratio. So here, very interesting, we can see with like the higher poisoning ratio, the smaller certification backdoor radius we can achieve. And also there are number of adversarial agent like scalars. The higher the scalar is, which means the attacker is more powerful by injecting the backdoors, then the smaller like the backdoors certification we can achieve. Similarly, we can look at the number of adversarial agents. So the larger the number of agents it is, empirically we observe that indeed the certified radius is smaller, showing the validation of our analysis. And next, more interestingly, we may wonder what's the impact of different training protocols like vanilla fed average and the robust aggregation approach. So here, surprising or not surprising, we can see that indeed, if you improve the robustness of the training protocol from comparison of these two sides of the figures, you can see from the x-axis, if we can leverage some robust aggregations, the certified radius is significantly improved, meaning that indeed we can, from the observation, like certification, which provides a lower bound of the performance of the robustness of the model, we can see that indeed the robustness aggregation contribute a lot in addition to their empirical performance. And we show that the tightness of this analysis, which can reflect the different aggregation protocols. So with that, I think I'm almost out of time, but let me quickly show an interesting framework that we provide so that we can provide for training the different federated learning agent flexibly, which I think will be helpful for the general audience. So here we can see, based on the certified robustness we have seen, we know there are lots of parameters and uncertainties that we can choose to train a federated learning framework. For instance, the smoothing parameter, clipping, frameworks, and algorithms, like vertical, horizontal, all kinds of like settings, etc., etc. So it's very hard to like change every component when we change a little bit for our requirement for the setting. So here we provide a unified federated learning framework by providing like 4 components. One is based on the data set and the tasks input. We can provide a federated learning framework recommendation. And then based on that, we'll provide a configuration UI so that people can specify different requirements of it, and then it will automatically generate a configuration file, which you can download to train on your local machines or directly train on our provided cloud servers. And then you will have be able to have different distributed training frameworks, and finally have unified logging systems to show the different results of the selected configuration you have, and automatically provide a leaderboard by comparing with standard FL configuration choice, so that you can know for the configuration you have, how good or how bad it is, etc. So as a quick overview, you can go to the website. Later I will send the link, and you can see, for instance, if we say choose encryption framework and the algorithm. We want to have MPC to provide privacy guarantees, and then we can select the data set. It will automatically give you some recommendations of the model configuration, and we can choose different loss function, optimizer, etc., and then it will automatically generate the configuration file for you to run your preferred federated learning framework, which I think is very useful for general FL applications. So in the end, I want to provide more platforms that we have provided to provide certification for, say, certified robustness of any deep neural networks against the testing time, perturbations with bounded adversaries, and the certification for different reinforcement learning, NLP tasks, like the unified federated learning. This is a link we mentioned before, and the Gemini Cricket, which aims to provide the AI ethics analysis verification, and the autonomous driving, including single autonomous vehicles and V2X networks to provide the safety analysis for it, so that you can deploy your safety critical scenarios and the autonomous vehicle algorithms easily on the platform to test the trustworthiness of it. So in general, I think this is the frameworks we provided, and they can help to accelerate the algorithms and analysis you have. So welcome to use the platform here. With that, thank you everyone. That's my talk. Sorry for go over like 1 minute. So happy to take questions.
Okay, all right. Let's just thank Dr. Lee for the presentation. Thank you. Any question from the audience? Yes, please.
Hi, can you comment on the trade-off between robustness and accuracy for the certified robustness framework that you described?
Oh, you mean the trade-off, right?
Yes, the trade-off between robustness and accuracy.
I see. Yeah, that's a very good question. So there are some results. For example, here the x-axis shows the certification radius. So when the radius is 0, it's a benign accuracy, meaning we don't consider any adversaries, and then later on consider adversary. So basically, we can see the drop of the line, which represents the trade-off between the benign accuracy and the robustness. And then I want to say, here, considering this point and the later point, there is a trade-off, but it's not that obvious. And the different algorithms, say vanilla fed average and the robust aggregation, also have different types of slightly different types of trade-offs. So that means with any robust training approaches, it will hurt the benign accuracy a bit. And in order to provide certification, which means during training, remember we need to clip the model and add noise, that will hurt the benign accuracy a little bit. But eventually during the impure evaluation, we find the trade-off is not that obvious, which is good. But the certified radius have some bounds. It cannot certify arbitrarily large radius of the perturbations. Yeah, thank you.
Okay. Do you have another question?
Yeah, I have one more question. You talked about the link between differential privacy and certified robustness. I can see that you're using the same tools in terms of clipping the gradients and adding perturbation to the gradients. But the threat model is very different, right? So in the case of differential privacy, this clipping and perturbation is done by the client, whereas in this case, this has to be done by the server in order to achieve the certified robustness.
Yeah,
Is
yeah,
that
that's a very
understanding correct?
good question. Yeah, go ahead, sorry.
Yeah, I mean, I just want to understand if my understanding is correct here.
Yeah, you are absolutely correct. I don't have my slides here. So you are absolutely correct. So indeed here, that's a very good point. So basically here, the server will clip and perturb the models and then send it. But in the other case, for the relationship between robustness and privacy, the agent will do the clipping and perturbation. So in that case, the assumption for the threat model is that the agent will follow some standard software like on their side. So they will directly run the software so that the software will give automatic help to do the clipping and the privation. And then with that, the model, the server side will again do a round of smoothing for the sended model so that you will have the satisfy the differential privacy as well as the robustness in the meantime. So I'm not sure if that answers the question, but I can give a very quick. Yeah.
Okay. Yeah, are there any other questions?
Yeah, so here is what you said. So basically here the agent need to clip and perturb, and then the server need to do similar thing. But then in this way, because the server agent already clipped it, and then the server have like smaller amount of things need to do, and then you still do the parameter smoothing, and then eventually you can get the bound. For example, the model robustness is a function of epsilon and the delta and the things. Yeah, that's a high level idea, but I can send you the paper later as well if you're interested. Thank you.
Okay. Any other questions? So we do have some online attendees. So if you have any questions, feel free to ask. Okay, if not, I have one question. So can you please go to the last couple of slides? You show these UniFed, the framework. So can you tell a little bit more? I didn't quite get this UniFed framework. So you mentioned this can be like take all the existing federal learning framework and do the like robustness benchmark. Can you please explain a little more?
Yeah. So let me see if I have an open here. Yeah, this is the thing. So basically the idea is that this is like the you can see my screen, right? So this is if you go to UniFed, so we have integrated like 10 open source federal learning frameworks, and then the idea is that we can automatically like call them and use it. For example, here we have different functionalities. If you click here, it will give you leaderboard for different framework under the standard use cases. And here is a UI recommendation for I will tell you what I want vertical, like I want to use deep like a DPSGD and tree-based model, whatever. It will give you recommendation of what framework you should use. And then here is the UI generation. This is the first step for giving the the recommendation and analysis of framework. And then in the UI, that's where you ask. So assume I want to like say train a fat tree, and then I want to choose algorithm like this. Then I have some standards say dataset I can choose, and I can also upload my own. For example, I can choose MNIST. Then there is some default settings we should choose, and then there are also other settings you can specify like the learning rate 0.5 and other things, and then what types of models you can choose, etc. And then you can request a standard evaluation. It will give you evaluation, or you can download the configuration so that this is a whole JSON configuration, so you can just run on your own server with the configuration for a federal learning framework. You don't need to configure all these things. And you can call any frameworks. Here is in total 10 open source frameworks. So that's the idea, so that you can easily run and then test and compare with other algorithm frameworks, etc. Yeah.
I see. Okay. Yeah, I think that's great. So the first the step you showed, like selecting the right or recommend the right model or framework. How is it user specified, or this UniFed framework will give us the choice to give us the recommendation?
Yeah, the UniFed will give us a recommendation. For example, I know some property. Yeah, go ahead. Sorry.
So what's the criteria, like the recommendation is based on, like how based on the performance, or
Yes.
what the criteria?
Yeah. The criteria is mainly based on the performance that we generated based on the leaderboard, because the leaderboard including the performance, including like accuracy and system performance like overhead, memory, runtime, etc. And therefore, based on this decision tree, actually give a kind of large recommendation for like which have what properties, like some algorithm only support horizontal, some only vertical or something, that basically different layers of the criteria, and then after choose it, eventually it gets the recommendation based on multiple criteria.
Okay. Okay, cool.
Mm-hmm.
So what kind of performance metric? So it's just general like accuracy, and also is there, because you're talking about the robustness, right? So is there any other metrics?
Yeah,
you have
so
the proposed metrics accuracy. What about the others? Like you have the robustness as well, other metrics?
yeah, we have privacy, but not exactly robustness metric point yet. Yeah, because the attack, it has a lot of variation. So this is more standard like performance and system performance, like the runtime, memory, etc.
Okay.
Yeah,
Okay.
robustness is the next step to integrate. Like we didn't integrate the certified robustness here, but that's another layer of things as a future work.
Yeah.
Yes.
Yeah. Okay. Yeah. Very cool. So I think so. This is available, right? Already.
Yes, this is just this link, unified
Okay.
benchmark.
Okay. Yeah, we'll definitely check it out. Okay. So are there any other questions? Okay. If not, I thank Dr. Lee again for the very informative talk. Thank you so much for your time. Right. Appreciate it.
Thank you.
Right. Thank you. Right. Okay, all right. So I think we will come to the end of all the keynote talk. So I think from 3:30, we'll have the oral sessions. We'll have 6 papers, except papers for oral presentation. So please feel free to grab some coffee or drink. So we'll come back at 3:30. Okay, all right. Thank you.
Okay, Deng, are you going to present for the OpenFed paper?
Okay, let me share my screen.
Yeah, I think we can maybe wait 1 more minute. So just want to test if everything's fine.
Okay.
Yeah, I think we can see the screen. We just wait maybe 1 more minute.
Okay.
Okay, I think we can get started. Please go ahead. Thank you.
Okay. Good afternoon, everyone. My name is Deng Chen, and I'm honored to be presenting our research at this workshop. In this presentation, we will briefly introduce OpenFed, a comprehensive and versatile open source federated learning framework. Recent developments in artificial intelligence techniques have enabled their successful applications across a spectrum of commercial and industrial settings. However, these techniques require large volumes of data to be aggregated in a centralized manner, fostering their applicability to scenarios wherein the data is sensitive or the cost of data transmission is prohibitive. Federated learning elevates these problems by decentralizing model training, thereby removing the need for data transfer and aggregation. To advance the adoption of federated learning, more research and development need to be conducted to address the important open questions. In this work, we propose OpenFed, an open source software framework for end-to-end federated learning. OpenFed reduces the barrier to entry for both researchers and downstream users of federated learning by the target removal of existing pain points. For researchers, OpenFed provides a framework wherein new methods can be easily implemented and fairly evaluated against an extensive field of benchmarks. For downstream users, OpenFed allows federated learning to be plugged and play within different subject matter contexts, removing the need for deep expertise in federated learning. For both academic and industrial applications of federated learning, it's essential that the software framework used is versatile and flexible. There already exist several influential federated learning frameworks, each with its own focus. However, these frameworks have left some challenges unmet. OpenFed provides an expandable toolkit for federated algorithm development across diverse topologies. The main contributions of the OpenFed framework are listed as below. The first, diverse topologies. OpenFed provides powerful automatic topology analysis and construction tools. By introducing the concept of a federated group, we are able to decompose an entire federated learning topology into its automatic units. Normal federated learning algorithms for split, vertical, hierarchical, or decentralized topologies can then be implemented as the standard centralized topology. In addition, OpenFed provides an interface for auxiliaries information to be exchanged across computer nodes. Second, comprehensive and standardized federated learning algorithms and benchmarks. OpenFed provides standardized dataset algorithms and benchmarks. Researchers proposing novel algorithm designs can conveniently and comprehensively compare their new ideas against the existing solutions. OpenFed also provides rich configuration possibilities. For example, server or client optimizer, simpering structure of partial activities clients, non-IID distribution of data partition, allowing researchers to better validate how well different algorithms generalize to specific situations. And the third, user-friendly API design. Mainstream deep learning frameworks such as PyTorch and TensorFlow, like ready-made APIs for federated learning. OpenFed carefully inherits the API design from the PyTorch library, which is commonly used by the deep learning community. This reduces the barrier to entry for the large deep learning community to participate in federated learning research and development. Furthermore, OpenFed provides rich built-in features including weighted gradient descent, federated averaging, diverse data augmentation, local area stopping, etc. These federated learning modules offers an immersive development experience to OpenFed users. The last one, third-party library support. The relative maturity of deep learning has resulted in the rise and the success of open source secondary libraries. These libraries provide state-of-the-art implementations for their respective domain areas. For example, Hugging Face for natural language processing, MONAI for medical analysis, and MMSV for computer vision. However, few of these support federated learning natively. Furthermore, because these libraries are increasingly widely adopted, it's unlikely for newly proposed libraries that offer only federated learning as an advantage to gain much traction. Therefore, OpenFed is designed to be plug and play, compatible with these third-party libraries. As for the future works, as federated learning continues to gain traction, we anticipate that new features will become necessary for OpenFed to continue to meet the requirements of academia and the industry. First, topology benchmarks. At present, all benchmarks default to be centralized topology for algorithm evaluation and low relevant large-scale experiments have been conducted on the impact of different topologies on federated learning performance. We will continue to promote this work as OpenFed matures. Second, industry deployment. OpenFed runs in a Python runtime environment, which makes it a challenge for deployment on resource-constrained devices. Therefore, more efficient runtime environments such as C and C++ must be supported. Furthermore, we will continuously increase the number of third-party libraries that OpenFed supports. Third, cryptography. Although there are many major symmetric or asymmetric encryption algorithms in the communication field, these algorithms are often too complex to encrypt large amount of data and consume too much computation. An open problem is therefore to design an effective encryption algorithm under the condition of limited computing resources according to the characteristic of federated learning. The last one, poisoning and adversarial attacks. The data used for training in federated learning often involves personal and private information. There has been research work demonstrating vulnerabilities in federated learning. For example, it has been shown that the content of training data can be inferred to some degree through the exposed gradients. OpenFed requires more defense mechanisms and algorithms to counteract these attacks. And last, we hope that our presentation will provide you with valuable insights into our research and we welcome any questions or feedbacks you may have. Thank you for your attention.
Okay, yeah, thank you for the presentation. Here I have some questions. Can you please bring up your slides? Because I think I have a couple of questions.
Okay.
Yeah, I cannot see the slides here. Okay.
Okay, let me find the approach.
Yeah, I think see the slides. Maybe you can have the presentation mode.
Okay.
Right. So
it
yeah,
okay?
yeah, it's visible. Can you go to the second slide, I believe?
List.
Oh no, the third one. Sorry.
Oh, this one.
Yeah. So is it already online now? Is the code already available so people can starting to using this framework?
Oh yes, this and I have yes, and the web you can screen this figure. You can scan this figure to get a website.
So what's the difference between this OpenFed and other like the open source like FedML, those kind of framework?
As I have described it, I think the most insight of OpenFed is to make third party library supports and user-friendly API design. So there are many federated learning frameworks existing, but we found most of them is hard to be widely used in different tasks in most population tasks such as image classification or natural language processing. They only most of them only design a framework limited in federated learning. We are trying to make OpenFed can be widely used by PyTorch, Lightning, or OpenMM Lab, so that they can only use OpenFed as a third-party library to make their code to do federated learning tasks.
Okay, so basically using that to call like API. If I want to do object detection, maybe I can go with OpenML Lab. For the medical, this Mona, right? So that's the that's the medical image database. Okay, the toolbox. Okay, all right. So yeah, thank you again for the presentation. Just to confirm, is there any other question?
I have a question.
Okay, yeah.
Can you go to slide 4?
Yes, this one.
Yeah, so it says here that FedML and yours are the only ones that that support decentralized federated learning. So yours it has good support for the decentralized case. Are there any special considerations when trying to apply a decentralized topology to your federated network?
Yes, yes. As for different topology, federated learning, we have designed a 3-level framework on this image. Actually, as for various topology graph, we will take it into many federated groups. This federated groups is focused on individual devices, and as for each individual devices, we could find that a centralized federated learning scheme can be applied. For example, we can go into this hierarchical topology. For example, As for the in the first row, as for the first devices on this point, we can find that it's only necessary communicate with its far point, like this blue one. And as for the blue one, it's only communicates with his two child as a far point. And this one is also the same. This one is also the same. Yes. In a word, in OpenFET, we will decompose the complicated topography topology graph into a group of federated groups, and within these groups, all the devices can be recognized as a centralized one.
All right, thanks.
Okay, thank you. So I think we have to move on to the next presentation. So the paper is Federated Learning in non-ID settings, aided by differentially private synthetic data. Okay, Deng, maybe you can stop sharing. So I'll go to the next one.
Okay.
Hi everyone, my name is Huan Chen. I'm from the University of Texas at Austin. Today, I'm going to talk about our work on using the differentially private synthetic data to improve federated learning in non-ID settings. Federated learning is a privacy perceiving framework that enables numerous distributed devices to collaboratively train a global model without exchanging their private data. In practice, however, it's unrealistic to expect the data across the device is identical distributed because the user's property, preference and the behavior may be very different. And training on non-ID data has detrimental effects on the performance of the global model. To illustrate how running fat average on non-ID data may lead to objective drift problem, we use a two-climb system as an example. Let's say climb 1 has data that contains only the images of cat and dog, and climb 2 has the data that's only contain the images of birds and fish. As a result, the local optimal model of climb 1, the X1 star, is distance from the X2 star. Nevertheless, the servers deploys fat average still from the global model by the averaging the local models. Therefore, the global model converged toward the average of the two local optimal models, X stars, instead of the true global optimal model, Y stars. In non-ID scenarios, the points in each climb's dataset predominantly belongs to a subset of class labels. For convenience, we refer the dynamic classes labels as abandoned classes. Clearly, the other classes are relatedly underrepresented. We say such classes are scarce classes. Essentially, the objective drift problem is caused by overfitting the local models due to the class imbalance. And such a drift could be avoided if possible to augment a client's scarce classes. In our work, we utilize VAEs to synthesize the artificial data based on the class-wise data representation extract from other clients' abandoned classes. Our methods consist of two stages, preliminary training and secondary training. The purpose of the preliminary training is to train a global decoder, which will be later used to generate data for augmentation. To be specific, each client uses their local private data to train their VAE models, consisting of an encoder, a classifier, and a decoder. The objective function in the local training consists of a cost entropy loss and a standard VAE loss. Following the training, each client only uploads the parameters of encoders and classifier to the servers for aggregation, while the local decoders remains on the device. At the end of the preliminary training, all clients upload the local decoders to the servers. The servers aggregates them into the global decoders and broadcast it to all the clients for data augmentation. The secondary training involves several steps. The first one is differential private means sharing, as illustrates in the figures here. During this step, each client computes the class-wide data representation, means over the data points in a set of abandoned classes. For each data representation, we generate the samples from a zero-mean Gaussian distribution with a variant sigma f squared and add it to the original representation. And then the client utilizes the global decoders to reconstruct the images to the XIC and forward it to the local encoder and classifier. If the predictions of the classifier is correct, then the clients add the tilde ZIC to the proof and repeat the procedures until the numbers of the noise preserved data presentation in the proof, which in the predetermined folder alpha. Finally, the client I will send all the data representation in the proof to the server. Before proceeding to the next step, I would like to briefly discuss the motivation for adding noise to the data representation. Share the means of the data representation rather than individual representation is a step forward promoting privacy. The hope here is that the individual features are hidden by the average operation. However, if an adversary captures the means of data representation compute on two adjacent data sets, the adversary would be able to infer the data representation of the single data point. Therefore, to further promote the privacy, we apply the differential privacy mechanism. Here is a quick reminders of the definition of differential privacy. For a randomized mechanism M, if the max divergence of the two output distribution given to adjacent data set D and D point is bounded by epsilon with the confidence 1 minus delta, then we say that the mechanism M satisfies epsilon delta differential privacy. For any deterministic function F, the Gaussian noise mechanisms can enhance F achieving epsilon delta differential privacy by adding the zero-bin noise. The variance of the Gaussian noise determines the values of epsilon if we fix delta. In our case, the deterministic function F is average operation. The sensitivity is 1 over NIC, where NIC is the numbers of the samples with label C in client I's local datasets. For NIC equals to 100, sigma set to 4, delta set to 0.01, we can obtain epsilon equals to 0.5. Therefore, we with 99% confident that the means of the data representation computed on two adjacent data sets would differ by less than 0.5, which made them indistinguishable. The following three figures illustrate the artificial images generated by the VAEs on fashion MNIST, Cipher 10, and 100. Even though the synthetic images appears incomprehensible, they carry sufficient information to help improve the training process. Go back to the training procedures. After collecting noise preserved data representation from the clients and as well as the site information about the abundance and scarce classes, the servers provides the helpful the servers pair up the clients by designating the one clients appear of receiving clients and the sending clients. Step 3 of the training stage deal with the images synthesis. In particular, after the clients have been matched, the servers provides the helpful class-wide data representation to clients in needs of the information. The receiving clients utilize the global decoders to generate some data and include them into the original local dataset. After that, all the clients are allowed to deliver all the parameters of the local and the global decoders to free the memory. And in the following training, the clients utilize the argument local data set to train the local model. In experiments, we compare our methods with the 4 previous proposed algorithms on the 3 data set. We follow the strategy that using the deleterious distribution with different concentration parameters to generate the data partitions. The visualizations of the data partitions with beta 0.5 across 10 clients and 50 clients are shown in the figure. We run extensive experiments on the 3 data set with 5 different concentration parameters, betas from 0.1 to 0.5, and they're controlling the heterogeneity of the data partitions. As shown in the 3 figures, our method outperforms the baseline in all the settings. The ratio of the preliminary to secondary training runs influence the performance of our methods and its computational cost. For each experiment, we explore 3 different settings with 15, 20, and 25 preliminary training runs out of the total 50. As shown in the figures, the test accuracy dramatically increased after the data augmentation. Note that we do not need the generator to generate high quality images. The synthetic images only occupies a small fractions on the augment data sets, essentially acting as regularizers in the secondary training. To conclude, DPMS enable data augmentation in non-IID federated learning by sharing class-wise data representation. Data augmentation effectively improves performance of non-IID federated learning with only a minor additional competition and memory overhead. To promote privacy, we rely on differential privacy concept, and as a part of the future work, we will investigate settings in which the privacy concern may require further privacy protection mechanism. Thank you for your attention. I would like to answer any questions.
Okay, questions? What about online attendees? Do you have any questions? Okay, so can you please go to the slide where you show the reconstruct images, like the CVPR 10, 100? Yeah, I was curious, or I see this FMNest database. Does that show somehow the appearance of the original data?
Yes, because the fraction MNIST is the latent space is relatively simple and it's easy to extract. I mean the latent space, the data representation for one classes are almost the same. So so we compute the means of the data representations for one class, and you can generate a very good quality images.
Yeah, but will this cause some privacy concerns because, you know, these reconstructed images the synthetic image may looks very close to the original one?
In this case, maybe we can adjust the hyperparameters. If we need higher privacy protection level, we can have a higher sigma is related to the variance of the Gaussian noise. But maybe we will affect the performance of the models. It's a trade-off between the privacy and the performance.
Yeah. So yeah, definitely. So I think if you have more level of privacy, then I think the performance will suffer. So yeah, but I think it's 10, 100 may be okay. By the way, what about the communication overhead? Because you have the encoder, you have the decoder. When you see those like 2 parts of the network, I was kind of curious, like, will that cause like communication overhead?
Yes,
or more communication cost?
Okay, I can answer this question. So that's why in the preliminary training, in the local training, we train the VAE, but we only upload the parameters of encoders, and the classifier is half of the VAE during the training. but we only transmit the full VAE models at the last round of the preliminary training. So if we have totally if we have 1,000 rounds totally, but we only transmit the VAE like double communication bandwidth for one shop, and in average, I don't think the overhead should be very high.
Okay. And another final question is, you mentioned the synthetic data is just a small fraction. Then what's the point have the small portion of the data to mitigate the non-IDness? Are you trying to analyze the label skew so that, let's say you have a long tail distribution of the data, then you purposely generate those more samples for those tail classes, or you just treating every class similarly? You just generate a set of augmented data.
So I mentioned the small fractions of the argument data set is related to alpha here. So how many synthetic images you want to include in your local data set? In our case, if you have a very small concentration parameters to generate the data predictions, basically all the claims they have some classes, they have 0 samples. So if you generate some sample, some class doesn't appears in this claims data set, even the number is not very much, but you still be meaningful to prevent the overfitting in the local training.
Mm-hmm.
And in our paper, we have tried different alpha here. We have tried different fractions of the generated images in the local data set. And in our experience, we can say that the fraction is small and the performance is the best with larger fraction of the generated images, because the quality of the images is not very good. So if the fraction of the generated images is high, the total local training will be very bad.
Okay. Okay.
And our motivation not to train the high quality images, because our task is image classification, is not image generation. This is a more complicated task. We don't want to solve a problem with a more complicated problem.
Yeah. Yeah. Okay. Okay, cool. All right. Thank you. Let's I'll have to move on to the next presentation. Yeah, thank you. So the next one is many task federated learning, a new problem setting and simple baseline. Any author for the many task federated learning, a new problem setting, a simple baseline here? Are we doing remote or in person? Okay. How about we just move on to the next? Mixed quantization enabled federated learning to tackle gradient inversion attack. Is the author here or online? Okay, cool. We cannot hear you.
Can you hear me now?
Yeah, yeah. Okay, great.
Okay. Hello, everyone. Welcome to my presentation. This is Pritam Roy Abhi, a PhD student from University of Maryland, Baltimore County, and working in the research domain of federated learning and data confidentiality in AI under the supervision of Dr. Arya Gangopadhyay. Now I am going to present my paper, Mixed Quantization Enabled Federated Learning to Tackle Gradient Inversion Attacks. So the centralized machine learning has privacy concerns and the risk of confidential data breach. To ensure the privacy and data confidentiality, federated learning was proposed by Google in 2017. It enables multiple parties to collaboratively train a model without sharing the data. So explicit data sharing is not necessary here. Only weight or gradient updates are shared. So basically, federated learning has been developed to protect the data confidentiality. However, gradient or weight sharing protocol as part of the training process can potentially reveal sensitive information to the third party or to the adversaries. And these attacks are performed in such a covert way that it doesn't hamper the training performance, but the attackers can backtrack from the gradients and get information about the sensitive raw data. And such kind of attacks can completely reconstruct the training data and associated labels from the gradients. So in this slide, we illustrated the gradient inversion attacks on 3 different data sets by extracting the training samples from the gradient. Here, the ground truth samples and the extracted samples are marked with blue and red bounding boxes, and you can see that the reconstructed samples within only 100 iterations reveals the ground truth training data. So in recent time, gradient inversion attacks have been investigated intensively, and based on the process of data extraction, these attacks are of 2 types. One is recursion-based attacks. RGAP, COPA, these are the name of the attack methods of such type. And second one is iteration-based attacks. It is actually efficient and mostly popular. DLG, IDLG, grade inversion, these are the name of the attack methods of such type. Now I'm going to describe the data extraction process of gradient inversion attacks. In federated learning, private gradients are transmitted to the server. So the attacker may intercept the communication channel and get access to the private gradient. After that, the attacker initializes the dummy sample, and dummy samples are fed through the same network to get the dummy gradient. And finally, minimize the distance between the private gradients and dummy gradient. During this loss minimization, once the loss is minimized, the dummy sample reveals the ground truth training samples. And based on the loss minimization strategy, several attack methods are proposed, like some of them consider L2 distance, whereas others consider cosine similarity to minimize the loss. And different attack methods use different regularization terms to make the process efficient and to extract better quality data. Now I will mention some of the existing defense strategies against the attack as well as their limitation in FL context. One is differential privacy. Actually, DP ensures defense with theoretical guarantee while compromising some accuracy. But implementation of differential privacy in federated learning setup is quite challenging. Like DP is effective when each worker has access to a large training dataset. But the federated learning setup cannot guarantee large training dataset for every worker. In addition, DP requires carefully privacy parameter selection based on the total number of workers, total number of training rounds, and total number of instances to add the optimal amount of noise. But number of the workers and number of the training instances can vary every round in the entire training process. And second one is the gradient pruning. Actually, pruning removes the neuron that is least significant. But in the initial training round, the model cannot determine which neurons are significant and which are not. So pruning the network from the first epoch of training is not recommended and may result in poor training performance. So now the question is, how can we secure the gradients of private data and prevent the adversaries to exploit it? To answer this question, we thought of a new use case of scalar quantization to tackle gradient inversion attacks. In quantization, gradient values are transitioned into less precise form according to our choice of bit size. And because of this transformation, quantized gradients are no more directly correlated with the raw training data, and that prevent the adversaries to exploit it. Like in our experiment, we implemented all the recursion-based and iteration-based attack methods on multiple datasets and demonstrated the capability of quantization. That means the quantized gradients in tackling the attacks. We can see in this slide that training images are not reconstructed even after 500 iteration of distance minimization with DLG and INF-grade attack methods, whereas the same training samples are reconstructed within only 50 to 60 iterations when gradients are not quantized. In a similar vein, we depicted the reconstruction of batch data with CPL and grade inversion attacks. And from the right side figure, it is observed that not even a single sample from the batch is extracted by these attack methods when gradients are quantized. And similar result is also found for R-gap recursion-based attack method as well. So, since the quantized gradients are capable of defending the attack, we integrated the scalar quantization in federated learning framework and proposed quantization-enabled FL scheme. So according to the framework, after each round of local training, worker nodes will first quantize the gradient, then transmit. And after the transmission, the server will aggregate the quantized gradient, update the global model, and send back to the clients again. And after receiving the updated model from the server, each worker will apply scalar dequantization to get back to the gradients in the prior format and starts local training. So we integrated the scalar dequantization so that the local training cannot be impacted by quantized gradient. And according to our framework, both the scalar quantization and scalar dequantization, both is performed in the worker side. And that's why the only worker node will know the parameter for quantization and dequantization. So our designed scalar quantization and dequantization depends on 3 tuning parameters: quantization mode, rounding mechanism, and minimum and maximum range information. So the set of parameters that are used for quantization must be identical for dequantization as well. Otherwise, the dequantized gradient will have a significant mismatch with the real gradients. And we proposed mixed quantization over single bit quantization because the mixed quantization ensures higher security against a brute force attack methods where an attacker intends to dequantize the gradient by trying all combination of tuning parameters. In mixed quantization, the choice of quantization bits and quantization parameters for each layer of the model is not uniform. And that means it induces a n to the power L overhead on the worker side, where n is the number of quantization parameter and L is the number of layers in deep learning model. So this n to the power L, this number is exponentially high. That makes the dequantization process and ultimately the data extraction process more arduous for them. Here we experimented with the baseline defense strategy. So differential privacy injects Gaussian or Laplacian noise to the gradient. So we separately apply Gaussian and Laplacian noise to develop 2 DP baseline. And to find out the optimal noise that can prevent the attack, we added Gaussian and Laplacian noise ranging from low magnitude to high magnitude. And results depicted that for both DP Gaussian and DP Laplacian, noise with variance level of 10 to the power minus 1 is the minimum required noise that can completely prevent the data extraction. Next, we apply another baseline defense, gradient pruning. And from the figure, it is observed that pruning in the range of less than 30% cannot defend the attacks. But when 30% pruning is applied on the gradient, the attack is prevented for CVPR images. But it requires more pruning, like around 60% pruning ratio, to defend the attack in retrieving the fashion MNIST training samples. So we cannot determine a fixed pruning ratio that can prevent the attack. That ratio actually varies dataset to dataset based on the data complexity. Now, finally, we evaluated the performance of our proposed approach and baseline defense approaches in federated setup. And in the table, the BaseFL is the basic federated learning framework without any defense strategy. And our proposed approach achieved almost same level of performance of BaseFL, only 0.5% drop for amnesty and fashion amnesty dataset and 1% for the CVPR dataset. And the reason is, since the quantization and dequantization is not 100% fully reversible process, and this caused this slight decrease in performance. But still, our proposed approach outperforms the DP Gaussian by 13% on average and DP Laplacian by 20% on average. And along with the traits of attack resiliency, our proposed approach is capable of less transmission bandwidth and less transmission cost because of the quantized gradients are shared in our network from server to client. So in conclusion, in this work, we proposed a defense strategy against gradient inversion attacks in FL context, and our approach outperforms the baseline defense strategies and offered less communication bandwidth uses. And our next step is successfully applying our defense approach on other modalities like NLP or audio domain to claim it a universal one. So these are the references, and this research is supported by US Army and NSF grant. Yeah, thank you.
Okay, thank you, Pritam. Let's see if we have any questions in the audience. Yeah, please go ahead.
Hi, thank you. I think you may have already answered this, but can you say how you chose the variance scale for your method? Like, how do you know which scale that you can prevent against, say, a membership attack? Because you're comparing against these DP methods. So the DP methods depend on a privacy parameter to ensure a certain guarantee. So how do you know that, you know, the noise scale you're operating at is comparable to these other methods? Because of course, you can always just change these parameters to increase performance. So do you have any comparison about how vulnerable your method is compared to those other methods you're benchmarking against? Yeah, thank you.
Actually, the way we select the parameters for differential privacy, it is based on the number of workers or number of instances, right? But gradient inversion attacks can be done on single image as well. So whenever there is single images, like or single training samples, we try to add DP Gaussian and DP Laplacian from low magnitude to high magnitude. This is the, can you see this graph? So you can see that we tested with the low magnitude to high magnitude and found out that like here, the attack is successful. In this case, attack is still successful. Here, attack is successful as well. So whenever we, like this way, we have counted the exact amount of noise that can prevent the attack for a training samples. And this way we have determined the level of variance which is required to prevent the attack.
Yes, I see. Thank you. That answers it. I think I remembered it was in the talk. I just wanted to see precisely again how you picked it. Thank you.
Okay. Yeah. Thank you for your question.
Okay. I have one question. You in the last you mentioned you also have the benefit of communication efficiency, right? So are you comparing with non-quantization or like a single bit quantization, not the mixed quantization? Yeah,
actually,
the less transmission bandwidth. Yeah. Are you what is you comparing against?
Okay, actually, our main contribution is how can we defend the attack? And
yeah, I mean,
in terms of so it is, we compare it with the like full precision gradient. Like in generally, the gradients values are in float 32. So if we make 8-bit quantization, so it will be more times faster and more, it will require 4 times less communication bandwidth. That's what I want to mention.
Yeah, I see. So you are just comparing to the full precision, right?
Full precision, yeah, right, you are right.
What about the baseline? Let's say you are not using the mixed you are not using mixed bit, like a single bit, like 8-bit or 16, 4-bit. I mean, the performance of your mixed quantization will be better, but what about the communication, right? Because you're doing mixed quantization for different layers, right? So
Yes.
overall, like, do you also have the benefit of communication, more communication efficient?
For say, if we use a combination of 8-bit and 16-bit quantization, right? So obviously it will require less bandwidth than the full precision gradient. Like it depends on what quantization bit you are choosing. Like in mixed precision quantization, I can choose a sets of quantization bit. For say 8-bit quantization for few layers, 16-bit quantization for few layers, or 4-bit quantization for some of the layers, right? So still, it will be much faster and efficient than the float 32.
Yeah, that I understand. I'm just saying compare with 8-bit, not the full precision, right? You said a single bit quantization, right? I can choose 8-bit quantization for all the layer, but here you are just have a mixed, right? Yeah, but I think I get the answer. So yeah, it's kind of depend on which kind of bit resolution you are choosing, right?
Yeah,
and you may get benefit in terms of the communication efficiency. Yeah.
Yes.
Okay. All right. Thank you so much for the presentation. We'll move on to the next one. So
yeah, thank you.
Yeah, thank you. Is the many task better learning authors here? Okay, still not here. Then let's go to the asynchronous federated continuous learning. Okay, I do it in person. Okay, so see, did you share
the number 12?
12? Okay, all right, great.
Just kidding. Okay, so hello everyone, I'm Don Shanai from the University of Padua, and today presenting our work titled Asynchronous Federated Continuous Learning. So continuous learning is a learning paradigm where we learn new tasks over time, and the objective is to avoid forgetting previously acquired knowledge. It is of particular interest in some real-world federated learning settings, because users generate new data regularly, but applying directly continuous learning to federated means to have a line sequence of learning steps across different clients, and it is not realistic and also not privacy preserving. Therefore, we propose this setting, asynchronous federated continuous learning, where each client follows his own continuous learning path asynchronously. In the picture, we notice in different color, different tasks, and we see that every client has his own task stream. To solve this task, we propose this federated learning system with prototype aggregation for continuous representation, which is divided in 3 steps. First step is server fractal pre-training. Then we have local training, which is guided by 3 losses. One is the standard supervised cross-entropy on the classes that we are currently experiencing in that client, for which we have the supervision. Then we have a prototype-based loss for the classes that we are trying to not forget, the classes coming from the other clients. And then we have the representation loss used to align the learning of new classes with the previous one. Finally, we have the server aggregation, which basically we did a simple modification in the standard federated averaging to work in this setting. So the first step is server fractal pre-training. We employ the fractal pre-training strategy, which was proposed in a centralized setting. And why we are doing pre-training in federated learning? Basically, it allows to improve performances for the downstream task. It speeds up training in federated learning, limits client drift, and allows for better feature space alignment. And why use fractals? Apart from the general appearance of the images, we use propose those because fractals are generated from EFS codes from the labels. Basically, we have perfect label accuracy at zero cost, no privacy issues, and we don't have examples of the classes to be learned. The first step is to compute local prototypes. At each round, every selected client computes prototypes for all the classes that he is experiencing, coupled with the radius. So each client computes this pair prototype radius and send it to the server for further processing. At this point, the server aggregates prototypes into global ones. When he doesn't have a previously computed prototypes, he basically applies a weighted average to compute the new one. Instead, when we have a previously learned prototype, we update it with a moving average. At this point, each client during local training can add noise to the previously learned prototypes and use it to remember to avoid catastrophic forgetting with this loss. The last loss term is the representation loss. This is used basically to perform a feature clustering, which is consistent across clients and time slots. Basically, we force the classes that we are learning to be consistent with the previous global prototype, if it's the same class, otherwise to be disentangled from the other classes. The final step of the algorithm is the server aggregation. We use this simple, after computing the average of the clients, we average with the previous global model, and this allows to have a stable aggregation that avoids client drift and forgetting of all the classes. To evaluate the performance of our algorithm, we propose 3 splits of CIFAR 100. CIFAR 100, we use 50, 100, and 500 clients, and we compare it with federated averaging and federated adaptation of a continual learning method which uses prototypes. We see a consistent improvement in every setting, and we did an ablation to validate the performance of each part. And we see that when we have more client, we see a larger improvement, in particular for the pre-training part and for the aggregation. To conclude, we introduced this asynchronous federated continual learning setting, which is a setting for continual learning in federated learning, which is more realistic. Then we propose an algorithm which makes use of prototype-based representation loss, fractal pre-training, and a simple modified aggregation policy. And we provide 3 splits for the CIFAR 100 dataset, and we reached better results than competing methods adapted to this setting. So these are some contacts, and thank you for your attention. If you have any question, feel free. Thank you.
Any question? Yes.
Yeah.
So could you perhaps elaborate a bit how the asynchronous process works? Because it seems a very interesting process, but maybe I missed how exactly, like when you do the federated averaging.
Yeah.
At what point across these, like in this example, at what point do we do the federated averaging?
Okay, so here maybe asynchronous is a bit misleading because we mean it in the continual learning sense. So every client is asynchronous in the when he switches tasks, but the aggregation is let's say slotted in some time steps. So
I see.
We perform aggregation, classic aggregation synchronous, but every client might be in a different state, let's say. So it's similar to a very heterogeneous federated learning setting where clients change the task over time. It is a bit dynamic setting.
Yeah, so the domain shift is happening throughout the local training, but
yes,
the federated averaging is happening afterward at synchronous time. Sure. Thank you.
Okay.
I think you mentioned why you're using the fractal. Can you please explain
yeah.
like the motivation of the fractal?
Yeah. It is here, okay. Yeah, okay. So the idea was, apart from the fact that, yeah, I like fractal images, is the fact that if you use ImageNet, basically you are training on some classes that you are going to explore later. So that could be somehow cheating. Yeah. And in general, pre-training allows for to have a better feature space alignment. Then later on, we're going to use prototypes. So starting with model initialized in a good way allows us to make use of prototypes. And the fractals, but also other synthetic data set have perfect label accuracy. So
yeah, I think yeah, maybe that one reference is
yeah, this one is the approach that we used.
Yeah, I think there's also works they are using fractals like for training a model, then using that to do the fine-tuning, because I think as you mentioned, you can generate a lot of fractals with the
yeah, and you can generate them on the flight, so you don't have to store them in a
okay. Okay, there's a
yeah.
So for each local trainer, each client, there's a split sequence, which is different. The tasks are different between each client.
Yes.
Okay. So when you compute your prototypes, it's with respect to the classes that have already been seen by each client. So each client has different prototypes, or the prototypes are shared.
After each client computes his own prototypes, he sends them to the server.
Yeah.
The server computes some global prototypes and send them back to the clients. So clients have different prototypes after they complete their local training.
Okay, and
but
the
they
server,
have they also the starting point, so they use it to
the
drive
server
the apps.
aggregate the prototypes.
Yeah,
And
the server aggregates the prototypes and send them back to the client.
And that's a concatenation, or that's just an append to a list of prototypes that are already computed by the server?
There is a list.
Oh, okay.
But then you update also the prototypes of the classes that you have already learned.
Okay, thank you.
Okay, all right, thank you.
Okay, thank you.
Okay, I think so. I think the last one is timely FL, heterogeneity aware, asynchronous federal learning with adaptive partial training.
Hello, everyone. It's nice to see everyone online. My name is To Zhang. I'm a PhD student from University of Southern California. Today, I want to present and discuss how to do heterogeneity aware synchronous federated learning with adaptive partial training. The first problem that when we do federated learning, especially the machine learning system, is how to scale FL to millions of nodes. In the cross-device setup, when we're doing the federated IoT or edge device, there are so many devices right now. And the device is heterogeneity. That is what we would discuss for all day. We have the powerful laptop. We have the small Echo device. We have the iPhone. Their capacity or their hardware resources is different. So in the traditional way, we do the synchronous aggregation. That means we wait for all participants to finish, aggregate them, and then do the next round of local training. But it's impossible for large-scale deployments, especially when I have more than 1,000 devices. I cannot wait for the slowest one. I need to wait maybe 3 days or 4 days to have everything to be finished, because the status is different. Some device may be turned off because of their power issues. Some device maybe do not have any signal to upload their training, or some device even not capable of doing the whole training due to the limit of the hardware resources. And then last year, 2 years before, Meta team proposed a new asynchronous aggregation, the SOTA one called FedBuff or Papaya. That means that we set up an aggregation target with the buff size k, as long as we collect the size of the local update equal to k, and then we do the computation. That means that in every time we wait for the top k local client to finish it, and then as long as we get the k samples, we do the aggregation. The thing is that that we will always introduce the stale participants of the clients. Some clients maybe need 3 rounds for compared to the fastest one to catch up to the aggregation. That and when they upload their local updates, they will introduce the stale updates. And also, you can see the plot in here. There's still the unbalanced participants among clients. That means that the Papaya scheme is preferred to select the top fastest device to do the aggregation, but ignore the slowest one. As a result, the accuracy will drop because a large portion of devices cannot be selected to do the model updates during the training. And also, the staleness is the issue for the job of accuracy as well. To eliminate the staleness and to introduce more participants to do the training on time, we introduced the timely FL, a scalable, dynamic, and a synchronous design. Instead of only a fixed number of clients to join the global update in every round, now we allow more available clients to join the global update every round. How we do that? We do not let them to upload the full model updates, but we let them to upload the portion model updates according to their hardware, according to their computation or computation resources at that time. Specifically, the timely FL is adaptive and fair federated learning, a system design based on the partial model training and auto-tuning. For the slow devices, we let them to do the partial model training. For the fast device, we let them to do more epoch for training. As a result, we let everyone to finish the training on time, and then introduce more participants to join in the global aggregation in each round. As you can see in here, in each round, we first collect, the server will first estimate what is the current resources that everyone have, and then to set up a uniform reporting time. Based on this uniform reporting time and their local hardware resources, we give them the target to the training. For the fast device, as you show, shown on the left, we let them to do more epoch of training. For the slow device, as shown here, for example, on this 3-layer example, we only let them to do the last layer training for 1 epoch. As a result, everyone can finish the training at the same uniform time, and then there will not have the staleness problem happen. So the advantage of timely FL compared to the synchronized and the SOTA FedBuff is that the more clients join the global update on time, as we said, we eliminate the staleness. And also most of the clients increase the participation rate. The participation rate in here refers to the number of the aggregation participate divided by the total number of the aggregation rounds. That means how often you participate in the federated learning. When we combine these two advantages together, you can see that both convergence rate and accuracy boost up. The green line is the FedBuff, and the yellow line is our timely FM. So to evaluate our results, we do very detailed experiments on 3 data sets: the Cypher10, Google Speech, and Reddit. The Cypher10 is a traditional image classification. We partitioned the Cypher10 with the digital distribution alpha equal to 0.1 to simulate the actual non-IID. The Google Speech is speech recognition or the keyword spotting task. It is a naturally partitioned dataset with more than 2,000 speakers in here. And the Reddit is the NLP text for the next word prediction. It has more than 200K clients in here. For the Cipher 10, every round we sample like 10 clients. For Google Speech, we sample 10 clients as well. For the Reddit, every round we sample 100 clients. You can see that no matter what test we are doing, the timely FL get a higher accuracy and much better conversion speed compared to the FedBuff and the synchronized FL as well. So this is the detailed results that for the 3 data sets. On the accuracy part, we definitely do much better than the FedBuff. And also for the conversion speed, we do much faster than the synchronized FL and at least 2 times faster than the SOTA FedBuff. Also, we do some ablation study to better prove our advantage. As the data becomes more non-ID, actually the timely FL much outperforms the FedBuff. Also, we do experiment to show whether adaptive is the key to improve the accuracy or not. So on the blue line, we do not do any adaptive training. We just let the model to do the, we'll just let some clients do the partial training on fixed, do not do the dynamic training based on their real-time communication and computing resources. You can see that accuracy actually dropped a lot. That means that adaptive training really increased the performance. Adaptive is the key to improve the performance on the synchronized as well. Also, sorry, I did not mention it in the beginning. The model in here, the Cipher 10, we use the ResNet 18. Google Speech, we use VGG 11. And Reddit, we use Albert. People may wonder that the timely FL do not work well for the small models because all the past models actually have many layers. So to eliminate these kind of questions, we also try a lightweight model in here on the Google Speech. In here, you can see that we only have 4 layers for the model. And you can see that timely FL still do much better compared to the FedBuff and synchronized FL, especially on the conversion speed. That show that timely FL can do can prove his efficiency on both lightweight model and heavy model. That's it. Any question?
Okay, there's a question.
Yeah.
Hi, nice talk. So my question is about the aggregation method that you use when combining the local models that are trained in this way. So if one device does full training and does many epochs of training, whereas another device does partial training, how do you combine the resulting models in a consistent way? Because won't the global model be biased towards the device that does full training?
I don't think so. Actually, we do the layer-wise aggregation here. You can see the dot line here. Instead of, in the traditional federated learning, I will add all the model together and then do the average, something like that, right? But in here, I just do a layer-wise one. For example, on the layer 3, I will add this device A, B, C, D, and then I will add them together to aggregation divided by 4. For layer 2, I will add A, B, C, and then divided by 3. And for the last layer, I will add A and B and divided by 2. And also, I think I forgot to mention is for the layer-wise training, we always let the low resource devices to train the output side layer, because actually the output side layer is much significant for the training for the training results. Because think about it, if you have a ResNet, the beginning part of the model actually is the feature extractor, and the last one is the classification layer. And then the key of it is that, federated learning is more like preserving the data privacy. And then, but even though the data is different, the data distribution is different, the feature are normally the same. For example, on Cipher 10, everyone is the 32 by 32 image. The feature actually the same, but the most different is the data distribution. So the key is on the output side layer. So we add the low efficiency point at least to train the last output layer. And then we do this kind of layer-wise aggregation for the global model.
So even if you do layer-wise aggregation for one of those layers, let's say you have layer 1, and then there are 2 devices here. One device runs more training epochs for that layer, whereas another device does less training epochs. Don't you need to do some kind of normalization when aggregating?
Actually, I have a future work called inclusive FL, is actually in submission right now. We do a detailed theoretical analysis in here. The thing is that we found that we do a layer-wise cosine similarity score for all the layers that's in the under the FL setup. We found that, as I said before, the input side layer actually is really similar across all the devices, because the input side layer only extract the features. And then no matter how heterogeneity your data it is, the feature is actually the same. The output side layer actually differs very much during the aggregation. That's why we just use, that's why we let the low efficiency, low resources devices only train the outside layer.
Okay, thank you.
Yeah, thank you.
Okay, are there any other questions? Okay, if not, thank you for the presentation. So this is a really interesting work. Then I think, see, so is the many task federal learning author here? Shui, are you here?
Yeah, I'm here.
Oh, okay,
Sorry
okay.
for the inconvenience.
Yeah. So maybe you can share the screen and do the presentation.
Yes. Okay, can you see my screen?
Yeah.
Okay, great. Yeah, hi everyone. My name is Shui. Today I'm going to talk about our work, many-task federated learning, a new problem setting, and a simple baseline. This is joint work done by UT Austin and Cisco. So first, the motivation. The motivation here is for federated learning. Our intuition is traditional federated learning are usually leveraged in order to make full use of data created by edge devices. And the distribution of data owned by different edge devices are usually different, which is the key challenge of federated learning. While there are challenges, the federated fundamental intuition behind the introduction and success of federated learning is that we hope the more data we can use, the better model we are likely to obtain if we do it in a correct way. In other words, we can further boost the performance by syncing more data. However, here the challenge is not all data are labeled for the same task. And for example, the smartphone users might have text data for next word predictions, sentiment analysis, search prediction from history, and connected vehicles, for example, might have each performance, sense classification, lane detection, and so forth and so on. This motivates us to incorporate multitask learning with the federated learning so that we can relax the restriction or clients enable federated learning to unify more diverse data for training. And the second motivation is that similarly, we hope federated learning can also help multitask learning. The key and inherent challenge of multitask learning is cross-task conflicts, which means nearly training all tasks together in one model often degrades performance. And the backbone or drawback of multitask learning is that traditional multitask learning still training one model backbone with shared weights, where the conflicts of the different tasks are hard to disentangle. In contrast, with the scope of federated learning, the weights of different tasks are naturally disentangled, provides us a chance to do aggregation or do learning more flexibility to deal with the cross-task conflicts. So here, based on these two motivations, we propose a new problem setting. So as we can see from the figure, different local edge devices are able to collect data performing different tasks. Some devices will do semantic segmentation, while others will do estimation. So with our new framework, those highly diverse devices can still, we hope they can still collaboratively train a model. And despite the opportunity, there are new challenges. Traditional federated learning, we only need to care about data heterogeneity, which is caused by different data distribution. Here, task heterogeneity is also our main challenging. Each client may train a local model dedicated to its own tasks, which differs from others in the same network. In our work, we call it task heterogeneity. And a more challenging problem is that task heterogeneity and data heterogeneity could coexist with our framework, which makes it more complex. And to deal with the task heterogeneity and data heterogeneity simultaneously, we propose dynamic grouping to deal with this problem. Specifically, in each communication round after the cloud collecting all local feature updates, so as shown as the left box in the middle, we first compute the similarity score between each pair of clients. And then we choose top K for each client to select K friends of them. So each client only use the updates of their top K friends to perform their updates. And for each client, we will collect all his layers. We do it aggregation layer wisely to perform a layer voting and pick the top friends with the highest accumulated vote from all layers. And after identifying the most similar friends for each client, we adaptively aggregate weights with the same group. As we can see on the top figure, the segmentation with our results show that clients on segmentation tasks mainly will dynamically choose their friends who is also doing segmentation for aggregation. And here is our results. We to evaluate our method, we conduct two experiments. One is Pascal context 5, which means all clients have a subset of Pascal datasets, and each client specializes on one of the 5 tasks proposed in the Pascal context. And another one is Pascal context YUD 9. Here, by the way, the 5 means there are 5 tasks, and 9 means there are 9 tasks. And Pascal context YUD 9 means some clients has each client specializes on 9 tasks, including 5 tasks from Pascal and 4 tasks from NYUD. We compare our method with the 3 baselines. One is a single task federated learning, which means we train each client. Only clients of the same task are involved for federated learning, and the plain manual task ML means we directly extend fed average on multitask scenarios without considering task heterogeneity and data heterogeneity, which means we don't apply dynamic grouping. And another baseline is fed prox. We can, which is a more advanced federated learning approach to solve data heterogeneity. We can draw 2 interesting observations from the results. The first one is, despite the potential inference brought by task heterogeneity, directly extending single task federated learning in many task federated learning without any grouping technique can benefit training, which encodes the more data, the better model intuition. And the second observation is that after using dynamic grouping and adaptive aggregation, model can be free of interference and further benefits from more data. Yeah, that's all. That's our paper. Thank you. Any questions?
Okay, so do we have any questions for the presenter? Okay, I have a question. When you say group the friends, how do you define the friends? Are you just grouping them by the data modality, like all the task? Like you have the depth, edge, and the semantics, segmentation. Is that how you define them?
Yeah, thank you for your question. We by defining friends, we can actually calculate the cosine similarity of the client's weights updates. So we choose the top K clients which has highest cosine similarity with the current our target client, and then we use the top K clients to aggregate to get our aggregation.
So does that mean those clients can perform different tasks? Because you're doing this based on the cosine similarity of the is a gradient, the cosine similarity.
Yeah, it's gradients.
Okay,
yeah,
so
in our setting, different clients perform different tasks.
So they can be perform different tasks, right? So even
yeah.
Okay, so kind of similar to some multitask learning, right? So some of the tasks may be complementary to each other, like segmentation, depth estimation, maybe surface normal estimation. So that could be eventually like closer to each other, even though they are performing different tasks. Okay.
Yeah. This is our motivation. We want to apply multitask learning. We want to use federated learning to boost the multitask learning because we can group, we can disentangle, because federated learning naturally provides a way to disentangle and combine them together by dynamic grouping the updates of different tasks. We hope there is just like multitask learning, there is a way to dynamically finding this overlapped interests or overlapped information that can be used for different tasks.
Yeah. Another thing is, since you are trying to establish a new problem setting, do you provide like a very easy to use or clear evaluation protocol, or establish some of the baselines so people can, the follow-up work can directly compare, because you are trying to establish a new problem, right? So here I didn't see many of the baseline for the comparison.
Yeah, because our project is still going on. We are trying to include all the baseline as much as possible. After we have done many more experiments, we will release our code.
Okay, sounds good.
Thank you so much.
All right, so if there's no other questions, I think we can conclude the workshop. Thank you so much all for hanging out to the last. So it's good. We have a fabulous program today. So thank all the speakers and all the oral session presenters. Yeah, we hopefully to do this again next year. And by the way, we intend to make all the videos for the speakers and the slides available on the workshop site website. So, but they may take some time for me to process those videos in the slides. So, but yeah, be sure to check out if you want to, maybe going back, check some of the details. Okay, you can check out the website. Okay, and also, I think I also would like to see some of the papers maybe focus on some of the medical imaging problem, right? So because healthcare or medical domain, FL learning is maybe make more sense, right? Because the data privacy of the patient. So we'd love to see some of the papers that maybe using some medical imaging data, right? Since we're doing the computer vision conference, right? You can using some of the medical data as the benchmark database to do some evaluation. So that's just some of my suggestion. And also, if you have any suggestions for the workshop, right? So you have any specific area for the FL
you can definitely let me know. So we may change some of the format of the workshop. So if we have many submissions and a lot of papers get accepted, maybe we'll have a poster session instead of the oral session, so that we can allocate maybe more talks, in the morning have 4, the afternoon have 4. So we have different speakers cover different aspects of federal learning. So yeah, okay. All right, thank you all very much. And we hope you enjoy the rest of the conference. Okay. All right, thank you.